Welcome to UV Physics Academy. So here we are discussing a new technique to solve any quantum circuit. So this lecture series are divided into 5 parts. The first part contains a single qubit quantum gates and with the solved quantum circuit examples. And second part contains a 2-qubit quantum gates and with some quantum circuits. Third one is about equivalent quantum circuits to check whether these quantum circuits equal or not. And fourth one is about some patterns will be repeated in the quantum circuits. So that special patterns I have discussed there in the fourth part. And the fifth part is about 3-qubit quantum gates and some solved examples. So I will solve all these quantum circuits by using this new approach or new method. So I hope you understand this. If you are facing any trouble, please let me know. Okay, thank you. Right. So let us discuss the first part. And here I'm going to introduce this new method. So here I'm using a decimal notation to represent qubit states. So let us discuss what is that. For example, you have number of qubits as a 1. That means we have 1 qubit. Then base states. You know what are the base states for this? That is ket 0 and ket 1. These are binary numbers 0 and 1. But here in the notation, I'm going to use this in a decimal notation, that is a 0 and a 1. That 0 and 1 are a decimal only. Okay. So to represent there exists a 1 qubit, I'm using this suffix 1. Right. So let me explain what is this. For example, here you have 1 qubit. Okay. So generally we will take it as a Q naught LSB. So here I'm going to take this decimal notation. This is very crucial. I'm representing this state as a 1. That means I'm taking that 1 stands for on state. For example, if you take this a qubit, it is having two possibilities, either off or on. If it is off, it takes a 0. If it is on, it takes 1. Okay. So, and I will tell you how I got this idea. One, this is nothing but a 2 power 0 actually. Okay, so that 2 power 0 I have taken as a 1. And let us see the second one. Number of qubits. If you have a number of qubits 2, then generally base states in the decimal notation we have 0 0, 0 1 and 1 0 1 1. So in this method, I'm going to represent this as a 0, but 2 qubits are there, and this is a 1 with the 2 qubits, and this is a 2 with the 2 number of qubits, and this is a 3 like this. Now let me explain what are these states. Here we have a quantum circuit with the 2 qubits, then generally we will take like this. Okay, so I hope you know this. And this is, let us suppose q naught, sorry, this is a q naught and this is a q1. Now this is the LSB 2 power 0, I'm taking it as a 1, and here it is I'm taking a 2 power 1, that is a 2. This notation is a very crucial while we are solving the quantum circuit in this new method. Okay, you will understand slowly, no need to get tension. So the idea came from this is nothing but 2 power 0 and this 2 is nothing but 2 power 1. And let me explain what are these 4 states. For example, you can consider like this. So both states are in off, that is nothing but a 0. Once one is in on, second is in off state, that is 1, and second is on, first one is off, so I can take it as a 2, and both on, so this is nothing but a 3. Okay, right. Like this, if I take another example, that is Let me take the number of qubits as a 3. If you have 3 number of qubits, then base states we have 0 0 like this, 0 0 1, let me write, and 0 1 0 and 0 1 1, and the next 1 0 0 1 0 1 1 1 0 and next 1. So these are the base states in a binary notation, but in this method I'm going to use this as a 0 with the 3 qubits and 1 2 3 and 4 5 6 and 7. These are decimal numbers, and this 3 suffix indicates we have 3 qubits, right? So for example, if you have a 3 qubit quantum gate, sorry, 3 qubit quantum circuit, and let us suppose we have 3 qubits like this, I can take it as a q0, q1 and q2. So now I hope you understand. Here the first one I will take it as a 1 2 power 0, and this is 2 power 1, I will take it as 2, and this is 2 square 4. Now for example, if you have 4 qubits, I hope you understand the next one is 1 2 4 8. In this method these numbers are very crucial. Okay, so for example, I have, what is the meaning of this zero state? So here I have 4 2 1, 3 states are there, that means 4 2 1. You just check how you will get this 0. So 0 state means here 0 plus 0 plus 0, that means all are off. And here 1 we have, this is a 0 plus 0 plus 1. So the only the first one is on and the remaining two are off. And the next, if I take 2, this is nothing but 0 plus 2 plus 0, that means 2 is on, remaining 4 and 1 are off. Next, if I take 3, so this can be written as 0 plus 2 plus 1, and this is 2 is on, this is 0 off. Like this, if I take the 4th and 5 and 6 and 7, so I can write this as a 4 plus a 0 plus a 0, and this is a 4 plus a 0 plus 1, and this is a 6 4 plus 2 plus 0, and the 7 4 plus 2 plus 1. That means here all 3 qubits are on, here first two on, the last second third one is off, here these two on and this is off, and here this fourth one is on, like this. Okay, so if you have 4 number of qubits, its order is a 1 2 4 8, like that. Like this you can take any number of qubits, it's not a problem. Okay, so one more time let me explain briefly. If you have 1 qubit, we will take that as a 1 decimal value, and if you have 2 qubits you have to take it as a 1 2, like this, from LSB to MSB. And if you have 3 qubits you have to take 1 2 4, like that. And 4 number of qubits, 1 2 4 8. So like this you can take n number of qubits, that means uh, it goes from 1 to 2 power n. So these numbers, these are very crucial in solving this quantum circuits in this new method. Okay, so here now next I'm going to start this single qubit quantum gates and some quantum circuits. Okay, so whenever you have single qubit, you know, basis states we have two, that is a 0 and 1. That means that the dimension of Hilbert space, the dimension of Hilbert space is 2. Then if you have this single qubit quantum gate, it is represented by a unitary matrix. So a unitary matrix of order 2, of order 2. So here I'm taking a more general notation like this. I'm taking this matrix as a, sometimes you can take alpha and beta, but I'm taking it as a B, C, D like this. I'll tell you why I have taken like this. Okay. And of course, it is a unitary. That means U dagger U equal to I identity. Okay. So here I have three options are there, three cases. Sorry, three cases. The first case, I'm taking it as that A, B, C, D element, that elements of that unitary matrix, all are non-zero. That means uh, case 1, A comma B comma C comma D. All these elements are not equal to 0. This part is very crucial. I request you please focus. And here this then U equal to A, B, C, D like this. And whenever all the elements are non-zero, what it will do? It will create a linear superposition of qubit states. It creates superposition, superposition of qubit states. You will understand in the examples. No need to get tension. And the second case, we have, let us suppose this A equal to 0 and D is also equal to 0. That means the diagonal elements are 0, but off diagonal elements are not equal to 0. B is not equal to 0 as well as C is not equal to 0. Then the unitary matrix, we can write it as a 0 C and here B 0. So what this type of matrix will do? It will flip the quantum gates, quantum states, flip the qubit states, flip the qubit states. And I will give some examples for this also. First, let me explain the cases. And the last one, case 3, here we have, and A is not equal to 0 and D is not equal to 0. That means the diagonal elements are not equal to 0, but off diagonal elements B equal to C equal to 0. Then this unitary matrix can be written as A, D, and here 0, 0. And this type of gates, they will add a phase to the qubit states, add phase factor, phase to the qubit states. I request you first part please watch this properly, then only you will understand the remaining parts. And here I am going to give some examples for this uh, three cases. The first case, all elements are not equal to 0. You can take a Hadamard gate, that is a 1 over root 2, this 1 1 1 minus 1. And you can take Rx, and Rx and means rotational operator about x axis and a rotational operator about y axis also you can take. So for example, if you have this Rx of theta and Ry of theta, I will write here Rx of theta. This is cos theta by 2 minus I sin theta by 2 and minus I sin theta by 2 and cos theta by 2. If you want that Ry of theta, it is a cos theta by 2 minus a sin theta by 2, and the next element is a sin theta by 2 and the last element is cos theta by 2. And here the case 2 examples where the diagonal elements are 0 and off diagonal elements are non-zero. Here we have Pauli X matrix, that is 0 1 1 0, and Pauli Y matrix, this is a 0 minus I a 0. And the case 3 examples we can take which add a phase to the qubit states. I can take a Z, Pauli Z matrix, which is 1 0 1 0 0 minus 1, and S matrix, that is a 1 0 0 I, and a T, that is a 1 0 0 e power I pi by 4. So this Z gate will add a phase to the qubit state, okay, pi, and here s, this is I is nothing but e power I pi by 2, and here this will add T gate will add e power, I mean pi by 4 phase to the one state. That means whenever the qubit state is on, it will add that phase. If it is in off state, it won't add any phase. That's the point. Okay, and if you see the relation between all these things, you can write a t square. T square means e power I pi by 4 whole square. If you take, you will get e power I pi by 2, which is nothing but I. So that's why t square equal to s. And if I take a t power 4, that means that 4, this e power I pi by 4 whole power 4, you will get e power I pi, which is nothing but minus 1. So that's why I can take a t power 4 as a z, right? Right. So now let us discuss about this first case. So here I have taken the first case where all the elements I am assuming as a non-zero. Examples we have seen Hadamard gate and Rx of theta, and a rotational operator about x-axis and rotational operator about y-axis. And here this creates superposition of qubit states. And in the earlier we have already discussed all these qubit states. We are using this to represent these qubit states, we are using the decimal notation. Okay, now for example, I have a single qubit gate. Let us suppose this is the single qubit gate, which is represented by this unitary operator. Whenever you have only single qubit, you have to take the state notation as a 1. If you have 2 qubits, take it as a 1 2, and if you have 3 qubits, 1 2 4, like that. Okay, so just wait, you will understand what is that. And here the operation is represented by, because this is a single qubit, so operation, this is very crucial. The operation is represented by u of, that means it may be h, it may be rx, it may be ry. So there is no control. I am taking this as a target bit only, because this u operator operates on that state, qubit state. That's why I'm using the word target. So this is a 0 comma t, t for target. Okay. So this target stands for this one, 1. Okay. So either that state will be in off state or in on state. So in this we can write it as u of 0 comma 1, because here it is a 1. Okay, so that means this operation is creating a superposition state of 0 and 1. How it will create? Now let us. Now for example, I request you please see this matrix one more time carefully. This one, we have 2 columns, this first one and second one. Okay, so just take like this, and I request you, this is a very crucial. And here we have first column and this is the second column. Use the first column if the target bit is in off state. Use this first column if target is in off state, and use this second column as amplitudes for the superposition state if target is in on state. I will explain what is the meaning of this. So now I'm going to take this operation. U is operating on 0. This 0 stands for here off state. So then I have to take the first column, this one, AB, as the amplitudes. That means here I can take it as first one A 0, B plus B 1. Remember, you have to take this order. That means 0 1. First you have to take 0, next you have to take 1. Don't change the order. Okay, and next if it is a 1 and this operation U operation, that means this 1 stands for on state. Then you have to take the second column if the target is on. Then this is C 0 plus D 1. Qubit states are 0 and 1 only, because there is only one single qubit, it available either in off state or on state. So that's why 0 and 1. It creates a linear superposition of 0 and 1. with the different amplitudes. So, what I'm saying is this is 0 stands for off state. If it is off state, target is off, use the first column. If a target is on, use the second column. This is very crucial. For all these single qubit gates, whenever target is on, use the second column. Target is off, it is an off state, then use the first column. Okay, let me explain this by using one example, by taking one example. The first one, here I am taking the Hadamard gate. You are familiar with this Hadamard gate, and you know there is only one single qubit, that's why I am taking it as a 1. Just now I discussed what is the operation. This is a h of 0 comma 1. That means this Hadamard operator will create the linear superposition of 0 and 1. Now, just here I am using this notation, zeros first one always off and the second one always on. Whatever the order pair we have, for example, if you have h of 2 comma 3, just assume the first one is off, second one is on. I will explain what is that, no need to get tension. Okay, so the Hadamard operator 1 over root 2, this is 1 1 1 minus 1, sorry. So just now I discussed, just divide that as a first column and second column. Now this I can write at a time, that is 0 and 1. This Hadamard is operate on 0 and 1. Okay, don't take it as a matrix, just take it as a 0 and 1. I'm just writing combinedly. 0 stands for off state, already we have discussed. That's why 1 over root 2 is the uh, outside normalization constant. So for off state we have to take the first column, that is 1 1. So you have 0 plus 1. Remember, this operator always creates the linear superposition of these two decimal states. These are not binary, please remember, decimal only. And the second one, this 1 stands for on state, that's why I have to use the second column. That's why it creates a superposition of 0 and 1, but now it becomes 0 minus 1. If you want to write this in the Ket notation, this is nothing but 1 over root 2 0 plus 1, and this is a 0 minus 1. Now let me take one more example, then you will understand more properly. Second one, I'm using this rotational operator around about x-axis. And we know what is Rx of theta, rotation about x-axis. This is a cos theta by 2 minus I sin theta by 2, and this is also minus I sin theta by 2, and here cos theta by 2. As usual, first column whenever target is off, use the second column whenever target is on. And operation just now I discussed, this is Rx of, this is only single qubit is there, that's why our notation it is a 1. So there is no control, only target, this is a 0 comma 1. So it creates the states 0 and 1 as a superposition of 0 and 1 only. So what does it mean? For example, you have 0, so this is Rx is operating on this, then you have to take the first column because it is off. So this is a cos theta by 2, and here the first one is 0. You have to take that order only, don't change the order please. 0 and minus I sin theta by 2 1. And if it is a 1, Rx operates on this. Now this 1 stands for target is on, then please take the second column as the amplitudes, minus I sin theta by 2, 0 only, order should not be changed, plus cos theta by 2 1. Let me take one more. Third one, still not understanding. There is a single qubit gate, and this is Ry of theta, rotation about a y-axis. First write what is the matrix. So here we have cos theta by 2 minus a sin theta by 2, and this is a sin theta by 2, and the next one is cos theta by 2. I request you please just take the divide into two columns. First one is for off state, second one is for on state. and this operation Ry of, since we have 1 qubit, our decimal notation it is a 1, so this is a 0 comma, that is 1, this one we have to take. If there we have 2, you have to take a 2, if that is a 1, you have to take this 1. When you will get to 2, I will tell you, just wait. Okay, so this is nothing but, here I am writing like this, that means 0 and 1 is there, Ry is operating on that. So 0 is off, we have to take the first column, cos theta by 2, 0, plus a sin theta by 2, k2. And the next one, 1 become, you have to use the second column as the amplitudes, minus a sin theta by 2, 0, plus cos theta by 2, 2. Okay, so just I'm writing with these brackets. Okay, no need to get tension, this is get 0, get 1. Remember, all these 0 and 1 are not at all binary, and here strictly I'm following this decimal notation. I feel little bit easy to solve these quantum circuits by using this notation. If you are facing any trouble, please let me know. And now, for example, now you got it out. Okay, you have taken only one single qubit, that's why, for example, we have 2 qubits and we have combination of a single qubit gates, then how to solve? That means, for example, let us say we have 2 qubit states, and here we have u, this is very crucial, and here the first one, nothing is there means we have identity, nothing is there means identity. Generally what we will do is we will take the tensor product of from top to bottom, that is I, uh, tensor product u. This will give you another unitary matrix, by using that you can operate, but here we are not using that. Now here really you will appreciate this method, how it is useful to solve this type of circuits. Now listen careful. So 2 qubit states are there, so I have to take this as the LSB 1 and this is a 2. Now identity, forget about that identity operator, it won't change any qubit state, just leave it. And here we have u operator, I'm representing this as a b c d, so this creates linear superposition, and the first column and second column I divided, this is off and this is on. Okay, right. Now see how I'm writing the operations, this is very crucial, please listen. Now the operation, here it is the u gate, that means u operator, u of 0 comma, here what is the target? 1, 0 comma 1. And what about the other possibilities? Now see here you have another qubit with a 2, you just add plus 2 to the above operation, that is u of u of this 0 plus 2 is a 2 and that 1 become a 3. That's it. That means whenever you have 2 qubits and a single qubit gate is on that first line, that is LSB, that is 1 here. Okay, then it not only creates a superposition of 0 and 1, it creates a superposition of 2 and 3 also. If you want, you can check by using that tensor product of I tensor u. But this is very easy, very easy. So as usual, first one is off, second one is on. Now see how I'm writing. This is 0, 1, 2, 3. Directly I'm taking, if you don't mind. Okay. Otherwise, I will write separately. So 0 and 1. See here 0 is off, 1 is on. Off means you have to take the first column, that is A 0 plus B 1. Remember, you have to take the superposition of these one 0 and 1 decimal states only. Okay, and the next one we have, this is on, that's why C0 plus D1. That's it. And if I take this 2 3, now see carefully, this 2 is off, that's why A into, remember u of 2 comma 3 means that gate or that operator creates a superposition of 2 and 3. That's why A2 plus B3. And this is 3 stands for on. This is C. You should not change the order. You have to take the same order 2, 3 only. Here. Don't see there. Here, please see here. That is a C2 plus D3. I hope you understand. Still not understanding? No problem. So let us take another example. Please listen. And this time I have the unitary operator or a single qubit gate on the second line. So we have 2 qubits. That's why I'm taking it as a 1 and 2 decimal notation. Now here it is identity, leave it, no need to consider in our method. This is u of 0 comma 2. This time it is on that second line. So that's why 0 comma 2. The remaining is what? 1. So just add that. This is u of 1 comma 3. So total it creates a superposition of 0 and 2 and superposition of 1 and 3 with amplitudes. First column as first column, it use the first column if the target bit is off. It use the second column if the target bit is on. It's very simple. So the first one is always take it as off and second one is always take it as on. So for example, so 0, you can take anything, 0, 2 I am taking. You can take 0, 1, 2, 3 also. Okay. Now let me write all together, then you will understand 0, 1, 2, 3. These are the basis states for 2 qubits. Okay. I hope you know that. And now what this quantum circuit, how this quantum circuit is changing these states. Let us see. 0. Now please carefully see. Here is a 0. Here is a 0 which is in off state. Okay. And one more thing you have to see, that creates a superposition of 0 and 2. So that's why off state A0 plus B2. No confusion. Observe carefully. Next one is 1. Here you have this 1. 1 is in off state. It creates a superposition of 1 and 3. 1 and 3. So that's why this is nothing but C1 plus D3. Oh, I'm sorry. Because it is off state, you have to use the first column. I'm sorry. That is A1 plus B3. Superposition of 1 and 3, but you have to use the amplitudes as the first column because it is off. Next, second, 2, this one. Here we have second one which is on state. That's why you have to use C0 plus D2. Okay. And last one, third one. So here it is an on state. That's why C. This creates a superposition of 1 and 3. That's why you have to take a 1 plus D3. If you have any confusion, you can do like this also. You please take the numbers of this state or anything, it's okay, no problem. If you have any trouble, 0, 2 you can take separately, and after that 1, 3 you can take separately. For example, if you take a 0, that is off, A0 plus B2. If you take 2, it is in on, that's why C0 plus D2. If you have any confusion in writing all this together, you can do like this also. And next 1 is, this is off state, that's why A1 plus B3, and this is a C1 plus D3, like this. Okay. Now let me explain a small example for this 2 qubits. Two qubit states are there, but a single qubit only we are using in the circuit. Now for example, let me take this example. We have head mod gate here, okay, and here nothing is there, but we have 2 qubits. That means identity is there. So 2 qubit states, here it is a 1 and a 2. I hope you are following. And this head mod operator 1 over root 2 1 1 1 minus 1. Let us write the operations. That is a h of 0. Okay, so your target is 1 here because it is on a first state, and after that you have to add whatever the remaining decimal state is there, that is a 2, you have to add that, that is a h of 2 comma 3. Now see, here I'm taking like this 0 2. So why I'm taking for this head mod like this, you will understand. So my advice, whenever you have head mod gate like this, please take first one 0 2. I'll tell you why it is like this. Okay, now this head mod operator is operating on this. Be careful. So 0 is here. Okay, so it creates a superposition of 0 and 1, right? And now this is off state, this is off state, and this 1 and 3 are in on state. So that's why 0 plus 1. 1 over root 2 is outside, no need to get tension. Next 2, this is also off state, that's why here I have to use the first column, that is 2 plus 3. Okay, now I'm using the next one, that is a 1 3. Why I'm using like this, it's very simple. You just change the sign of this middle one, that is a 0 minus 1 and a 2 minus 3. Whenever head mod operators are there, you better to take in that order. Anything you can take, it's not a problem. But if you write the first one, second one is very easy, just to change the middle sign. Because here 0 is in off state and 1 is in on state, that's why I have taken the second column. Here 2 is in the off state, I have taken the first column, and here 3 is in the on state, that's why I have taken a second column. Directly we can write. Still not understanding? Let me take one more example. So if I have head mod gate like this is a 1 and a 2 because the 2 qubits are there. Now observe carefully the operations. H of 0 comma 2, and for this I have to add the remaining one, that is a plus 1, that is a h of 1 comma 3. Okay, so I told you first take that column 0 1 like that, I mean first elements in that bracket, next take the second element. This is for head mod gate, because just only by changing the sign you will get the other one without doing again. So here I am taking a 0 1 head mod gate operating on this 0 1. 0 is an off, so that's why 0 plus 2. Please see in that bracket what you have 0 2. So it creates a superposition of 0 2 only, and it is off, that's why take the first column, that's why 0 plus 2. Next 1. 1 is in off state. What are the numbers there? 1 and 3, that's why it is a 1 plus 3. Now what I am saying is, without doing the next one, you can write directly 2 3. Of course outside normalization constant will be there because the two states are there, and this is a head mod gate. No need to do it because the 2 is in on, 3 is in on, that's why 0 minus 2 1 minus 3. Okay, so still if you are having a trouble, I will take one more example with this rotational matrix. I have 2 qubits, that's why I'm taking a 1 and a 2, and here I have Rx of theta, and here nothing. Okay, that means identity. So first let me write what is this rotational operator. Cos theta by 2 minus I sin theta by 2 minus I sin theta by 2 cos theta by 2, and take this first column off and this is on. Now come to the operations. This is Rx of, since it is on the first one, this is a 0 comma 1. If the operator is on the second one, 0 comma 2. And next what you have to do, you have to add whatever the remaining, that is a 2, that is Rx of 2 comma 3. Okay, now you can take anything here, it's not a problem. Earlier Hadamard gate means for Hadamard gates only I said take the first elements of that bracket. You can take anything 0, 1. So 0 is off and 1 is in on state. So that's why 0 off, you have to take a cos theta by 2, 0, minus I sin theta by 2, 1. You have to take the first column. And 1 is in on state, that's why minus I sin theta by 2. You should not change the order, 0 plus a cos theta by 2, 1. That's it. And the next one, 2, 3. This is not only Rx, sorry, this entire, this entire circuit. And here the 2 is in off state and 3 is in on state. That's why I'm taking cos theta by 2, but it creates a superposition of 2 and 3. So that's why minus I sin theta by 2, 3 here. And that 3 minus I sin theta by 2, 2 plus cos theta by 2, 3. That's it. Okay. So now you got a doubt. For example, I have 3 qubits, then somewhere in the middle I have a single qubit gate. Then how to do this? I will explain one example. After that you can do it. Now for example, I have 3 qubits states. Let us say like this. And what is our decimal notation here? 1, 2, 4. Fine. Now for example, you have this single qubit gate on the second one, and remaining are empty, means we have identity operators. Then you have to, if you want to create the entire unitary operator of the circuit, you have to take the tensor product of I, tensor U, tensor I. So I hope you know this. This method already is there. Okay, but without finding the tensor product, we are writing here. So then how to get these operations? Now listen carefully. Always we have to take the first one as that operation, that operator U, on which state it is a second state. That's why I am taking it as U of 0 comma 2. And then you have to add. Which one you have to add? Then you got a doubt. Remember, anything you can add, either 4 or 1. But my advice, so please add least one, least to highest. That means first I am adding plus 1. This is very crucial. I request you please listen. Now you got the two operations. It will create the superposition of 0, 2 and 1, 3. Next, one more is left. What's that? 4. That fourth one you have to add for these both. Okay. That means you have to add 4 to this both operations. Then you will get another two operations, that is u of 4 comma 6. This is u of 5 comma 7. Okay. So this is the technique. Or for example, if you add first 4 here, then you will get 4 comma 6. Then you have to add 1 to both the operations. So total it creates 4 operations: 0, 2, 1, 3, 4, 6 and 5, 7. That means it will change 0, 2. I mean, it creates a superposition of 0, 2, 1, 3 and 4, 6 and 5, 7. If any number is not there, means there is no change. That's the point. Okay, so I hope you understand this 3 qubits. Let me take one small example, then you will understand. So one more time I'm saying, you have 3 qubits. So 1, 2, 4, and I'm taking this head mod gate here, and the remaining are identity. Okay, so if you want, you can take identity. Then by using our notation, how to write these operations? This is a h of 0 comma 2. Now you are here, I hope you understand. Anything you can add, but I am adding a lowest number to highest number like that. So first one I am adding 1, that is a h of 1 comma 3, and this is a plus 1. So for this both we have to add a 4. That's why it become h of 4 comma 6, and this is a h of 5 comma 7. Then how to write? I told you already, please take the, whenever head mod operation is there, please take the first elements in the bracket, that is 0, 1, and here 4 and 5 are off, and the second one is in on state. I'm taking 0, 1 or 4, 5. So at a time I can take, no issue, because the second one is very easy to write, head mod operation. So the 0 is in off state, it creates a superposition of 0 2, and a head mod operator, you know, 1 over root 2, 1 1 1 minus 1. So please take the first column if it is off, and take the second column if it is in on state. 0 off state, that's why 0 plus 2. 1 off state, 1 plus 3. I hope you are observing. And 4 off state here. Okay, so then it creates a superposition of 4 and 6. So that is 4 plus 6. And next we have 5, it creates a superposition of 5 and 7, and this is a 5 plus 7, because the first column we have to use. And once you have written this, you can take the normalization constant 1 by root 2, because the two states are there. And now it's very easy to write the other states, that is a 2, 3, 6, 7. I'm taking the second elements in the bracket, which are in on state. All these are off and all these are on. Especially whenever you are dealing with this head mod gates, better to take like this, because without doing anything, directly we can write the middle one, whatever the middle sign we have, just change, just take opposite, that is 0 minus 2, 1 minus 3, 4 minus 6, 5 minus 7. But whenever you are having some other combination of quantum gates, maybe sometimes you will get a minus here, then you have to take the opposite plus. That's it. You will get the answer directly. So that's it. If you want, you can check with the tensor product also. It's not a big deal. Okay, right. I hope you are understanding this method. If you are facing any trouble, so please let me know. Okay, now let us go to the type 2. So here I'm taking this type 2, where we have this unitary matrix, this A, B, C, D, and I'm taking this A as a 0 and D as a 0, and C and B are not equal to 0. That means this is a 0, B, C, 0. So we have already discussed, and what it will do, it will flip a qubit states. So this is just an alternate way or alternate method to solve these quantum circuits. Okay, so fine. Now examples, if you have, let me take it directly. So because I have already explained that operation, that is 0 comma t, t for target, whatever you have. So I'm taking this single qubit x. So here we have single qubit, that's why it is 1. Now this operation is represented by x of 0 comma 1. Now earlier I told you u of 0 comma 1, it creates a superposition state of 0 and 1. Now this is a Pauli X gate, and type 2, what it will do, it will flip the qubit states. That means it flip 0 and 1, 0 to 1, 1 to 0. So that means you need not to find any matrix. Directly you can write 0 to 1 and 1 to 0. Okay, right. And if I take a second one, let us take a Pauli Y gate, a single qubit gate, and since it is a single qubit, it is a 1. And let me write this X matrix also, then you will understand. This is a 0 1 1 0, and here this Y operator 0 minus I 0. Observe carefully, this is also superposition only, because once the first one element is a 0, one amplitude is 0, that's why I'm using that. It is flipping the quantum state or something like that. This is also superposition only. This is off and this is on. Now the operation is represented by Y of 0 comma target. Here target is 1. Now 0 stands for off, 1 stands for on. So 0 operates on this, Y operates on this 0 state. We have to take 0I. That means flip with the phase. Observe carefully. It will flip and add this phase. And if the target is on, it will flip the bit, qubit, and add this phase. So I hope you understand what I'm saying. First column contains I, that's why I1. Flip with some phase I. And 1, so it flip 0, but with the phase factor minus I. Okay, that's it. So you can represent like this also. Whenever you have 0 state and 1 state, if this is X gate is there, 0 to 1, 1 to 0. And if it is a Pauli Y gate is there, we have 0 and a 1. Remember, all these are decimal states only, decimal notations. The qubit states, but I am using the decimal notation because it is a single qubit. That's why as a both are similar only, 0 and 1 only. So 0 to 1 flip with a phase factor I, 1 to 0 flip with a phase factor minus I. Next, let us take type 3. I hope this is type 2 and type 3. Here I am taking this diagonal elements are non-zero, that is A, D, and off diagonal elements are 0. So this will just add up because you will get the same state again. That's why I'm using the word, it will add phase to the qubit states. This is also superposition. Okay, add a phase to qubit states. Okay, so as usual, you have to divide this into two columns. First column, if the target is off. Second column, you have to use if the target is on. Now I'm taking a direct example. This is JET gate. So here single qubit, that's why it is represented by 1. Okay, and the operation is as usual same, that is a 0 comma 1. Remember, so 0, first one is off, second one is on. Always first one is off, second one is on, like that please take. Okay, now so just it will add phase to the qubit state, it won't flip any bit, any qubit. That means the 0 become 0 with the phase of that here. Here we have A, but in this case Z is nothing but 1 0 0 minus 1. This is off and on, that's why it is a plus only. And next, if I take 1, it is in on state, I have to take the second column, that's why minus 1. Let me write here also. So here 0 to 0 become A into 0 and 1 become D into 1, like this. If you have a single qubit and this is a 1, operation is U of 0 comma 1. Let me take one more example, and here I have the S, the phase gate, S gate. So operation is here it is 1, S of 0 comma 1 and S matrix. Let me write the S matrix here. This is 1 0 0 I. This is off, this is on. Now here I have 0 1, and this S gate operates on 0 and 1. So since 0 is off, 1 is on, so no change, that is a 0 only. If it is a 1, it add a phase of I, that is a I1. So I can write this as a 0 and this is I1. And let me take one more example, third one. This is a T gate I am taking, single qubit 1. So the operation is a T of 0 comma 1, and T operator unitary matrix 1 0 0 e raised to I pi by 4. So this is off, on, and first column off, second column on. So that's why the 0 1 gives 0 no change, and 1 will be having a extra phase factor of e raised to I pi by 4 1. So if you have a problem, you can add this Dirac notation like this. Okay. So whether it is type 1 or type 2 or type 3, we are taking that matrix and using the first column as the amplitudes if target bit is off. We are using the second column as the amplitudes if the target bit is on. Now you got one more doubt. So you have explained separately, if I have the combination of, let us say, this H, Z, T, or something like that. If all these gates are there, then how to solve? I will explain that also. Okay. So now here I am taking some examples involving single qubit quantum gates. Now first one, here I have this 2 qubits I am taking. Okay. So here I have H, and let us say this is a Z. So please use our notation. Two qubits are there. So that's why here I am taking 1 and 2. Observe carefully. See here, you can take, generally will take from, whenever you are taking the tensor product, you will take top to bottom. But this operation, it's not a problem, but my advice, please take from top to bottom only, or you can take anything, because the reason is a Z you can slide like this, that means a Z is operating first. If you just slide H this side, that H is operating first. Here I'm going with the operations, not a tensor product. Okay, so that's it. I can take anything, so I'm taking H first. H of, I hope you understand already, it is here 1, that's why 0 comma 1. But remember, one more qubit left, that is a 2, you have to add, that is a H of 2 comma 3. Just strike a line. We have one more gate, that is Z of 0, because there is no control. The target is 2. But this time you have to add 1, because 1 is remaining, that is Z of 1 comma 3. Then how to operate this combined? This is very crucial. Now I told you, whenever head mod is involving, so better to take that first elements of that bracket, that is a 0 and a 2. Okay, I'm taking that 0 2. Observe carefully, it's easy only. Now first I'm operating a H, because anything you can take, either H or Z, because it is operation, not a tensor product. H you can take, it's not a problem. So 0 is off, and first one is off, second one is on always. Already we have seen that head mod gate, no need to write that head mod operator or matrix. 0 off state, that's why it creates a superposition of, be careful, it creates a superposition of this one, 0 and 1. Okay, right. So that's why this is a 0 plus 1. And the next 2 is also in off state, but it creates a superposition of 2 and 3. Off state means first column 2 plus 3. Next, Z is operating on that. Now come to this Z operations. Already we have seen Z operation, it won't change, it won't flip any state, okay, it will just add a phase factor. For which one? If it is in on state. Which states are in on state? It's very easy to observe. 2 and 3 are in on state. 0 and 1 are in off state. That's it. So here 0 off, that's why 0 only. 1 off, that's why 1 only. Next 2, it is in on state, that's why -2. And next 3, it is in on state, that's why -3 over. Next we have to take another one, that is 1 3, 1 3 here. That means the next elements of that bracket, that is 1 3. This is what I said. Whenever you are having head mod, if you take like that, this is the advantage. You need not to do it again. For example, this 1 is in on state, that's why here you will get a 0 plus, sorry, on state, that's why I have to take the second column, 0 minus 1. See, if you observe carefully, here plus is there, I am taking minus here. And a third, sorry, 3, it is in on state, that's why 2 minus 3. Without doing all these things, we can directly simply change the sign in the middle. Please remember this one, this one. So here 0 minus 1, 0 plus 1, and here, oh, I'm sorry, here. So this is the first answer, and if you want to get the second answer directly, whatever the sign in the middle, just change that. 0 minus 1. Here sign in the middle is minus, that's why -2 plus 3. That's it. If you want, you can check. So Z is operating on 2. So here 2 is on, that's why -2. And 3, that is on state. That's why Z operate on -3. It will become +3. That's it. So this is what I am saying. If you have header mod operator, take this 0 to first, and after that 1 3 next. Okay, now that's it, because we have 2 qubits. And take one more example, still not understanding. If you have any confusion, take one more example. Let me take a H here, header mod, and I'm taking a T. Okay, right. So this is 1 and here it is a 2. First you have to write that decimal states, and now operations. Observe carefully. I can write H first, next T, or T first, H next. It's not a problem. Operations, no issue here, because uh, there is no control here. It's okay. Now I'm taking H. So 0 comma, it is on 2, and you have to add the next one, remaining is 1. That's why H of 1 comma 3. You have to add that 1 to both the elements of that bracket. And the next T, it is on first state, that's why 0 comma 1, and I have to add 2 now, that is a 2 comma 3. And always off and on, first one is off, second one is on. Okay, right. Head mod is, I hope you understand. If it is off, plus plus, if it is on, plus minus, that means second one is minus. And if you forget this T operator, 100 e power I pi by 4 I am taking. And head mod also I will write, if you want, 1 over root 2, 1 1 1 minus 1, off on, and this is off on. Now here also I am taking, I told you 0 and 1 I am taking, because here see this one. If it is a head mod, I will take like this. Otherwise, anything you can take, it's not a problem. Okay. Sorry. Head mod is operating on 0 and 1. 0 is off. It creates a superposition of 0 and 2, 0 plus 2, because off. And next 1, it is also off, but it creates a superposition of 1 and 3. So that's why it is a 1 plus 3. Next T is operating. Now observe carefully. 0 off, no change. 2 is off, no change. But 1 is in on state, because second one is on, second element in that bracket is on, first element in that bracket is off. One on, that's why it will add a phase factor of e power I pi by 4. I'm using that Dirac notation. 3 is also on, e raised to I pi by 4, 3. Here also you can use if you want, it's not a trouble. Now the next one, no need to do it directly, you can write the next remaining second column. If I take here, this is a second column, then I will write it as 2 3. This is the advantage. Directly here I am writing, trying to write the answer. You please do it and check. So just I am changing the sign in the middle. This is the middle sign, that is 0 minus 2, and this is e raised to I pi by 4 1 minus e raised to I pi by 4 3, like this. Okay, right. So like this we can do. Now you got a doubt. So whether this is right or wrong, how to check? For this, I will use this quantum simulator, circuit simulator. Wait, just wait. Okay. Now, please take that first one, that is a Z and a H gates. So I'm taking this one. Okay. So here first I'm taking Z and this is a H. So if you have 0 0, that is a 0. And here one small issue is there, and whatever the state we are having, if you click that, so that is showing that 1 0. Remember, you have to take it in a reverse way. Okay, so in this they are taking top to bottom, but I am writing bottom to top, so that is a small correction you have to take from this. But don't worry, it's correct only. I have verified with this matrix multiplication also, and if you want you can also check with the tensor product. And here 0 0, that means if you see the first one 0, final answer is this one, 0 and 1. Now if you see that circuit, they are showing here 2. That's what I am saying. They have given that ket 1 0. Please observe that 1 0. Okay, sorry, yeah, 1 0. You please take it in a reverse one, a 0 1. Then it is a decimal 1. Okay, so this is simulator and my method, that is having a small change. That is, I have taken from bottom to top and they have taken top to bottom. Okay, so and the next one is a 0 only. That's not a problem, all are zeros, that's why there is no change. And see the next one, I'm taking a here changing the 1. That means here I have taken one decimal, but one decimal, that is a 0, sorry, 0, and this is 1. So let me go through this. 1, here you have 1, so 1 become 0 minus 1. Of course 1 by root 2 will be there. So here let me write this normalization factor, I forgot, 1 by root 2. Okay, and here also let me write finally 1 by root 2 is the normalization factor. Okay, although if I forget that normalization factor, I hope finally 2 states are there, take 1 by root 2, 3 states are there, take 1 by root 3, 4 states are there, take 1 by root 4. Okay, right. Yeah, here we are checking this one, we got 0 minus 1. Now see that circuit, here this one 0, phase is a 0 only, no problem. And this a second one, phase is 180, that means minus 1. Okay, uh, and this is a small confusion to you, but don't worry, it's exactly right whatever I'm saying. So you just change the order. It's not 1 0, it is a 0 1 and the decimal 1. That's it. And can check 3, that is both I have taken 1 1 input. Okay, then here we have a decimal 1, but remember that is a decimal, not a decimal 1, it's a decimal 2, because we have to take from bottom to top, that is a 1 0, it's a 2. And phase is a minus 1, because 180 degrees phase is there, we will get minus 1. And this one 1 1. So let us check. Here we have 3, this is minus 2 plus 3, exactly. So here this is 2 only, one more time I'm saying, and this is a 3. 3 is having a phase plus 1 here, I mean 0 phase, that is a plus 1, and this phase is 180, we have minus. Like this you can check. The second one also, if you want, I will check, that is a HT. Okay, so here the first one I'm taking H, and next I will take this HT. So here already we have taken input as 1 1, that means a 3. So let us check. And, this is a combination of decimal 2 they have given, but remember it is a decimal 1 with a plus 45 phase change, and the next decimal 3 with the phase change minus 135. Okay, let us see. And here, sorry, here I am checking this third one. Okay, so see, this is the phase difference, pi by 4 plus 45 and 1 only. It's not a decimal 2, it's a 1. As per my notation, it's a decimal 1 only. If you want, you can check that the tensor product and check, you will get this one. And third one, we are having a minus pi by 4. Minus stands for what? That e power I pi or minus I pi, and pi by 4. If you add, you will get 135. 3 pi by 4 you will get, minus 3 pi by 4 you will get. So that's why you are having this minus 135 here, minus 135. I hope you are seeing this. Like this you can check. And the last one I would like to discuss about this Hadamard gate. If you want one more example, I will take. If still having confusion, I will take one more example. So here I have 2 qubits. That's why I'm taking 1 and 2. So here I'm taking this Hadamard, and here I'm taking this Rx of theta, the rotation about x-axis, and here this Hadamard gate I have taken. Okay, so I hope you remember these matrices. Now let me write the operations first. So this is a h of 0, it is on 1, that's why 0 comma 1, and you have to add the second one, that is a h of 2 comma 3, and here Rx, it is on 2, that's why 0 comma 2, and next one you have to add 1. Okay, so since it is a Hadamard, first I am taking a 0 2. Okay, right. So 0 is off, that's why 0 plus 1. See, directly I am writing because it creates a superposition of 0 and 1. And a 2, that is also off, it creates a 2 plus 3. Normalization constant finally I will write. If you otherwise, if you want, you can write here. And the next Rx operation. Okay, so Rx operation, this is off and on. Maybe if you forget, I will write that Rx theta cos theta by 2 minus I sin theta by 2 minus I sin theta by 2 and cos theta by 2. Now here we have this is off and on. Okay, so let us see. No need to get tension. So here you have 0. 0 is off. Come to this Rx operations. Now you are operating Rx. 0 is off. That's why cos theta by 2. Remember, it creates a superposition of 0 and 2. Cos theta by 2 0 minus, I have to take the first column, minus sin theta by 2 2. Okay, and here I have no space, that's why I'm using plus here, this middle plus. Next 1. 1 is also in off state. Here see this first one, 1 here off state. That's why the same thing, cos theta by 2, but it creates a superposition of 1 and 3. So cos theta by 2 1 minus I sin theta by 2 3. This is the first one actually. Okay, and the next one, if you take this 2 is in on state, that's why uh, minus I sine theta by 2, 2 here we have 0 2, that's why superposition of 0 plus cos theta by 2, you have to use the second column plus, okay, and the next one 3, that is you have to use the second column, but 3 it creates a superposition of 1 and 3 minus sine minus I sine theta by 2 1 plus cos theta by 2 at 3. Okay, now you need not worry about the another one. So just now I told you the next column here, the sorry, next elements here 1 and 3 I am taking. So this 1 3, I need not to do all these things. Where is the middle sign? Please observe, the middle sign is this one. Just change that. So here cos theta by 2 0 minus I sine theta by 2, sorry, 2 minus cos theta by 2 1, just I am taking a bracket, minus I sine theta by 2 3. Okay, and the next one, this is minus, here this is the middle sign I am changing, please observe carefully because only this middle sign will change. So minus I sine theta by 2 1 plus yeah, sorry, 0 plus cos theta by 2 2, the middle sign plus, here it is a minus I sine theta by 2 1 plus cos theta by 2 3. Like this we can write directly. Now let us check whether this is right or wrong. Okay, but in this simulator it is not possible to check, but better to take some theta value and you can check. So here the first one is Rx. Okay, so I'm taking this Rx, and the next one is Hadamard 0, and this is a 0. If you observe carefully, all 4 states are there, please check. I hope you are observing. And which one are having a phase change? This one, left top one is having phase 0, that is a 0. And here I told you already, don't take it as a 1 0, please take it as a 0 1, that is also having a no phase change. So 0 and 1 no phase change, but uh, 2 and 3 are having a phase difference minus I, because there is a, sorry, minus I pi by 2, minus I pi by 2 e raised to minus I pi by 2 something. Let us check what we got. Mm, yeah, this one. See here carefully. So 0 and 1 we are having a plus, if you observe carefully, but 2 and 3 we are having a minus. Or if you just give some theta value here, now let me change this. I'm taking it as a pi by 4. Shall I take pi by 4 or pi by I'll take pi only, pi by 2. See, only 2 states are there. Maybe somewhere you got a cos value or sine value, maybe 0. So just substitute theta is equal to pi by 2 here and check. Now I'm taking a theta as a pi by 2. 1 minute. I'm sorry, here I have taken pi. Okay, so if I take a theta as a pi, okay, then we got only 2 states. One is 3 with phase difference with the phase minus 90, and another one here it is 0 1 means 1 0, 2 with phase difference minus 90. Now let us check. Now theta is equal to, we have taken pi, then cos pi by 2 0. So that's why we have, for 0 state we have minus I 2, that means 0 2, let me write properly. Then final answer here I am writing cos 90 0, this is a minus I 2 and this is a minus I 3. And similarly 1 3 if I take, and this also cos 90 0, and here it is, oh I'm sorry, I have to write like this, minus I 2 minus I 3. And second one cos 90 0, cos 90 0, that's why it is a minus I 0 minus I 1, and 1 3. Okay, so this is minus I 2 plus I 3, and minus I 0, and plus I 1. No need to worry, just change the middle signs. You will get the second one as whenever you have this head mod operation in the beginning. That's it. You can check like this also. If you want, you can take theta as a pi by 2 also. Let me write, so pi by 2. Okay, now then you will be having a four states. Why? Because this cos pi by 4, sin pi by 4, nothing will be 0. That's why you'll be having a combination of superposition of all those 4 states, 0 1 2 3. That's it. Okay, so I hope you understand this method. So I will give a few examples, so try yourself. Okay, if you are facing any trouble, please let me know. And here head mod I am taking here, this time ry of theta I am taking here, and the second one try yourself, and here rx of theta, and here ry of theta. And third example I will give, let us take a z here, and rx of theta, and fourth one let us take mm, yeah, so take both head mods, try to do it. Okay, so these are 4 examples. I request you please try and start like this, 1 2 1 2 1 2 1 2, like this, and write the operations first, and then uh, take the initial state and proceed. Okay, if you are facing any trouble, please inform. Okay, so thank you. I hope you understand this new technique, and in the next lecture you like more, because 2-qubit quantum gates, whenever we consider, uh, if there are many quantum gates, you will get you will face difficulty to solve the quantum circuit. But with this method it is very easy, and we will discuss about the 2-qubit quantum gates in the next lecture. Okay, thank you. Welcome to UV Physics. So I request you please watch the first video, first class video, before going to watch the second or third lectures. Because here we are introducing a new method to solve any type of a quantum circuit, 2-qubit, 3-qubit, any circuit you can solve. So here we are introducing a decimal notation to represent the qubit states. uh, it's a new method and a new approach. So I request you first watch the lecture number 1 before watching the other lectures, and let us continue the second lecture now. Welcome back. And in the first lecture we have discussed about this single qubit quantum gates, and we have explained a few examples of quantum circuits. I hope you understand that method, and this 2-qubit quantum gates is really interesting. Let us start. So whenever you have 2-qubit quantum gates, and this is represented by this CU, C for control, and U. This U stands for this a single qubit quantum gate. That means unitary operator corresponding to a single qubit quantum gate. Now we can represent like this. We have two qubits. This is the control and this is the target. Okay, and here we have this unitary operation, just I'm taking it as one. And I have already discussed the decimal notation. Since we have two qubits, the decimal notation will give you here 1 and here 2. Observe carefully. This is really interesting. Generally, what we will discuss in this two qubits, here we have control bit. It is having two options. Maybe it is in off state or it is in on state. For example, if I take a c equal to 0, that means off, or c equal to 1, it will be in on state. If c is in off state, what about the final state? The final state is nothing but there is no change, that is a ct only. If a control bit is on, that means the final state is nothing but c, and this operation u operates on that target if the control is on, means ut. This you know already, I hope. Now what I'm explaining in this new technique, so earlier we have written a single qubit quantum gate operation as u of 0 comma whatever the target, it is 1 2 3, anything you can take it as, you can take that target. But here the operation, this is very crucial, the operation is represented by, and let me write this u matrix also. This u matrix I am taking it as a b c d, generally anything you can take, but same thing, no change. First column you have to use whenever target is off, second column you have to use whenever target is on, no change. Okay, right. Now the operation is represented by, this is a u of, it may be x, it may be head mod, it may be z, or it may be s, anything. So u of, see carefully, earlier we have taken 0, now it is a c, c for control. Remember, you have to take the decimal value of that control in my method, don't forget this. So c comma c plus t, that's it. So what is this? I didn't understand. Yeah, let me explain. Now in this present example, if I take like this is CU control operation, this is a control and this is target. I have decimal notation, I told you 1 and 2. Okay, as per this, this is a U of, here what is the control? 2. That's why 2 comma C plus T. C is 2 and T is 1. C plus 2. Sorry, C plus T. That is 2 plus 1 is nothing but 3. Okay, this will create a superposition of 2 and 3. It depends upon the type of that unitary matrix. Okay, type 1, type 2, type 3, anything. Okay, more general one is type 1 only. Okay, right. So that means what? For example, if you have 2 3, just I'm taking combinedly like this, and what this circuit will do, this total circuit actually. Okay, so we have already taken u as a abcd, this unitary matrix. Okay, so 2 is in yeah, the same thing, same technique, whatever I have explained. This 2 is off and 3 is on. That's why it will take A2 plus B3. Since 3 is in on state, you have to take the second column, C2 plus D3. That's it. Now, what about the other two states, that is 0 and 1? No change. Okay, because 0 1 not came here. That's why 0 1, the circuit won't do anything. Now let me take example, then you will understand. Okay, so let us start with this C naught. The first one, I'm taking this C naught gate. Okay, so here we have two qubits. This is a control and this is x. This is a CX. We have two qubits in our notation. We have to take it as 1 and 2. Now see, so simple, very easy, very easy. Now here u is nothing but x. X, that is a type 2, it will flip. So here the control is 2 and the target is 1. Just now I said c comma c plus t, that is nothing but x of 2 comma 2 plus 1 3. Just take the control and come to the target, add 2 plus 1 3. So that means if you have 2 3, it will, this 2 3 circuit will make it as 3 2. And what about 0 1? No change, no change in this 0 1. Let me take one more example. So I'm taking a CH, control H, okay. So this is 1 and 2, okay. So our unitary operator is a H here. It's very simple. First come to the target, sorry, first come to the control. Control is 2, comma, come to the target, that is a 1, 2 plus 1 3. So it creates only superposition of 2 and 3. It won't change that 0 and 1. So 2 is off, 3 is on, that means 2 3, 2 3, 2 off, that's why 2 plus 3, 3 on, 2 minus 3. If you practice that first lecture, you can write very easily. Of course, normalization constant will be there, that is 1 over root. If you want to write properly, you can write this as 1 over root 2 ket 2 plus ket 3, and this is ket 2 minus ket 3. And what about 0 and 1? No change, no change in 0 and 1. Let us take one more, that is here I am taking this time control Z I am taking 1 and 2. This is a Z, no need to write CZ, just Z only, because operation depends on that operator Z only. Control is 2, 2, 2, 1, 2, 2, 1. Just say like this, 2, 2, 1. From where it is coming? 2 and it coming to 1, 2, 2, 1. That is 2 comma 3. So this is 2 off and 3 on. And you know what is the Z operator? 1, 1, sorry, 1, 0, 0 minus 1. Off and on. So Z won't flip anything, it will give the same state with the phase changes, that's it. That means 2, 3. The first column 1, that's why 2 only. Second column you have minus 1, that is minus 3. Clear? And 0, 1. So this is a no change 0, 1. And next fourth one, I am taking this as let me take a T gate, control T. So here it is again 1 2, and you have to write a T from where to where? 2 to 1, that's why 2 comma 3. 2 is off, 3 is on, and T operator 1 0 0 e power I pi by 4. First column off, second column on, that is 2 3, 2 is off, no change, 3 on, that's why phase change, e raised to I pi by 4 3. And there is no change in the 0 1. Okay. And if you want, I will take few more examples. That is, here I am taking control S. Okay, 1 2. So just take S from where to where? 2 to 1. That's why 2 comma 3. Off and on. S matrix 1 0 0 I. So this is off and on. 2 3. The circuit, what it will do? 2 off, because we have first column 1 0, that's why 2 only, and 3, there is a phase change I 3. I means here the phase change is pi by 2. Okay, so because e raised to I pi by 2 equal to I, right? Okay, and take another example also. Here I have Rx, and again I'm taking 1 2, and the operation Rx of from where to where? 2 comma 3 you have to add that target to the control. 2 starting comma, add that target bit to the see decimal addition only, no binary, it's a normal decimal addition only. Okay, right. So Rx operator, let me write, maybe you forgot, cos theta by 2 minus I sin theta by 2 and minus I sin theta by 2 cos theta by 2. So if you practice like this, definitely it will be very easy. And here we have 2 3. So what it will do, this 2 is off, that's why cos theta by 2 2 minus I sin theta by 2 3, and 3 is in on state, that is a minus I sin theta by 2 2 plus cos theta by 2 3. Like this you can proceed. Any examples? And I request you please try this last one yourself, that is 1 2 we have here, sorry, I will give this, you have to remember. And this is ry of theta. So fine for this. Okay, right. Okay, so here we have seen this control U operations, that is a 2-qubit quantum gates. Now sometimes that control and the target bits will be interchanged. Then how to proceed with this new technique? Okay, so let me take that. Sometimes control and T qubits are interchanged. Then how to do this? Okay, so here I'm taking the, so earlier the first one is control and the next one is a target. Now I'm taking a reverse like this. So no problem. Now this is a control and this is a target. Remember, we are using the decimal notation, that is here 1 and here 2. So always you have to go from control to target, control bit to target, use that decimal states addition. Okay, so now this is a I'm taking the U operator as a B C D, and this one is as usual, first column for off, second column for on, and this operation can be written as U off. Now where is the starting one? Control 1 comma, you are going to 2, that is 1 plus 2 3, that's it. So it creates a superposition of 1 and 3. And what about 0 2? It won't do anything. That's it. So 1 3 and the circuit. Here 1 is off, 3 is on. That's why A1 plus B3 first column, and 3 is on. That's why second column, C1 and D3. You should not write C3 and D1. Please remember order, that 1 3 order must be always the same. Let us take some examples. First one, I'm taking this reverse C naught gate. Okay, so as per our notation, this is 1 comma 1 2, and this is x, from where we are starting from 1 to 1 plus 2, that is 3. So it will flip 1 and 3 only. 1 3 will become, because x is having that flip operation, that is a 3 1. And what about 0 2? No change. Sorry. And let us take the second. Here you have a reverse control jet, that means a target and control bits are interchanged. Here 1 and 2. So same thing, starting from 1 going to 2, 1 plus 2, that is a 3. And you know this is off and this is on. Okay, you know Z operation already. Off state means no change, on state means add the phase of that pi, that is -1 will be added. So here it is 1 3, 1 no change because it is off, 3 this is a -3. And what about 0 to? No change. Wait a minute. Somewhere we have this same answer. 1 to 1, 0 to 0, 2 to 2, but 3 become minus 3. Somewhere we have seen this. Wait a minute. Yeah, here. See here. 0 and 1, no change. 2 also no change. And 3 change to minus 3. So that means we can conclude like this. Whenever if you have a control Z gate, okay, if a control and a target qubits are interchanged, there is no change in the CZ operation. That means if C and T are interchanged, so no change in CZ control Z operation. So we can represent like this. This is control and this is target. Here we have this CZ gate. This is equivalent to uh, control and targets are interchanged. So here this time this is control and this is target and both are same. Okay. So I hope you understand this, and still if you want some more examples, I will take this one. So here I have ry of theta I have taken and this one. Okay. So here 1 and 2. So this is ry of, from where we are starting, from 1 where we are going to 1 plus 2, 3. So this is off and this is on. Please write Rx of theta operator, sorry, Ry, I'm sorry, Ry. So this is a cos theta by 2 minus a sin theta by 2, and this is a sin theta by 2 and a cos theta by 2. As usual, first column is off, second column is on. So here let me take 1, 3, and what this circuit will do, this 1 is in off, that's why you have to take the first column, cos theta by 2, 1, plus a sin theta by 2, 3. And next 3 is in on state, that's why you have to take the second column, minus a sin theta by 2, 1, plus cos theta by 2, 3. And what about 0 and 2? It won't change. Like this, okay? Okay, now let us extend this to some other thing. You can take one more example if you want. I will end this, or you please try rz of theta. I request you please try this. And if you don't know this rz of theta, let me write. This is e raised to minus I theta by 2, 0, 0, e raised to I theta by 2. Okay, so remember, whatever this control and target interchange or not interchange does not matter. First always come start with the control. So start with the control bit and going towards the target, that means u of c comma c plus t. First to take the control and next add control and target. Decimal notation, decimal addition only, no binary addition. Okay, so you please try and check. Okay, next let us take a very interesting one, combination of quantum gates. Now here I am taking some combination of quantum gates. So till now we have discussed the single qubit quantum gates and 2-qubit quantum gates. Let us combine both, then how it will be. Okay, but remember a few points while we are doing this a combination of quantum gates. Remember, uh, generally the order is top to bottom. Okay, so because here control bits, control control unitary operation is there, that means control cu gate is there, that is 2-qubit gate. That's why my advice, now please take from top to bottom. If you have single qubits, you can take order, it's not a problem. But in the middle, if you have any C naught gate or CU gate, then little bit careful. So that's why finally we'll conclude this point here like this. Always take the order from top to bottom, and the next left to right. See, maybe you heard this whenever you are multiplying, you have taken right to left. Maybe somewhere you read this also. Whenever you are writing the matrices, you have written from right to left. The reason is, see, this is the initial state, and here you have one operator, here you have one operator. If you write from right matrix to left matrix, then only this left side matrix will operate on this first. That is the reason. But remember, here I'm taking operations first. So that's why I will go from left to right. So don't get confusion. Okay, I'm talking about operations, not matrices. Okay, so take the operations from left to right. No confusion, don't worry. Left to right. Sometimes I used to multiply the matrices, because otherwise if I write all the operators, it become it's a huge operations. I mean, so many operations will come. So then what I will do, I will multiply a few matrices. But whenever you are multiplying the matrices, you have to multiply from right to left only. This one don't forget, please. Okay, matrix multiplication. Always from, this is a general, everybody used to say this only, right to left. So don't forget these are 3 points. Now let me take one small example, then I will discuss. First one, here I have 2 qubits. It's a very nice, very interesting one. Please listen carefully. Here this is a 1 and a 2. I'm taking a H gate here and a C naught here. Then how to solve this? Okay. Now here we have two quantum gates. One is H, another is a C naught. You can start with H. I told you we have to go from operations, go from left to right only. Always write the operations from left to right. But whenever, in case if you are multiplying any operations, multiply from right to left, because we will multiply as matrices. We can't multiply the operations directly. We'll multiply them as matrices. Okay, please remember this. Now I'm going from left to right only. So this is the first one, H. See, this is on 2. This is a single one. It's a single quantum bit. That's why 0 comma target is 2. Now what's the remaining? 1 is remaining. That's why add 1 comma 3. Next one, 2 qubit quantum gate. That is a C naught. Okay, that is X. Where you are starting? 2. That is 2. And you are coming to 1. That is a 2 plus 1, 3. That's it. It won't do any other operation. Now, I told you earlier, if you have a head mod operator, please take the first column. And remember, always off, on, off, on, off, on. Okay, right. So I'm taking this 0 and 1. First a head mod. So 0 is off. That's why 0 plus 2. I hope now you understand. 1, it is also off. It creates a superposition. 1 plus 3. Okay, why you have taken plus plus? Because first column is 1 1. Next you have to operate X operator, because you are coming from left to right, and it won't do anything this is with the 0, but 2 will be changed to 3, 1 no change, and 3 will become 2. I hope now you understand this is entangled state. Okay, so here it is a 1 by root 2. If you want, you can write that 0 0 become 0 0 plus 1 1, okay, and 1 become, that means 0 1 become 0 1 plus 1 0. If you want, you can write in the binary notation and check whether this is right or wrong. And the next one is a 2 3. You need not to do anything, I told you already. Whatever the earlier final answer you have, this is only for H, not for other other things, okay. Whenever head mod is there, do like this, otherwise proceed with the original method, that is 1 over root 2. Here 2 is on, that's why 0 minus 2. 3 is on, that's why 1 minus 3. Next, x. So here 0 no change, 2 will become 3, 1 no change, 3 will become 2. That's it. Okay. So let us take one more example. Okay. So here I'm taking a second example. Let us change the order. Here first I am taking a C naught and here it is a H. Two qubits are there, 1 and 2. I told you how to come from left to right. So that's why X first, starting from 2, coming to 1, that's why 2 comma 3. Strike a line, each operation strike a line. Then H, it is on 2, that's why 0 comma 2. Now add 1, H of 1 comma 3. Now here anything you can take, it's not a problem. I'm taking all the things together, no need to get tension. 0 1 2 3 I have taken. So here a 0 no change, let me take another color. X is operating now, 0 no change, 1 no change, 2 will become 3, 3 will become 2. Okay, next come to this. This is off, on. 0 is off, it creates a superposition of 0 and 2, that's why 0 plus 2. 1 is off, it creates a superposition 1 plus 3. 3 is on, that's why it creates 1 minus 3. 2 on, 0 minus 2. Okay, only two states are there, normalization constant 1 by root 2. Okay, right, and take one more. So here let me take like this, and I have taken a reverse one, C naught. No problem, anything you can solve by if you understand this technique. Left to right, first head mod is coming 0 comma 1 because it is on 1, and add the another one, that is a 2, 2 comma 3, and x, it is going from 1 because always starting control bit is 1, 1 comma going towards 2, 1 plus 2 3. That's it, right? So whenever head mod is there, it's better to take a 0 to first, otherwise you can take all the things at a time. Let us see, because you already understand. So head mod operation, off, on, 0, 0 plus 1, 1, 0 minus 1, 2, 2 plus 3, 3, 2 minus 3, and 1 over root 2. Next x operation, that is a 0 plus 3, 1 2 3, 3 2 1, 0 minus 3, 2 plus 1, 2 minus 1. Like this you can do very easily. Okay, so let us take one more. Now here third one I am taking, let us take like this. This is the head mod gate, and here we have control not, C naught. Now two qubits, 1 and 2. Okay, so you have to take from a left to right. First head mod is there. See, that is on 2, that's why 0 comma 2. Add 1, that is 1 comma 3. Next gate is going from left to right, don't forget this, that is x 2 comma 3. I hope you understand why it is, and strike a line, and h is repeated one more time, you have to write, that is h of 0 comma 2 and h of 1 comma 3. Okay, now let us see, 0 1 2, 0 1 2, 3, you have, right. So here I have taken all the states at a time. Okay, no problem. So please remember this technique. Oh, sorry. Off, off, on. This X is always flipping the states. That's not a problem. So here this is a 0 off. That's why 0 plus 2. Let me take another color. So 0 plus 2 and 1, it is off. That's why 1 plus 3, because 1 is in the combination of 1 and 3. 2 on, that is a 0 minus 2. 3 on, 1 minus 3. I hope you understand. I will write the normalization constant at the end. It's not a big deal. So this is x. So 2 will become 3, 3 will become 2. That's why 0 plus 3, 1 plus 2, 0 minus 3, 1 minus 2. Now see, again one more head mod operation came. Okay, so here 0 is in off state. So 0 become 0 plus 2. Let me take another color. So how I'm writing for this is 0, 0 plus 2 plus 3. That 3 is in on state, be careful, 1 minus 3, because it is a combination of 1 and 3. Next 1, it is off, 1 plus 3 plus 2, it is on, that's why 0 minus 2. Next 0, 0 plus 2. If you observe carefully, this one, 0, 3, only middle sign is changed. That's why here just change the middle sign. And second one and last one, only middle sign change. That's why 1 plus 3 minus 0 minus 2. That's it. So here 4 states are there, 1 over root 4. Actually 1 by root 2, 1 by root 2, that is 1 over root 4. Okay, so I hope you understand this. Right. So let us go to the next one. Next one is a little bit quite interesting. And here the next I am taking quantum circuit like this. This is the C naught, and here we have H and H gate, head mod gate. I hope you know this. This is equivalent to control jet, but let us apply our technique. Okay. So this is a 1 and a 2. So first I am taking a left to right operations, that is a H of, listen carefully, this is that's interesting, 0 comma 1, and you have to add 2, that's why 2 comma 3. Next control, I mean X, this is the C naught, 2 comma 3. And next head mod again, head mod 0 comma 1 and 2 comma 3. Now listen. Sir, if you are having these many operations like this, how we will do? I'll tell you a small technique. So commutation, interchange, or yeah, AB equal to BA operations like this. This is possible in our technique only when, observe carefully, here there is no 0 comma 1. So that's why this H of 0 comma 1 directly you can write here. That means you are interchanging that first one. Okay, and this H, you cannot multiply H01 with H23. H01 is multiplied with H01 only. Then it is H square 0 comma 1, which is identity 0 comma 1. So this one won't do anything with that 0 and 1 states. And the next one, H2, next one you can apply our technique. So we have 2, 3. That means yeah. So the remaining is a H of 2 comma 3 and X 2 comma 3 and H 2 comma 3. If you want, you can apply our technique, you will get the same answer. But you know, all of you, I mean most of you know this H, X, H is nothing but Z. Okay, so that's why I can write this as Z of 2 comma 3. Okay, so this will become, okay, this will become Z 2 comma 3. Carefully see 2 comma 3. What is the meaning of 2 comma 3? First one is always a control. So that's why this is 1 and a 2, you are here. And how you got this 3? That is a 2 plus 1. So C plus T. So T is a 1. That means the target is 1. Like this. Okay. That's it. That means if you take a 2, 3, this is a Z operation. That means a 2 is 2 off, 3 on, 2 minus 3. So finally we can conclude like this. So if you have uh, you have C naught here and a head mod gate and this head mod gate. This is equivalent to this control Z. Okay, right? And you know that if control Z, you can interchange control bit and target bit also you can interchange. Next, let us take a few examples. Um, yeah, so I'm taking this circuit. So here H, and this is a C naught, and here H like this. Let us check what you will get. Okay, just now we have seen this this gate. This is nothing but control Z. So now I'm going to replace this with the control Z, and here you have control Z gate, and the rest of the head mod operators, head mod gates are as usual. And earlier we have discussed whenever control Z is there, control and target bits can be interchanged. Then uh, you will get here Z, because here I interchange that control and target bits. Here also you can change this. It's not a trouble. It's not a big deal. But head mod gates are as usual. No change in the head mod gates. And just now we have discussed H Z H is nothing but X. So this is nothing but again we have H Z H, that is this one, which is nothing but X. So we got a C naught. That means control and target bits of C naught are interchanged. Okay, so we can say it upside down, something like that. Okay, so that's it. And take the another example. Let me take head mod here and on C naught, and again head mod I am taking and a C naught. No need to get tension. So just aram se apply our method. So here 1 and 2, don't forget this. So first left to right, add mod 0 comma 2, add 1, 1 comma 3. Next C naught, that is a 2 to 3. Next again head mod 0 comma 2, 1 comma 3. Next again x 2 comma 3. That's it. Now observe carefully. Now you got a doubt. So shall we multiply this h of 0 comma 2 like this? Earlier you have multiplied. Here h of 0 1, h of 0 1 you multiplied. Shall I multiply here? No. Because see, h of 0 2, h of 0 2, here you should not have either 0 or 2. But you have 2 3. So that's why we should not multiply. Then how to proceed? Then follow the usual method. So here I am taking 0 1. See, first elements I have taken. First head mod 0 plus 2. I hope already you got some perfection. That's why I'm doing fast. So 0 plus 3 and 1 plus 2 and again head mod. So 0 off, 0 plus 2, 1, sorry, 3 on, 3 on, that is 1 minus 3. 1, 1 off, that is 1 plus 3, and 2 on, that is a 0 minus. Next again x. Okay, so this will give 0 plus 3, plus 1 minus 2, 1 plus 2 plus 0 minus 3. Now the next one, no need to worry. Next one we can write directly, that is a 2, 3. I'm not doing all these things. Directly you can write. The reason is 2 is on. Here the combination is a 0, 2. 2 is on. That's why 0 minus 2 and 1 minus 3. So no need to do all these things. Directly you can write. In the middle you have minus. Wherever middle sign is there, just change it. 0 plus 3 minus 1 minus 2, 1 plus 2 minus 0 minus 3. That's it. Okay. Right. I hope you understand this. So I will give you a few examples. You please try, and if you are facing any trouble, please inform me. And here we have head mod, and this is a C naught, and this head mod. Second one here, X gate, and this control head mod. And third one, so here I have head mod gate and another control head mod gate. Okay, so whatever it is, no need to get tension, just go from left to right. And the last one more is left in this 2-qubit quantum gates, that is swap gate. The last one, swap gate. Okay, so swap gate, generally here we will write like this, and we will represent like this, A, B, and here you will get B, and here you will get A. So then how to represent this in our decimal notation? Okay, so here I'm taking this swap gate. So 2 qubits are there, that is a 1, 2. Then it's very simple. It's very simple. I'm using this SW, okay, because I cannot take a first letter S because already S gate is there. SW, that is 1 and 2 will interchange. That means 1 comma 2 only. Either you can write a 2 comma 1 or 1 comma 2. It's not a problem. Okay, right. And I will explain if more number of qubits are there, then how to do all these things in the next video we'll discuss. Okay, let me explain one interesting thing here. I'm taking a combination of C naught gates here, like this, C naught and a reverse C naught and a C naught. Let us find. Now here swap gate 1, 2 means what? 1 become 2 and 2 become 3, like this. Just like flipping, but you cannot say it's a flip. Okay, so 1 become 2, 2 become 1. Don't say flip, sorry. So here 1, 2, proceed, x of 2 comma 3 because the starting 2 ending 1. So that's it. And the next x is a 1 comma 3 because the starting 1 ending 2. Next x is a 2 comma 3. Okay, now I want to check 1 and 2 only. That's why I'm taking 1, 2. If you want to check another, you can check, you can take all the things, no problem. 0, 1, 2, 3 I'm taking. So 0, there is no 0 in all these things. That's why 0 is as usual. Next one is 1. See, always go from left to right. Any 1 here? No. Then go to the next. Any 1 here? S. 1 become 3. Then go to the next. Any 3 there? Because already 1 become 3. Now you are in the 3 state. So 3 become 2. Still not understanding? One more time. So here we have 1 initial state. So 1. You have to travel from left to right. There is no 1. Go to the second. 1 become 3. Don't write. So come to the end, till the end. Go till the end. Next 3 become 2. Right. Next one 2. So here it is 2. 2 become 3. 3 become 1. And here is no 1. That's why 1. One more time. Here it is 2. 2 become 3. 3 become 1. Here there is no 1. That's why I have written. Next one 3. 3 become 2. Here there is no 2, but don't stop till the end. Again 2 become 3. That's it. Now if you see carefully, this one, 1 to 2, 2 to 1, 0 and 3 remains the same. And still not understanding, take one more. So this time I am taking a reverse C naught, and here C naught, and again a reverse C naught. This is 1 2. So I'm taking here, this is x starting from 1 going to 2, that's why x of 1 comma 3, next x of 2 comma 3, next x of again 1 comma 3. Okay, right. Now here I'm taking this 0 1 2 3. I hope you understand, that's why I'm taking directly. So you please check, here is no 0, go next, no 0, no 0, that's why 0 is as usual, I mean same. Next 1, here 1 become 3, 3 become 2, here is no 2, write 2. If there is no state, just immediately write next to 2. Here is no 2, go to the next, 2 to 3, 3 to 1. Next, and here 3, first one 3 to 3 become 1, here is no 1, now 1 become 3. That's it. So same answer. Okay, so we can conclude like, we can conclude this, what means so if you have a swap gate, this is equivalent to C naught reverse a C naught, again a C naught, and this is equivalent to uh, like this. Okay, right. So fine, and till now we have discussed about this 2-qubit quantum gates. Okay, so I hope you understand this method and you are following. Okay, so in the next lectures we will discuss some more interesting points. Okay, so thank you, and if you are facing any trouble, so please let me know. And okay, so thank you, we'll meet again. Right. So till now we have discussed how to solve these quantum circuits involving a single qubit gate and a 2-qubit gates. Let us take a few more examples. Now here I am taking the first one, taking 3 qubit states, and a single qubit gates I am taking Hadamard, and here it is Toffoli X, and this is S. So how to solve this? Generally here the initial state they will give 0 0 like that, but with this method you can solve for any input. Okay, so give the decimal notation to the qubit states starting from LSB 1 2 4. Now write the operations top to bottom, left to right. The first one single qubit, that's why u of 0 comma target, so that is a 0 comma here target is a 4. Next you have to add the remaining states. Now first I am adding 1 to the above states, that is a 1 comma 5. Next you have to add this 2. Remember, whenever you are adding any state, you have to add to all the previous operations. That means h of 2 comma 6 and h of 3 comma 7. And after that we have x, this is x 0 and the target is 2. Next add 1, x of 1 comma 3. Next add 2 to the previous operations, that is sorry, not 2, 4, because x already taken 2 and 4 is remaining, 4 comma 6, and here it is a 5 comma 7. And the next one is s, it is on first one 0 comma 1. Now I am adding 2, that is s of 2 comma 3. Now I am adding a 4 to the previous operations, 4 comma 5, and 6 comma 7. Now I told you already, whenever head mod is there, better to take this first decimal values of that ordered pair. That's better. Okay. So okay, 0, 1, 2, 3 I have taken. Now first head mod operation, just go from left to right. Okay. So head mod operation. So the 0 is off, here off, second on. So a fixed one, I think I have already explained what is the meaning of that off and on, off, on, right. So this is a 0 plus 4, 1 plus 5, 2 plus 6, 3 plus 7. If you are watching this video directly, I request you first watch the first lecture and then come to this video. And next x, which will flip the states, 0 become 2, 4 become 6, 1 become 3, 5 to 7, 2 to 0, 6 to 4, 3 to 1, and 7 to 5. It's very easy. Next we have this s. I hope you remember what is this s operator. 100i. Okay, and the first column is off and second column is on for on state. So here 2 is there, 2 is in off state, that's why no change. 6 is also in off state, no change. So and here we have 3, 3 is in on, like in on state, that's why 3 I3, and 7 is also on, that's why I7, and 0 off, 4 is also off, but 1 is in on state, that's why this is I1, and 5 is also on, I5. So right, finally if you want to write this normalization constant, you can write 1 by root 2, and this is a 1 by root 2, you can write like this. This is a 2 plus 6, and I is a phase factor, and here's 0 plus 4, and I1 plus I5. I told you earlier, whenever head mod operations are there, it's very easy to write the rest of the states. Now the rest of the state means take the second elements in that order pair, it is 4, it is a 4, 5, 6, 7. Now if I take a head mod operation on this, now whatever earlier we have, that middle sign will be changed, that is a 0 minus 4, 1 minus 5, 2 minus 6, 3 minus 7. And I need not to do all these things, directly you can come to the answer. This is the one advantage if you start with the head mod first numbers of that ordered pair. So it's simply a 2 minus 6, and this is I3, the middle one is minus I7, and this is 0 minus 4, and this is I1 minus I5. That's it. Okay, right. And now let us take some other examples. This time let us take a combination. First I am taking 2-qubit states. Here I have head mod, and this one control S, and again head mod gate is there, and after that one swap gate. Let us do this. Okay, so no need to get tension, top to bottom and left to right. So first give the decimal notation, this is a 1 and a 2, and here we have head mod, it is on 2, that's why a 0 comma 2. Next we have to add the remaining, that is a 1 comma 3. Next here we have S, control S. You need not to write CS, you can write S. So you are coming from 2 to 1, that's why 2 comma 3. Next again header mode, it is on sorry, it is on first state, that's why 0 comma 1. Add the remaining, that is h of 2 comma 3. And next swap, just I'm taking the letter SW. Okay, this is a swapping between 1 and 2, decimal states 1 and 2, right? Okay, now I told you already, first take these two, 0 1. Once the head mod is operated, it is a 0 plus 2 and a 1 plus 3. And a normalization constant you can write at the end, or now also you can write. And this is off and on. S will add I as amplitude to the on state, and off state remains same because S is 100 I. First column stands for off state and second column is for on state. So I will write the normalization constant at the end. Now 0, there is no 0 actually, 2, no change, 1, no change, and 3, I3. Next again head mod operation we got, so no issue. I will write the normalization constant at the end. Now here 0 is there, this is off and on. So this is 0, 0 plus 1, 2, 2 plus 3 here. 1 on state, that's why 0 minus 1 plus I, it is a 3, that is a on 2 minus 3. And finally swap gate, it swap 1 and 2. So the final answer here it is 4 states are there, that's why 1 over root 4. 0, 2, 1 plus 3 and 0 minus 2 because 1 and 2 swap, and plus I 1 minus 3. So once you got this 0 1, you can write directly that other one 2 3. No need to do all these things because the initial operation is head mod. This is possible whenever initial operation is head mod, because here the initial operation is with head mod. The reason is if you write the starting one, so it becomes 0 minus 2 and 1 minus 3, and rest of the operations are same. That's why what I am saying is finally come to the last step without doing all these things. Just change the sign in the middle. Just change the sign in the middle. 0 plus 2 minus 1 plus 3, 0 minus 2 minus I 1 minus 3. That's it. Okay, right? So let us take one more example. Now here we have 2 qubit states. Give the decimal notation 1 and 2. Now write the operations. So here we have head mod, two head mod gates are there, but no issue. Start from top to bottom and left to right. So the first head mod is 0 comma anything you can take, 0 1 0 2, anything you can take, it's not a problem. So 0 2 I'm taking, and add the first one, that is 1 comma 3. Again you have to take a head mod. The reason is you are coming from top to bottom first, so that's why again h of 0 comma 1. Now this time I'm adding 2 comma 3. Next z is there, that is on 2, that's why 0 comma 2. Add 1 comma 3. And the next x, that is you are going from 1 to 2. Okay, so whenever 2 qubit gate is there, just see the starting number and ending number. So that is control to target. So control is 1, target is 2, that's why 1 plus 2 3. That's it. So off on like this. For x it is not required because it's just to flip the states, right? Now first I am taking 0 1. This is 0, let me take here 0 1. So the head mode operation will do 0 plus 2 1 plus 3. I hope you understand. I'm writing the normalization constant at the end, and after that again head mode operation is there. 0 becomes 0 plus 1. All of you please see this one, okay, and plus 2 is in off state with a linear combination of 2 and 3, 2 plus 3, and 1 it is in on state, that's why 0 minus 1 plus 3 on state 2 minus 3. So if you want you can write the normalization constant 1 over root 4. And now Z operation, uh, 0 and 1 are in off state and 2 and 3 on state, that's why 1 over root 4. So 0 off state, 1 off. And next, sorry, so 2 is in on and 3 is also on, that's why minus 2 minus 3. So that's why we can write it as minus common, that is 2 plus 3. Next one, 0 minus 1 as usual, no change in the 0 and 1. And after that 2 will be changed and 3 also a phase change will be there, minus 2 plus 3. So just I am taking minus common, then it become 2 plus 3. Sorry, 2 minus 3. This is 2 minus 3. Okay, right, because minus 2 plus 3 minus common 2 minus 3. That's it. And after that we have one more operation, that is x. So it flip 1 and 3 only, 1 2 3 3 2 1. So 0 plus 3 minus 2 plus 1 and 0 minus 3 minus 2 minus 1. That's it. And normalization constant 1 by root 4. So the advantage of this method is you need not to do the operation of the next one, that is a 2 3. You can write it directly, come to the last step, whatever the sign in the middle, just change it. So if you have any confusion, please do this entire process and check whether you are getting the same answer or not. Okay. Right. So thanks for watching, and I request you please watch the lectures in order, first lecture and next second one, and like that. Okay. So thank you. And if you have any trouble and if you are facing any problem while solving the circuits, so please let me know, and definitely I will help you. Thank you. Welcome to UV physics. So here we are discussing a new approach to solve any quantum circuit. That means we can find the output state by using this decimal notation method. So in the first lecture I have already explained the method. So once again let me explain briefly about this decimal notation method. For example, if I have a single qubit, let us say q naught, then I am taking this as a 1. That means whenever that a qubit is on, that value is 1. I have taken like that. And if I have 2 qubits or 3 qubits or 4 qubits, any number of qubits you can take, then it is 1 2 1 2 4 1 2 4 8. The decimal values. If you want you can write it as a ket notation also, it's not a problem, right? Okay, so next thing, for example, you have single qubit gate. Just I am explaining briefly. So if you want more clearly, I request you please watch the first lecture. So single qubit is there. Let us suppose you have single qubit state and gate is also single qubit gate is there. Let us say U. So for this what I have explained, the operations. The operation here it is U of, so there is no control, only target. Whatever you have, that is the target. Okay, 0 comma t. That's it. That u may be x, s, t, any single qubit you can take. Okay, so for example, in this case we have only one. Okay, so that's why the operation is given by u of 0 comma 1. Now for example, you have two qubits, that is 1 and 2, but you have a single gate here itself. Then how to proceed, how to get this operations? The operations here I have already explained everything. Operations, this is u of, first u is on this second state, that's why you have to take a 0 comma 2. After that you have to add whatever the remaining. It's a simple decimal addition only, no binary addition. It's very easy. So 1 comma 3, that's it. That means it will operate, I mean it will make the changes or superposition or flip only these states only, 0 and 2 combination and 1 and 3 combination. 0 and 3 combination you won't get in this case. Okay, 1 and 2 combination also you won't get, that's the point. Okay, and one more example I will take. So for example, if you have 1 and 2, and here we have Hadamard gate, I'm just taking an example to understand, and here I have S gate. So whenever you are having like this, you can come from top to bottom. Single qubit gates, you can go from top to bottom or bottom to top, it's not a problem. But whenever you are making the tensor product, you have to always come from top to bottom. But remember, operations we are doing, not matrix multiplications. So that's why operations are from left to right, because the left side operator will operate on the initial state. We are trying to find the final state. Okay, so here the operations, you can take h first, no issue. H of 0 comma 2, and you have to add this one, that is a h of I will write like this to understand more clearly. So this is a h of 1 comma 3, and next you can take s, this is on 1, that's why 0 comma 1, and here we have to add the remaining 2, that is s of 2 comma 3, like this. If you have 3 qubits, then also I already explained this method. I request you please go through this. Definitely you will enjoy while you are solving this quantum circuits. It's very easy. I feel it's very easy. That's why I want to share with you. So please go through that method. And a 2 qubit gates also I explained. Let me give that example also. 2 qubit gates. So for example, here we have 2 qubits and I am taking control U. Okay, so this is unitary U and this one control U. This is a C and this is target. Okay, now you know if C is 1, then only this operator U will operate on T, otherwise no change. Output is a CT as usual, tensor product of C and T. But whenever C is 1, then only C and U operates on T. This is what we have discussed, I mean generally. So initial state C, T become C, UT, only when this is C equal to 1, if C equal to 1. If C equal to 0, there is no change at all. Okay, everybody know this. But in our method, how we are doing this, so no need to write C, just take operations. So this is our method, a decimal notation method, operations, how to write. Once again, I am taking this 2 qubits, 1 and 2. It's easy, please follow 1 and 2. And let us suppose this is C and this is T. And here I am defining the operation as U of, earlier control is not there, that's why we have written 0 comma T. Now control bit is there, that's why you are coming from which bit? Control. So this is the starting, that a dot is the starting, C comma, you are coming towards T, just I am assuming like this. Okay, C plus T, easy. In this example, U of, you are coming from 2, 2 comma 2 plus 1 3. That means what is that U of 2 comma 3? That unitary operator will affect only those two states 2 and 3. It won't affect the other states 0 and 1. I hope you understand. For example, if you take instead of you have taken a Hadamard gate, it will create a superposition of 2 and 3 only. It won't create any superposition of 0 and 1. If you take u as x, it will flip 2 and 3, 2 2 3, 3 2 1. 0 and 1 states remains the same. This is what I'm saying. Okay, so I have already explained all these examples. Maybe you will get one doubt. So for example, I have 3 qubits. Okay, so here only I have this control u operation. Then how to do this? Yeah, very simple. 3 qubits, notation 1 2 4. Then how to write the operations? Let us see. Okay, so initially where is this CU gate? Here we have. Okay, here we have. So please go there. So this is u of starting 2 ending 1, that's why 2 plus 1 3. For this you have to add the remaining one 4, that is u of 6 comma 7. Okay, now last one more example I will explain. And if you have 4 qubit states, but somewhere here I have this control u operation, then how to do this? Generally it is a tensor product of I, tensor cu, tensor I. So here we have 1 2 4 8. Okay, so you need not to bother about that 1 and 8. Okay, you just operate this only, and after that simple addition only, but decimal addition only. Okay, so this is quite interesting. U of 4 comma 6, because of 4 plus 2 6. After that add the next state. You can add either 8 remaining or 1, but I am taking the least one first, plus 1. Then it is u of 5 comma 7, and this is important. Whatever the remaining state, decimal state we have, you have to add that 8 to the earlier all states. We have to add to that earlier all earlier states. That means after adding after adding 8, this become u of 12 comma 14, and this is u of 13 comma 15. Oh, that's it. So these 4 operations only will happen if this is a single. If a combination of gates are there, that also I have explained in the earlier classes, the first lecture and second lecture, so kindly watch. And today in this third lecture we are going to discuss about equivalent circuits. So let us start this third part, that is equivalent circuits. So here that means here we are going to discuss about 2 quantum circuits which are equivalent, that means which will give you the same output. Let us discuss. So here we have 2 qubits, okay, and this is Pauli Z gate, single qubit, and here we have a C naught, and here I am taking the another one, so 2 qubits and C naught gate here, but this time that is here and here also. Let us see whether these are equivalent or not. Okay, so proceed with our method. So decimal notation 1 and 2, here also 1 and 2, and you have to write the operations. So left to right, don't forget left to right. First I have z here, z of 0 comma 1, then I have to add 2, it's clear. Next x 2 to 3, that means 2 to 2 plus 1, you are coming from 2 to 1, that's why 2 comma 2 plus 1 3, that's it. And here also I am taking x 2 comma 3, and after that any z you can take, either upper one or bottom one, anything you can take. So z of 0 comma 2, I'm adding 1, and after that second z I'm taking z of 0 comma 1, adding 2. Now see, I'm taking all the states at a time. That means initial state. This is the initial state. Okay, so here first z is operating on that, and you know already this first one is off, second one is on. Okay, I hope that also you know, right? So where is the 0? 0 is in off. Whenever you take a Z matrix 1 0 0 minus 1, this also I have explained already. I request you please go through that. Just divide into two columns, and this is the off, this is on. First column you have to take for off, and the second column you have to take for on. So that's why 0 is in the off state, that's why again 0 only. 1 is in on, that's why minus 1. 2 off, same. 3 on, minus 3, phase change. And after that again one more x is there, this one. Only it flip 2 to 3, 0 as it is, minus 1 as it is, it become 3 and it become minus 2. So this is your final state. Now let me check whether you are getting the same answer for this or not. So here again I am taking a 0, 1, 2, 3 initial state. Now first here we have x operation. So that is it flip only 2 and 3. So 3, 2. And after that z operation. Okay. So 0 off, 1 off, 3 on, that is minus 3, sorry, minus 3, and 2 is also on, minus 2. Next again z, 0 off, 1 on, and minus 3 on, that's why one more minus, that is 3. 2 is off, that's why same. Now if you observe carefully, here we have this final state, and these two final states are same. So that's why we can conclude that these two quantum circuits are equivalent. Let us go to the next one. So here I have taken two qubits. Okay, so first one here we have C naught, and after that Z, and here first Z operation and after that C naught operation, just like a commutation relation. Okay, let us see. So order, because order is reversed, no? That's what. So here we have 1 and 2. So first operations x of 2 comma 3. I hope everybody understand why it is x of 2 comma 3, 2 comma 3. And after that z of 0 comma 2, and you have to add the remaining, that is a 1 comma 3. And here same 1 comma 2, that means sorry 1 and 2, z of 0 comma 2, add 1, that's it, and x 2 comma 3. Now let us take 0 1 2 3. This is the initial state. First x operation 0 1 3 2. Next z operation, these two are off, these two are on, that's why the 0 1 as it is, minus 3 minus 2. Now let me check this second one. So 0 1 2 3, this is the initial state, and here z operation, so off, 1 is off, 2 is on, 3 is on, minus 2 minus 3, and x, I'm using that on and off notations only. Okay, so next one 0 1, it flip 2 and 3, minus 3 minus 2. Now this is the final state, and this is the final state, and both are same. So that's why we can conclude that these two quantum circuits are equivalent. Actually, this is not only for Z, this is valid for any diagonal matrix. That means what I am saying is, a small note, this is true for here we have two qubits. What I am saying is this is the C naught, and here U, this is equivalent to, this is U, and here C naught. But remember, this U is a diagonal. Examples that U may be Z, S, T, that's it. Okay. So identity no need to check, because if you take identity, both are same circuits only. So this is valid for any diagonal operator or any diagonal matrix. For example, here we have Z, S, and T. Okay, we'll go to the next one. So here we have two gates are given. Let us check. Sorry, two circuits are given. Let us check whether they are equivalent or not. And if you take this rz of theta, that is a rotation operator about z axis, which is e raised to minus I theta by 2 0 0 e raised to I theta by 2. Wait a minute. Just now we have discussed, this is a, no doubt this is a diagonal operator, diagonal matrix. If the operator is a diagonal, okay, I mean diagonal matrix, then these both are equivalent only. Just now we have discussed. Okay, no need to check. Or if you want to check, you can proceed with this method. Let me explain that method also. So here we have 1 and 2, 1 and 2. First we have x, 2 comma 3. Next we have rz, 0 comma 2, and we have to add 1, 1 comma 3. Next here also, let me write initially rz of 0 comma 2, sorry, and this is x of 2 comma 3. Now here 0 1 2 3 I have taken this initial state, and x 0 1 3 2 and rz. So here 0 and 1 are in off, 2 and 3 are in on. Okay, so I told you already, since it is a diagonal, only a phase factor will come to that state won't be changed, and you won't get any superposition state also. If all elements are not equal to 0, then you will get the superposition state. If a diagonal matrix is there, only just a phase change, and uh, diagonal elements are 0 and off diagonal elements are non-zero, then you will get a flip, that is x and y. So I hope I already explained in the earlier lectures. Please go through that. Yeah, phase difference is a 0, e raised to minus I theta by 2, 0. I'm writing ket 0. 1, same, e raised to minus I theta by 2, 1. 3, e raised to I theta by 2, 3. And this is e raised to I theta by 2, 2. Okay, that's it. So let us check the answer for the second one. So initial state I am taking 0 1 2 3. So this is the initial state, and here we have rz. So 0 off, 2 on, 1 off, 3 on. So 0, e raised to minus, because the first column is for off, second column is for on. E raised to minus I theta by 2, 0, and e raised to minus I theta by 2, 1, and e raised to here theta by 2, 2, and e raised to I theta by 2, 3. Next after that x. So x will flip only 2 and 3, the first two terms as it is, and here e raised to I theta by 2, 2 is a flip to 3, and 3 to 2, that's it. And if you see these two final states are same, so that's why we can say that these two are equivalent. Okay, let us go to the next one. Now here I am taking a fourth one, in terms of head mod operations. So here H gate, and here also H gate, and this is the C naught, and another circuit. I'm reversing this C naught, and after that this head mod gates also like this. Okay, this is also just like a commutation. That means a b, of course here it is a tensor product of h and h. Okay, and okay, let us see 1 and 2. Let us apply our method. Okay, so first h I am taking operations 0 comma 2, and we have to add 1 1 comma 3, and the next h, second h is also there, h of 0 comma 1, h of 2 comma 3, and x of 2 comma 3. So close here and come to this 1 comma 2, 1 and 2. You can write initially like this, operations 1 comma 3, because it is 1 to 2, 1 comma 3. You can take any h, h01 and h23. After adding 2, h02, and I have to add 1 1 comma 3, right? See, I'm not doing any binary addition or something, just very easy, just a decimal notation and decimal addition only. So I hope you are following. If you are facing any trouble, please let me know. And here I told earlier, if I take this elements of that first elements of that bracket, it is very easy to write the next state. This is what I said, but here it is not like that. It's okay. Now I'm taking 0 1 2 3, all the things at a time I'm taking. Let us try. So here 0 is there, which is a linear combination of 0 and 2. That's why 0 plus 2. I'm not writing in normalization constant. Finally I will write, because 2 head mods are there. Maybe you will get 1 by root 4. Let us see. And 1 off state only, 1 plus 3, 2 on state, 0 minus 2, 3 on state, sorry, 1 minus 3, and again one more h. So 0 off, 0 plus 1, 2 off, 2 plus 3. I hope you understand. This 2 is a linear combination of 2 and 3. This 0 is a linear combination of 0 and 1. 1 on state, that's why 0 minus 1, 3 on, 2 minus 3, 0 off. Just observe carefully. Here 0 plus 2, here 0 minus 2, right in the middle, minus 2 that above 1. And here 1 plus 3 and here 1 minus 3. I hope you are observing what I am saying. Okay, here 1 plus 3, 1 minus 3. 1 plus 3 already you have written. So write 0 minus 1 in the middle, minus 2 minus 3 like this. And after that we have x. Still we are doing the first circuit only, 2 to 3. So that's why finally I can write 0 plus 1 plus 3 plus 2, 0 minus 1 plus 3 minus 2, 0 plus 1 minus 3 plus 2, 0 minus 1 minus 3 minus 2, and a normalization constant 4 terms are there, 1 over under root 4. Okay, next let us say this is the A and this is a B. So this is A output. Now I am coming to B. 1 2 3 4. So first initially x we have 1 2 3, here 3 2 1 4. The remaining are as it is. Next we have head mod operation. So 0 off, 1 on, 2 off, 3 on, 3. That is a 2 minus 3, 2, 2 plus 3, 1 on, 0 minus 1, and 4. Oh, 1 minute. 1 minute. What is this? I'm sorry. I'm sorry. 0, 1, 2, 3. I'm sorry. So x, that is a 0, 3, 2, 1. So now initially we have 0. Okay, so 0 off, 0 plus 1, 3 on, 2 minus 3, 2 off, 2 plus 3, 1 on, 0 minus 1. Okay, right. And after that one more head mod is there. So here 0 off, so 0 plus 2. Next 1 off, that's why 1 plus 3. Next 2 on, 0 minus 2, minus 3 on, 1 minus 3, I hope you understand. 2 of here, see here, sorry, 2 on, see here, that is 0 minus 2. Just see that above and change the middle sign, plus 1 minus 3. Already you have written 0 plus 1, and here it is 0 minus 1. Take that above 1 and change the minus. Okay, so I think something, no, absolutely right only that order of numbers change. Okay, so because here I have taken h of 0 to first, here I have taken h of 0 1, that's why order of numbers change, but same state only, if carefully observe. So for example, if you check the last one, so this one check, so both are same. So 0 plus 2 and minus 1 and minus 3. Okay, so this is the advantage of this method. Okay, it's very easy, and the normalization constant 1 over root 4. So these two are same. So these two circuits are equivalent, right? So now let us take a combination of CNOT gates, and here first one I am taking 3 qubits I have taken, and first CNOT and the second CNOT. Here I am taking again 3 qubits. This time this is CNOT, and here another C. Okay, let us check whether they are equivalent or not. 1 2 4, 1 2 4. So this is the first C naught, x of 4 comma 5, and 2 remaining, that's why 6 comma 7. Just add, very easy. X of 4 comma 6, because it is coming to 4 to 2, 4 to 2, and this is x of next remaining is 1 5 comma 7. And let me write for this also immediately. X of 4 comma 6, add 1 5 comma 7, x of 4 comma 5, add 2 6 comma 7. So it will change only 4 5 6 7 only, there is no 0 and 1 2 3. Okay, so that means 0 1 2 3, no change, because no operation is involving with that 0 1 2 3, that's why no change. So we have to check only this 4 5 6 7. This is very easy. Okay, now start with the 4, always go from left to right. The starting is 4, 4 become 5. Don't write, just continue, because this is all are same gates only, same operations only, no need to write. Earlier why we have written step by step, so once you are getting x, next you are getting h, that's why I have written. Now continue the operation. 4 to 5, 5 to 7. I hope you understand. One more time. 4 to 5, 5 to 7, that's why I have written 7. Next one, 5, 5 to 4, 4 to 6, 6, 6 to 7, 7 to 5. You please try, 7, 7 to 6, 6 to 4. That's it. This is a final state. Okay, this is initial and this is final. Let us check the second circuit. Again I am taking 4 5 6 7. Now you please try 4 to 6, 6 to 7, that's why it's a 7. Next 5, 5 to 7, 7 to 6, 6. Next to 6, 6 to 4, 4 to 5, 7, 7 to 5, 5 to 4, 4. The same. Okay, so that means here we have commutation relation. So these two are equivalent. So next here we have 3 qubits, but a CNOT gate, that is uh, here from 1 to 4, 4 to 1. So this is equivalent to what? So this is also quite interesting, and here we can draw an equivalent circuit like this. So take only one step. One step means 4 to 2. Take only one step, 4 to 2, and again 2 to 1. Just to break it. Okay, you came from 4 to 1. Just take it as a step. 4 to 2, 2 to 1. Repeat that again one more time. Repeat. That means 422, 221. And you can take a reverse one. Reverse one means just like a mirror image. Mirror image means you can take a, sorry, not mirror image, reverse order. Reverse order means right to left. So that means here first one, this one, observe carefully, this one, I am writing this is right to left. Next above, okay, I hope you are seeing, this is the third one which is below, and again the next one like this. Okay, so once you got this, you can reverse the order, not a mirror. Yeah, you think you can take it as a mirror image also. I think, for example, if I keep one mirror here, let us say this is a mirror. Now this way, this gate came here. Yes, absolutely. This one, and here this one, and next this, and next this. Yeah, correct only. So, but let us check by using our method whether this is right or wrong. Okay, so now I am taking the first one, that is x 4 comma 5 adding to 6 comma 7. Next here combination is there, x 1 2 4 1 2 4, x 4 comma 6 add 1 5 comma 7. So many are there, that's why I am taking a little bit this side, x 4 comma 6, x 5 comma 7, next x 2 comma 3, add 4, this is 6 comma 7, next again x 4 comma 6 and x 5 comma 7 and x 2 comma 3 and x 6 comma 7, same repeated. Okay, so let me write this also. So here third one I am writing, this is x of 2 comma 3, first one always left to right, 2 comma 3, 6 comma 7, so after adding this, take the next x gate, that is 4 comma 6 and 5 comma 7, and repeat again the same thing, 2 comma 3, let me write properly, and repeat the next one, right. Okay, so here we have only 4 5 6 7 combination only, it won't change any 0 1 2 3. Now you got a doubt here, that means first let me finish this first one, a b and c, we have to show that all a b c are equal. So here 0 1 2 3 no change, so 0 1 2 3, and next 4 5 6 7 and 4 to 5, 5 to 4, 6 to 7, 7 to 6. Next I am coming to this, now observe carefully. So here 2 3 2 3, here in the middle we don't have 2 comma 3, that's why you can bring this side, and x x, that is identity, so there is no change in 2 3, that's good. Next, that's why here 0 1 2 3 remains the same. I hope you understand this method. Next 4 5 6 7, now 4 to 6, just proceed from left to right, 4 to 6, we'll use this, 4 to 6, 6 to 7, 7 to 5, that's it, 5. Next 5, 5 to 7, 7 to 6, 6 to 4, that's it, 4. Next 6, 6 to 4, 4 to 6, 6 to 7. Till the end, please proceed. 7. 7 to 5, 5 to 7, 7 to 6. Same. Still not understanding? See the third one. So here also same. Here there is no 2 comma 3. So that's why I can bring together and I multiply x square 2 comma 3, that is identity 2 comma 3. So 0 1 2 3, 0 1 2 3, no change. Now I'm checking this of 4 5 6 7, right? So 4, start from left to right. Here there is no 4, then go to the next one. 4 to 6, 6 to 7, 7 to 5. Next 5. Here there is no 5, then go to the next. 5 to 7 and 7 to 6, 5 to 7, 7 to 6 and 6 to 4. Okay, so 4. Next 6, 6 to 7. See the second one, 7 to 5. Next there is no 5 in the third, go to 4, 5 to 7, 7. Next 7, 7 to 6. Second one, 6 to 4. Next there is no 4. Last one, 4 to 6. That's it. So all are same only. So that's why all these quantum circuits are equivalent. Okay. So one more time, whenever you are having this CNOT gate after jumping one qubit state, that means 4 to 1. Actually 4 to 1 came. In the middle there is a 2. So what I'm saying is one step, take only one step, and from there again take one more CNOT connection. So from 4 to 2, 2 to 1, and repeat the process 4 to 2, 2 to 1. You can take the same thing reverse also. Reverse means yeah, like this. You please check this one. So what I am saying is just take a 2 stages, 2 steps. Here 1 2 4, directly it is going from 1 to 4. So what I am saying is first go from, just go like this, 1 to 2 and again 2 to 4. Next repeat the same process, 1 to 2, 2 to 4. You can take the mirror image. If you place a mirror, okay, so here top, next bottom, next top one, next bottom. So I request you, please try this and check whether all these things are equal or not. Okay, and I think this, like this also we can proceed. Maybe for example, if you have 4 qubits and from top to bottom we have like this 1 2 4 8, that means you have 8 to 1. Okay, so this one you please check, do it yourself, and if you are facing any trouble, please inform. Now here if you have 4 qubits, that is 8 to 1, so you have to take only one step at a time. I think this, I didn't check, you please check. So 8 to 4, 1 2 4 8, 8 to 4 and 4 to 1, and again 8 to 4, 4 to 1, and take the mirror image. So here this one first, next top, next bottom, next top, like this. Okay, so I didn't verify this. I hope this may be correct again. And again, if you want, you can divide this also. Like this we can divide in the, but you have to repeat that step, whatever splitting you have taken, that is directly 8 to 1, but you break it 8 to 4 and after that 4 to 1. So you have to repeat that process one more time. Okay, so I hope this is what I observed. I hope you understand. Okay, so this is quite interesting one. So here we have C naught gates and Ry of theta and Ry of minus theta. First let me write what is Ry of theta. So this is cos theta by 2 minus a sine theta by 2 and sine theta by 2 cos theta by 2. And next if I take ry of minus theta, so cos theta by 2 only, and this becomes sine theta by 2, and here minus a sine theta by 2 and cos theta by 2. So that means what happened? The diagonal elements interchanged. This first diagonal and second diagonal are interchanged. Yes. Okay. Right. Okay. Now let me apply our technique. So first one x 2 comma 3 over, and this ry, just I am taking a minus there. Okay, theta I am not writing. So this is 0 comma 1 and add, that is 2 comma 3, and next again c naught 2 comma 3, next again ry, this is a plus only. Okay, so I am not writing anything, otherwise you can write plus. So this is a 0 comma 1 and ry plus 2 comma 3. Now carefully observe. Now here see, here we have 0 comma 1 and 0 comma 1. In the middle here we don't have any 0 comma 1 combination. That's why you can that means whenever if you observe this one, top one, so you can bring this ry plus this side, because there is no 0 comma 1. So that's why these two directly multiply and this become I of 0 comma 1. Oh, 0 comma 1 is not changing. So only here the change is between 2 comma 3 only. Okay, so this one is quite interesting. Here finally we have x 2 comma 3, x 2 comma 3, ry minus 2 comma 3 and x 2 comma 3. Carefully observe, and one more is there, ry plus 2 comma 3. Now this one, we have x, an operator, and x. So here I will tell you a small thing. For example, you have Pauli X matrix here, and this is A, B, C, D, any matrix, and again x here. And earlier, I think earlier lecture series, I have explained these techniques also. So this x will operate on this, that means rows will interchange, because a Pauli X matrix, if you interchange the rows, you will get identity. If you interchange the columns, you will get the identity. So that's why it will flip rows and columns. That means whenever it is multiplying any matrix, this is a small technique. And this is this side, that's why you can take column. Right side rows, and this side you just take it as a column. Okay, so now you have to interchange both the rows as well as both the columns. Then what will happen? Here D will come, here A will come, here B, and here C. Please check. So finally what I want to say is, whenever you have X and a matrix A, B, C, D and X, this is nothing but just interchange AD and BC. That means D, B, C and A. This is a small observation. So then here I'm x ry minus x. Now go to ry minus. Okay, earlier I said one point. Please observe carefully that ry theta and ry minus theta. If you interchange that diagonal elements, first diagonal elements interchange and second diagonal elements interchange, then you will get the other one. So here ry minus theta, just interchange. Cos theta will come here, cos theta will come here, no same, but minus sin theta will come here and sin theta will come here. So this will become cos theta by 2. Just I am writing again here minus a sin theta by 2 and here sin theta by 2, and this is a cos theta by 2. Of course this is nothing but ry of theta. So this is nothing but ry of 2 comma 3. So finally we can write this entire thing is equal to ry. Now I'm not writing plus, it's okay, 2 comma 3, and again ry of 2 comma 3, that means ry square 2 comma 3. Okay, 2 times. So if you observe carefully, this entire circuit is equivalent to only 2 3. Only operation is 2 and 3. 0 1 remains same only. That means I can construct one control U operation which is like this, ry square. See, uh, if you want to construct quantum circuit from this operation, this first one is a C and second one is a C plus D. So here we have 1 and 2. It's very clear, control bit is a 2 and it is coming to 1, that's why ry square theta. That's it. Okay, so like this we can check by using this technique, and I hope you understand this also. So here what I have observed some interesting thing about this rx theta, that means rotational operator about x-axis. So if you take this rx of theta, this is cos theta by 2 minus I sin theta by 2 and minus I sin theta by 2 cos theta by 2. Just observe carefully. Just now I have explained that a diagonal elements, if you interchange that first diagonal elements, no change, and if you interchange that second diagonal elements, uh, no change. Okay, so that means x rx is x rx x equal to rx only. The reason is uh, that is Pauli X matrix, and here this is the rotation about x-axis. That's why this behavior came. What I'm saying is, if you take x, rx, and x, then what it will do? This will interchange the rows, and this will interchange the columns. Again, you are getting rx. So this we can see like this also, x, rx. I am multiplying on x inverse on both sides, that is a rx. Yeah, x inverse, no issue. Now this x inverse become I, so I can take this as a x rx identity, and rx x inverse. X inverse is nothing but x only, because x into x square equal to identity, so that's why this is also x. Oh, I think this is a commutation relation exist. So that's why we are having this equivalent quantum circuit, here C naught and here Rx of theta, and so this is a commutation x Rx, here Rx of theta and C naught, like this. So just observe x Rx and Rx x. Then how to check? By using our technique. This is 1 2 1 2. Okay, so this is first one left to right, x of 2 comma 3, and after that rx of 0 comma 1 and rx of 2 comma 3. Next rx of 0 comma 1 and rx of 2 comma 3 and x 2 comma 3. So just now I have discussed already, this is rx of 0 1, this is also rx of 0 1, so no issue. And this is x rx and this is rx x. So x rx of 2 comma 3 is equivalent to commutation relation rx into x of 2 comma 3. So both are same, just now we have derived here. So that's why we can say both these two circuits are equivalent. So not only this, and the second one, that means if you take up reverse, so the reverse C naught I have taken here, and this time Rx is here, because x Rx combination is equivalent to, so here it is Rx of theta and after that reverse C naught like this. If you want, you can check this one also. Okay, right? So finally this is because of the property x into Rx is commutes, that means equal to Rx into x. It's not surprising. This is Rx means rotation about x axis. Now Ry equal to Ryy. Yes. Zrz equal to Rzz, obviously. Okay, right. The next one, let me take another interesting one. So here I'm taking one circuit. This is C naught and Rx of theta and reverse C naught. So taking one more. Oh, okay. So there, let us check. It's easy only. Just now we have discussed. Now if you carefully observe here, Rx, X. So you can interchange X, Rx. So the remaining is as it is. This is the C naught, no change. This is the C naught. Okay. So only we have applied this commutation. This one. Okay, here, and this gate is as usual change. Sorry, as usual same. So if you want to check, you can check by using our technique. Okay. So let us say 1 2. Let us say 1 2. So this is x 2 comma 3, Rx 0 comma 2, Rx 1 comma 3, and x 1 comma 3. This one x 2 comma 3, and again x 1 comma 3, and again Rx 0 comma 2 and Rx 1 comma 3, like this. So you know what is Rx operator. So Rx of theta already I have written here. So just to go through this and apply. So first column off, second column on. Okay, I hope you know that. And in this bracket, first one is off, second one is on. Okay, right. And the next one, this is also quite interesting. So for example, here I have a C naught gate and another C naught gate. So simply here I am writing Rx, theta I am not writing. Okay, and what I am doing is just reverse that two C naughts. Then that Rx will come to the first, that means here. If you fill the two C naught gates, that Rx is coming down. So let us check whether these are equivalent or not by using our technique. This is 1 2 1 2. So this is x 2 3 and Rx 0 2, Rx 1 3 and x 2 3, and this is x 1 comma 3 and Rx 0 comma 1 and Rx 2 comma 3, and here it is x 1 comma 3. Okay, now see, if you observe carefully, here we have right, see this one 2 2 3 this side and 2 2 3 x gate x x, but 2 comma 3 operations. So I told you already. So this side rows will interchange and this side columns will interchange. So finally, wherever you have 2 in the row, that means matrix element 2 2 2 3, like that. 2 2 2 3 will become 3 3 3 2 rows. And column elements, if you have 2 2 and 2 3 and 3 3, like that, 3 2. So 2 and 3 will interchange. So that's why what I am saying, a small technique. So here 2 become 3, 3 become 2. If you want, you can check. This finally become Rx of 0 comma 3 and Rx of 1 comma 2. So this final operation is this one. That means it change only 0 3 combination and 1 and 2 combination. Okay, And similarly check here. So here we have 1 3 and this is also 1 3. So carefully observe, 1 is replaced with 3 and 3 is replaced with 2, because right side you have same operation and left side also you have same operation. So right side rows will interchange, left side columns will interchange. So final operation is rx 0 comma 0 comma 3 and rx, oh sorry, this is 3 1, I'm sorry. So 1 become 3 and 3 become 1. So that is rx 2 comma 1. Now you got a doubt. So are they same? Yes. This rx 1 comma 2 and rx 2 comma 1 same. The reason is if you interchange that elements you will get the same thing. If you want you can check. So both are same only. Right. Okay. Now let us go to the next one. So the next they have given this circuit to show that both these two are equivalent. It's very simple. Here we have Rx gate and please carefully observe this. And this is nothing but you just take a reverse C naught and that Rx will come here. Already we have seen the same thing. The rest of the part is not changing anything. Okay, like that. And the next one, this is a very interesting one, last one. And for example, you have this 2 qubits and this is a C naught, and here we have Rx and this is Rz, and here we have a C naught again. They are asking to show that uh, reverse C naught, and Rz and Rx will reverse. That means here Rz will come and here Rx will come. First let us check whether this, how these two circuits are equivalent. Now this is 1 2 and this is a 1 2. So here we have x 2 comma 3. So take the operations rx 0 comma 2 and add 1 comma 3 and again one more rz is there, careful. So this is rz 0 comma 1 and add 2 comma 3 and x 2 comma 3. And after that this is x 1 comma 3, next rx 0 comma 1 and rx 2 comma 3, next rz, anything you can take, it's not a problem, rz 0 comma 2 and rz 1 comma 3 and the next x 1 comma 3. Right. So now we have to check whether, so I'm leaving this as an exercise to you. So what you have to do is you know what is rx and what is rz. First let me write this rx. This is cos theta by 2 minus sin theta by 2 and minus sin theta by 2 cos theta by 2. So if it is off state, take the first column. If it is on, take the second column. Similarly, rz also, I hope you remember. This is e raised to minus I theta by 2, 0, 0, e raised to I theta by 2. So off and on. So you please proceed just like this. I will do one step for you, 0, 1, 2, 3, and here x gate 0, 1, 3, 2, and after that rx. So this 0 is off state, that's why cos theta by 2 0 minus I sin theta by 2 2, and the next 1 off state cos theta by 2 1 combination minus I sin theta by 2 3. Next 3 is in on, so that's why 3 is on. That's why we have to take the second column, minus I sin theta by 2 1 plus cos theta by 2 3, sorry. Next 2 on, that means the second column, minus I sin theta by 2 0 plus cos theta by 2 2. And after that rz, first one I am doing, second one I request you please do. If you are not getting, please contact. rz off and on, only phase change. Okay, so 0 phase change will be added, that is cos theta by 2 e raised to minus I theta by 2 0, like this. Okay, minus I sin theta by 2, and 2 is off, this by e raised to minus I theta by 2. You can write this side also, it's not a problem. So like this, please proceed yourself, and if you are not getting the answer, please contact. So these two are also equal, and by using this we can solve one a typical circuit like this. We have the C naught and Rx, and again C naught, Rx, and this is Rz, the C naught. Okay, so they are asking to show that another circuit which is like this: C naught, Rx, reverse C naught, and Rz, and here Rx, and this is C naught. Okay, so one second, I think this is yeah, oh sorry. So they are asking to show that this one, sorry, C naught and reverse C naught, Rx, and here Rz, and here Rx, and finally reverse C, like this. Okay, fine. Now just now we have discussed one technique. Observe carefully. So this is nothing but reverse C naught and reverse C naught, that Rx and Rz also reverse, Rz and Rx. So by using this, this circuit is modified. Okay, so first C naught as usual, next Rx is as usual. Now I am applying this, then it will become reverse C naught, sorry, here Rz, and here Rx, and reverse C naught. And after that, earlier we have already seen this commutation relation. Observe carefully this one. So this can be written as Rx C naught, C naught Rx. Already we have verified this. Okay, so finally this become C naught, and I am applying this one. So this is a reverse C naught, and Rx here, Rz here, and Rx as usual here, and reverse C naught. So I hope you understand how I have applied this method. Okay, so what I observe is final observation. This is true not only for Rx and Rz. For example, you have this one, what I observe. So here C naught, here C naught is there. Let me take a little bit big one. So here C naught gate, and here C naught gate, and here we have a single qubit where we are having A, B, B, A. Observe carefully, the diagonal elements are same and off diagonal elements are same, which is in case of Rx. And here any diagonal matrix, this must be a diagonal. That means let us say this is a C 0 0 D. Then what I observe, I have verified this, and reverse C naught, reverse C naught, and those two operations are interchanging. Here you are getting the diagonal C0 0D, and here you are getting that upper operation A B B A. So earlier case, why it is happening, why it is correct, because see this one here Rx, if you interchange that first diagonal and interchange the second diagonal elements, you will get the same matrix again, and that means A A B B, like that. And the next RZ is a diagonal matrix only, so that's why this is happening, right? And till now we have discussed an alternate method, uh, by using alternate method, how to check the quantum circuits are equivalent or not, equal or not. Okay, so I hope you understand. If you have any trouble and if you are facing any trouble in solving the circuit, so please contact. Okay, so thank you, and we will meet again in the next lecture. Welcome to UV Physics Academy. So here we are discussing how to solve quantum circuits by using our new approach. Just I am using the decimal notation and the decimal algebra to understand the operations. Finally, if you want to convert into binary notation, you can convert, it's not a problem. Okay, but I request you please watch that earlier lectures, then you will understand what is this new approach. Okay, so in this let us take a few quantum circuits and let us try to solve by using the new technique. So here this is the first circuit, and two qubit states are there. That's why I'm applying the decimal notation 1 and 2. Three states are there, 1, 2, 4, like that you have to write. Okay, now I'm writing the operations. So starting with, I mean, left to right, careful, these are the operations. Whenever this is the initial state, so here left side operator will operate first, a right side operator will operate last. That's why left to right. Okay, so here it is S, it is on 2, that's why 0 comma 2. I hope you know this notation also. If it is a single qubit gate, operation is represented by 0 comma T, T for target, the target is 2 there, and you have to add the remaining number, that is a 1 comma 3. Next again S, it is on 1, that's why 0 comma 1, you have to add to 2 comma 3. Next head mark, it is on 1, 0 comma 1, you have to add to 2 comma 3. Next control X, that means C naught is there. C naught operation, that means 2 qubit operation is a CU. That operation is represented by C comma C plus T. That's why 1 to 2, 1 comma 3. Okay, right. So now let us take the initial state. So here 0, 1, 2, 3. So I hope you know these matrices also. Now I am writing initially. I hope you know this. 1, 0, 0, I. And head mod also I am writing here 1 over root 2, 1, 1, 1 minus 1. And in our method, please remember, in this bracket, first elements, first numbers off, second on, off, on, off, on. And for operations, you have to use the first column for off, second column for on, first column for off, second column for on. Now let us apply. First here we have S gate. So 0 off, no change, 1 off, observe please carefully this one. Okay, so 1 off, no change, 2 on, that's why I2, and 3 on, I3. Again one more S. Okay, at a time 2 operations you can do, but better to do it one by one first time. So please observe this. Now 0 off, 1 this time it is on, that's why I1, and 2 off, no change, and 3 on, that's why minus 3. Next we have hide mod operation. I'm not taking a normalization constant initially. Finally, the final state I will introduce the normalization constant there. Okay, you don't need to bother about that normalization constant now. So here a 0 off, that's why 0 plus 1, you have to use that first column 1 1. Next I 1, that is on, you have to use the second column, that's why 0 minus 1, 1 minus 1, 0 minus 1. Next I 2, that is off state, that's why 2 plus 3 minus 3, that 3 is on, that's why 2 minus 3. Next after that we have a C naught operation which flip 1 to 3 and 3 to 1. Okay, right. So this is a 0 plus 1 3, I 0 minus 1 become 3, and 2 plus 3 become 1, minus this is minus 2 plus 3, that 3 become 1 again. So this is the final state. Okay, so generally how we will do this, by getting a unitary matrix corresponding to this transformation. How you will write that unitary matrix of the circuit? Generally we will find the matrix product, but matrix product order is from right to left, not from left to right. Here in our method we are taking operations, that's why left to right, but here the matrix product right to left and top to bottom. Right to left ordinary product, top to bottom tensor product. So that's why this is C naught normal product. Here head mod is there, nothing is there means here we have identity. So that's why you can take I tensor H top to bottom, not from bottom to top. So next one again S tensor S. Then you will get a unitary matrix of order of 4 by 4. But in our method, how to get this unitary matrix? This is very easy. So please take this matrix representation. Here you have 0, 1, 2, 3, and this is also 0, 1, 2, 3. I am taking here a decimal notation only to write it very easily. Now this is the unitary matrix corresponding to the circuit. So observe carefully here, first initial state 0 and the final state is a 0, 3. So wherever you have 0, that amplitude is 1, 3 amplitude is 1. One thing I forgot, normalization constant 1 over root 2, because 2 states are there finally, 1 over root 2. 4 states are there, 1 over root 4. So let me write that 1 over root 2 outside. Next one, for 1, this is the final state, that means 0 I, for 0 it is I, for 3 it is minus I. Next for 2, 1 I1, that means I here, 2 also I, observe carefully this one over. Next for 3 it is 1 minus 2, 1 minus 2, like this, and the rest of the elements are 0. So this is the unitary matrix corresponding to that circuit. Now you got one more doubt. So how to check whether it is right or wrong? Let us take a simulator. Okay, so here we have S, and here one more S, head mod, and after that we have this. Let me check. Yeah, this one, right. Fine. Now this is the circuit we have. Now here both initial state 0, 0, that is a decimal notation, or it is a 0 state. Then it's a linear combination of these two, and here a small problem is there that I will explain later. So here 0 and this is a 3, okay, 3. So absolutely 0 plus 3. Next you can check like this, but a small issue is there that I will tell you. Now I am checking for 3. Okay, so for 3 we got 1 minus 2, that means for 1 we got a phase difference 0, and for 2 we got the phase pi, because minus 2 is there. And here the small issue is there with this thing. While I'm constructing this algebra, I have taken the order of that qubit binary states from bottom to top I have taken, but here they are writing from top to bottom. That is the small change. That's why if you see, if I take the input as 1 1, I got like this. So here they have written in that ket 0 1. Remember, for us it is 1 0. I request you please change that order, then you will get the same answer whatever we got. So change the order 1 0, then it is a decimal 2. For decimal 2, phase is 180. This one. Okay, and see here, for them it is a decimal 2, but I request you please change the order. Please change the order. I verified with that matrix multiplication also. Whatever the answer I got, that is also right. And here the representation, a small difference is there, small change is there. So just change the order, that is 1 0 to 0 1, that become 1, decimal 1. So phase is a 0. So here if you see that this one, for 1 the phase 0, right? Okay, so if you have any doubt still with why it is showing some different answer, I request you please find this matrix corresponding to this product and just operate on the basis state 1 0 0, that is a 0, 1 0 0 0, next 0 1 0 0, 0 0 1 0. These are the basis state. Let me write and get this matrix. This is a 4 by 4 matrix, and after that just operate on the basis states 1 0 0 0, next 0 1 0 0, next 0 0 1 0, next 0 0 0 1, because this is 0 1 2 and 3. You will get the same answer whatever we got. Okay, so you can check it. Right, now let us go to the next circuit. Here this is the next gate, okay, sorry, next quantum circuit, and I am using the decimal notation 1 and 2 here. So I am writing the operations starting with the head mod, that is on 2 0 2, next 1 comma 3, and this is S, that is from 2 to 1, that's why 2 comma 3. Next again head mod, that is on 1 0 1. You have to add the remaining every time 2 comma 3, and this is the swap between 1 and 2. Okay, just I am representing like this operations. After doing the operations, if you want, you can convert that answer into binary states. That's not a problem. Okay, so here I am not writing the matrices because you know already. Okay, I am taking the initial state, that is a 0 1 2 3. So here head mod is operating, so this is off on. So 0 is off, that's why 0 plus 2, 1 is off, 1 plus 3, 2 on, 0 minus 2, 3 on, 1 minus 3. I am not writing the normalization constant, finally I will write. And the next head S, so 0, 2 off, you got a doubt. So what about 1? There is no 1 and there is no 0. One more time, here there is no 0 1, that means its identity, no change. So here 1, no change, 3 on, that's why plus I3, because here I will come, here nothing will come. 0 minus 2, 1 minus I3, because the 3 is on. Next again hard mod operation is there. Okay, good. So 0 off, that's why 0 plus 1, plus 2 off, 2 plus 3, carefully observe, 1 on, that's why 0 minus 1, plus I3 on 2 minus 3, on second column of first column. Next here you need not to write the third one, directly we can write. Okay, so here we have plus and this is minus, so that's why just change the sign here. That means 0 plus 1 minus 2 plus 3. And the next one, here we have plus and here we have minus, that's why just change the sign here. So that is 0 minus 1 minus I 2 minus 3. Next after that swap gate. Okay, and the final answer. So here I have 4 states output. That's why I can take normalization constant 1 over root 4. So here swap between 1 and 2. Okay, so this is a 0 plus 2, 1 plus 3. Next is 0 minus 2 plus I 1 minus 3. Next 0 plus 2 minus 1 plus 3. Next 0 minus 2 minus I 1 minus 3. Right. So you can check whether this is right or wrong. So here I'm taking this circuit. So this is sorry, head mod, and after that so control S, and again head mod and swap. So here I have taken 0 input. See, we got the linear combination of all state with the phase 0. So if you observe carefully, here we got all the states. And let us check the finally third one. You can check the remaining. Okay, so here we have, observe carefully, we have to change the order whatever they have given in that simulator. Okay, so 1 1. Now see, here 0 state phase difference 0, and here third one is having a 90 plus 90. That means there you will get a I. Check. So this one minus I minus 3. Okay, so that is nothing but plus I. Next for 2 it is a minus, so that means pi. And don't forget, so here they have written 0 1 and a decimal 1. Remember, please take the reverse order. Maybe that is because of my whatever the algebra I started, maybe that is the reason, I don't know exactly. Okay, so please change the reverse. They are writing from top to bottom, just write bottom to top. That is 1 0. 1 0 in our case it is a 2, so that is 190. Okay, and this one minus I. Okay, you should get minus I for what? Please change the order. That is a 0 1. 0 1 is a decimal 1, decimal 1 here, decimal 1. Okay, so I hope you got this. Okay, and if you want, you can write the unitary matrix corresponding to this very easily. Okay, so take 0 1 2 3, 0 1 2 3. Now for 0, normalization constant 1 over root 4, so we can write outside. For 0, we have all the states. For 1, 0 minus 2 I minus I. For 2, 0 2 minus 1 minus 3. For 3, 0 1. For 2 minus 1. For I, sorry, for 1 minus I. For 3 it is I. So I verified by using that matrix product also. Okay, so we got the same answer. Don't bother about that order in that simulator. So just take the reverse order and check your answer. Okay, let us go to the next one. So here we have again 2 qubits states are there. I have written this decimal notation 1 and 2. Let me write the operations first. So this is starting with H. 2 head mods are there. 2 head mods you have to take. Add 1 1 3, and next head mod is on 1 0 1 2 comma 3. Now you got it out which head mod I have to take, that bottom one or top one. You can take anything, it's not a problem. In our method there is no issue. Next Z, it is on 2, that's why 0 comma 2 and add 1. Next C naught, that is 1 2 2, that's why 1 comma 3. Okay, off on off on off on. Fine. Now let us take directly 0 1 2 3. Now head mod Two head modes you can operate at a time, but once you practice it well, you can write at a time, it's not a problem. Okay, right. And 0, I'm not writing any normalization constant. Off state, that's why 0 plus 2. 1 off state, 1 plus 3. 2 on, 0 minus 2. 3 on, 1 minus 3. Next again head mode, 0 0 plus 1. 2 2 plus 3. 1 on, 0 minus 1 plus 3 on, 2 minus 3. 0, say just to change the middle sign. I hope you understand what I'm saying. No need to bother, just to change the middle sign. And this is a 0 minus 1, and just change the middle sign here, this one, minus 2 minus 3. That's it. Next again we have Z operation. Okay, off, no change. On, there is a phase difference, you have to multiply with the minus 1, because you know the matrix 1 0 0 minus 1. Off, no change. On, minus 1 extra. 0 plus 1 off. 2 is on, that's why minus 2 minus 3, I'm taking minus common, that's why I'm writing 2 plus 3. Next is 0 minus 1. Again here both 2 and 3 are getting minus sign, that's why I'm taking minus outside. I hope you understand. Now the same thing, just to change the sign in the middle. It's easy, no need to worry. And after that X gate is there, which flip 1 and 3, 0 plus 3. Let me take little bit this side. Yes, 0 plus 3 minus 2 plus 1. Next 0 minus 3, because it is flip 1 2 3, 3 2 1. So 0 minus 3 minus 2 minus 1. 0 plus 3 here, and plus 2 plus 1, and 0 minus 3 plus 2 minus 1, like this. Okay, so now if you want, you can check by using that simulator, and you can write that unitary matrix also now. 0 1 2 3, 0 1 2 3. So if you want to check whether, cross check whether it is right or wrong, just find the matrix multiplication and get the unitary matrix. You will get exactly whatever we got. Okay, if you get the same thing, our method is right. If you get a different one, our method is wrong. So I have already checked, so I request you please check this with the simulator also. Okay, so here we have 3 qubit states. Okay, so first let us take decimal notation 1 2 4. Right, so write the operations from left to right. So first head mod is on 2 0 comma 2. Next you have to add anything you can add. Okay, so here I am adding a 1. But remember, whenever you are adding the another state, decimal state, you have to add to the all previous operations. That means now you have to add 4, that is a 4 comma 6, and this is a 5 comma 7. So the next we have one more head mode operation on 1. So that's why you have to take all the operations, that is a h of 0 comma 1. Now this time you have to add a 2, that is a 2 comma 3. Next, whenever you are adding any state, you have to add that number to all the previous operations. 4 I am adding now, 4 comma 5. Now this is a 6 comma 7. Next we have a C naught, that is from 2 to 4, that's why 2 comma 6. Next we have to add 1, 3 comma 7. Next we have 2 to 3, 2 to 1, that's why 2 comma 3. So you have to add 4, that is 6 comma 7. Okay, right. So remember, this is off on like this. Now here 3 qubit states are there, that's why 0 to 7 we have. But here a small technique is there. If I take this first numbers 0, 1, 4, 5. For the second numbers, I need not to do it again. You can simply change the sign in the middle. That is the advantage with the head mod. That's why I'm taking a 0, 1, 4, 5. This is the initial state I have taken. Now applying the head mod. Okay. So I'm not taking normalization constant. If I forget earlier normalization constant, you just add that and you just multiply with that factor. So here it is of 0 plus 2, of 1 plus 3, 4 of 4 plus 6, 5 of 5 plus 7. Right. Next again head mod. Okay. So 0 of 0 plus 1, 2 of 2 plus 3. 1 on 0 minus 1, carefully observe, 3 on 2 minus 3, 4 of 4 plus 5, 6 of 6 plus 7, 5 on 4 minus 5, 7 on 6 minus 7. So here I have two X gates. You can operate directly both at a time, no issue. Just observe carefully how I am doing. First take 0. Here there is no 0 and 1 and no 4, 5. That's why there will be no change in that 0, 1 and 4, 5. Okay. So 0 as it is, 1 as it is. Next 2. Careful. 2. 2 becomes 6. 6 becomes 7. That's why 7 plus 3. 3 to 7, 7 to 6. I hope you got it. Next one, 0 minus 1, no change. Now again 2. Already you have done earlier, only sign in the middle it is, middle sign is changing. That means 7 minus 6. Directly you can write because just now you have done. So 4, there is no change. Now 6, do it one time. 6. 6 become 2, 2 become 3. Plus 7. 7 become 3, 3 become 2. The next one no need to do, directly write. Only just change the middle sign here, this one change. So that's why this is a 3 minus 2. This is the answer. And the advantage of this method, if you want to write the remaining, that is a 2, 3, 6, 7, you need not to do all these operations. Directly come here and see, because of this 2 on state, here you will get a minus sign actually. 0 minus 2, 1 minus 3, 4 minus 6, 5 minus 7. Because all are on. So what is the difference between that earlier answer and this answer? Only sign in the middle. Here this middle sign, here this middle sign. Just change it. So 0 plus 1 minus 7 plus 6. 0 minus 1 minus 7 minus 6. 4 plus 5 minus 3 plus 2. 4 minus 5 minus 3 minus 2. Normalization constant 1 over root 4 because of 4 states are there, right? Let us go to the next one. This is a quite interesting one, and here all the initial states having the head mod operations. Okay, fine, which creates a superposition state of all qubit states, that is 0 to 7. Okay, so here it is 1, 2, 4. If I write that operations, it takes so much time. So what I want to say in this case, because whenever you have all head mod operations, you can apply that method also, but it takes a little bit more time to write all the states. My advice, you please fix any initial state. First I will do for 0 initial state. Okay, you can try another one. Okay, so I'm taking a 0, 0, 0. That means I'm finding the output for 0 state. So this is, so here why you are not writing the operations? Only I won't write this, okay, because it takes so much time. Okay, so what I'm saying is, if you want you can write that method also. Okay, so okay, let me explain that method and you can try that also. So here we have h of 0 comma 4. I'm adding 1, 1 comma 5. Next I'm adding 2, that is a 2 comma 6, and that is again 3 comma 7. Yeah, but the problem is one more h is there. So 0 comma 2, 1 comma 3, and now you have to add 4 and 5 comma 7. Next one more head mod, 0 comma 1, 2 comma 3, and again you have to add 4. This is what I'm saying. So it may take some more time to get this, okay, but here directly we can write. If you know that initial state one by one, you can write very easily. And after that, this is I hope you know this is a CZ, okay, this is also CZ. That means z of 422 or 224, anything. That's why they have given that notation. So for control z, control and a target, if you interchange, there will be no change. In the earlier lectures we have already derived that. So that is a 4 comma 6, and one more sorry, after that you have to add 1. Don't forget to add this, please. Next z again, 4 to 1, that's why 4 comma 5. The remaining 2 you have to add, that means 6 comma 7. Next after that again head mod operations are there. So here we have head mod 2, that is a h of 0 comma 2, add 1 comma 3. For this you have to add 4, 4 comma 6, you have to add 4, 5 comma 7. So this is h01, 2, 3, you have to add 4. Just after writing this you feel a little bit so comfortable. I mean, it's very easy to handle this algebra. Okay, let me explain another technique. So here I will tell you one more technique because it's a little bit lengthy. Okay, so let us suppose here we have initial state 0, because all head mod gates are there, that's why you are facing this trouble. So just apply this technique whenever you have all head mod operations like this. We have here 0 0 0. Actually this is you can write like this also. 1 minute. This notation represent the decimal 0, but it contains 3 qubits 0 0 0. Okay, fine. Now the technique is very simple. If you have all zeros like this, maybe in the earlier, I hope I explained somewhere head mod shortcut method or something, head mod operations, somewhere I have explained in one video. So if you have time, please watch that. This is very simple. Whenever you have 0, you have to take a plus plus. If you have 1, you have to start with plus minus. Always you have to start from this end, that is a 0. So what are these plus minus? I will tell you, just wait. So this is almost in all the algorithms. While I am using this technique, my new technique, I have used this notation only. Okay, so here 0 plus, starting here 0 plus plus plus, next again 0 is there, plus plus. Okay, for every bit or for every digit you have to repeat the earlier things again. If you get 1, interchange the sign. If you have 0 again, the same sign repeat. So that's it. Again I'm writing for third 0, but earlier I have 4 states. Repeat again 4. Maybe here you won't find this method is good. I will take one more example. So this means what? It creates also a superposition of 0 to 7 with all amplitudes. That means plus signs. So we can write this as a 1 over root 8. That is 0 plus 1 plus 2 and plus 3, 4, 5, 6 and 7. I will take one more example. Now, so let us take 101. That means 5 I am taking, 3 qubits, that is 101. Please focus on that first one, this one. Okay, so here I told you already, 0 is there, start with plus plus, 1 is there, start with plus minus. But whenever you got 0, repeat the same signs again, and if you get 1, you have to multiply with the minus. That means you have to interchange, plus become minus, minus become plus. That's a small technique. So here 1 is there, so that's why plus minus. Next 0, repeat. Next 1, take a reverse, minus plus minus plus. So this is nothing but 1 over root 8, first one 0, minus 1, plus 2, I hope you are observing, minus 3, minus 4, plus 5, minus 6, plus 7. Okay, so we have already written the initial state for this 5. That means here I have taken 1, 0, 1. Okay, so let us continue the output for this state. So all these head mod operations are over. Okay, so if you want to check whether this one and that one both are same or not, I will tell you. Just wait. Um, here I will take 5 you have taken, right? Observe carefully. Now this first head mod, 5 is on, that's why 1 minus 5. Next head mod, 1 off, that's why 1 plus 3, minus 5, that is off 5 plus 7. Next again one more last head mod, 1 become 0 minus 1 because on state, 3 become 2 minus 3, and next minus 5 become 4 plus 5, sorry, 5 is on, please observe last one, this one, 5 is on, that's why this is 4 minus 5, and next minus 7, again on 6 minus 7. Now carefully check whether both are giving same answer or not. 0, 1 minus, 2 plus, 3 minus, 4 minus, 5 plus 5, 6 minus 6, 7 plus 7. Just to cross check, maybe you will be having a doubt how this both are same. Just I have verified that. Okay, now I'm going to take this input. Now we have to apply JET gate. So 2 JET gates are there, that's why I'm applying both at a time. No need to worry, you can apply. So here there is no 0, no 1, no 2, and no 3. So these are as it is. Okay, so the only change is here I am taking JET, 2 JET gates. So 1 over root 8. So 0 no change, 1 no change, 2 no change, 3 no change, 4. So observe carefully, off, on, off, on. In both the JET operations, 4 is off only, that's why no change. Next 5. For first JET off, but second JET on, that's why minus extra. I hope you understand. Next minus 6. Okay, for first JET it is on, will become plus 6. Next one it is off, it is as it is plus 6 only. That means already one JET converted to plus 6. Next 7, first JET on, that's why minus 7. Next again on, one more time, that is a plus 7. That's it. And after that we have this is quite interesting, observe carefully, this is very nice. Now I am applying the first head mod, right? So here you need not to operate again head mod here, it's very easy to do, that's why I am preferring this algebra. Now see, here we have this 0 minus 1 plus 2 these states. Now carefully check, here we have first head mod, that is a 0 2. It will create the superposition of 0 and 2. If it is a 0, it makes 0 plus 2. If it is a 2, it makes 0 minus 2. Now reverse, again you are applying the head mod on this. So that's why you carefully see 0 plus 2. So strike 0 plus 2 and write 0. That means that first head mod converted 0 plus 2 as 0. I'm not bothering about the normalization constant. Finally I will write. I hope you are following. This is very nice. Please check. Next one, minus 1 minus 3. Take minus common, then it is a 1 plus 3. Okay, 1 plus 3, that means it creates as 1. 1 plus 3, if you again operate head mod, it will become 1. You must have these numbers. Observe carefully. You have to take these combinations only here, these combinations. Next, still not understanding. Cancel 1 and 3. Next we have 4 6 minus common 4 minus a 6, that become 6. Next 5 7 minus common 5 minus 7, that is 7. And again head mod is there. This time you have to see these combinations, second combinations. Careful. So here we have 0 1, 0 minus 1, cancel and write 1. Okay, so I hope you are observing. A minus common, that is a 6 plus 7. If it is 6 plus 7, here we have this combination which gives you 6. So that's why this is 6, because you have taken minus common. So only 2 states remaining, 1 over root 2. Now let us check whether this is right or wrong. Okay, wait. So here I have taken the input as 101 and this is the output. If you want, you can convert this into a binary notation, that is 001 minus 110. Okay, let me check. Here we have head mods, 3 head mod, and this is 101, that is a 5 input, and after that we have control Z. Next here we have only 2. Now please check 5. Here we got the superposition of 2 states only, but I request you, while you are checking this, you have to take the reverse order. There it is showing that 100, please take the reverse order 001. So that is a 1, this one. Okay, and the next one is 011, please take the reverse order 110, and that too phase difference. See here 180, see that phase 180, and here we have minus, this is a pi, phase difference. Absolutely will get the same answer. Now I request you, I am giving this as exercise to you. So take initial state as a 6, that is a 110, and you please try. Okay, so you apply this technique, whatever I have explained here, this. Okay, it's a very easy one. So thank you, and we will meet again in the second part. Okay, so thank you. So here we are applying this new technique to solve these quantum circuits, and in the next lecture we will solve some other quantum circuits. But I request you, please practice this method. I feel little bit easy to get the final state, and it is very easy to construct the matrix, that means unitary matrix corresponding to the quantum circuit. Okay, right, thank you. So welcome back, and here this is the next quantum circuit, and 3 qubit states are there. I am taking the decimal notation 1 2 4. Now I am taking the operations from left to right. So here head mod operation is there, h of 0 comma 4, and add 1 1 comma 5. Next you have to add the remaining 2 comma 6 and 3 comma 7. Next after that we have C0, that is x, 2 to 1, so that's why 2 comma 3, and you have to add the remaining, that is a 4. If you add 4, 6 comma 7, and the next we have x, that is 0 comma 2, add 1, 1 comma 3. Next you have to add 4, 4 comma 6, 5 comma 7. Next we have z on 1, that's why it is 0 comma 1. Next add 2, 2 comma 3. Next add 4, 4 comma 5, 6 comma 7. Whenever you are adding that a decimal state number, you have to add all the previous operations. Okay, and after that we have again c naught, but this time it is from 1 to 4, so that's why 1 comma 5, and the remaining is 2, that's why sorry, this is 3 comma 7, you have to add 2, that's it. And fine, so once you got all these things, now take the initial state. I told you one small technique, whenever head mod operation is there, better to take these first numbers in that bracket, off on off on, so this is off on like this. For x it is not required, it's just a flip. Okay, so I'm taking the initial state as 0 1 2 3. So first a head mod, so here it is a 0 plus 4, 1 plus 5, 2 plus 6, 3 plus 7. I'm not taking any normalization constant, and after that we have 2 x gates at a time, you can apply, no issue. So I'm writing 2 x gates there, only x gate, and now first is 0, here there is no 0, here 0, 0 to 2, that's why it will become 2. Next 4, here there is no 4, so but here 4 to 6, that's why it is 6. Next 1, in the first here we don't have any 1, so that's why just go to the next one, 1 2 3, 3, 5, here no 5, next 5 to 7, next 2, 2 to 3, here 3 to 1. Careful, you have to see both the things. So here 2 to 3 and again 3 to 1, so that's why we have 1 here. Next 6, 6 to 7, 7 to 5, next 3, 3 to 2, 2 to 0, next 7, 7 to 6, 6 to 4, and after that j, which gives some phase change to on state, and off state no change. Here 2 off as it is, 6 off, next 3 on, minus 3, 7 on, minus 7, 1 on, minus 1, 5 on, next 0 off, 4 off, and finally there is one more x gate which flip 1 to 5, 5 to 1, and 3 to 7, 7 to 3. So 2, 6 no change, minus 7, minus 3, minus 5, minus 1, because 1 and 5 flipped, and 0 plus 4. So 2 states are there in that combination, that's why I'm taking the normalization constant as 1 by root 2. Right. So next, if you want to write the other states, that is the next column, 4, 5, 6, 7. Remember, you need not to do anything, just change the middle sign. This is the advantage whenever you are dealing with this head mod operations. And finally, I can write directly, that is a 2 minus 6, minus 7 plus 3, minus 5 plus 1, and 0 minus 4. Normalization constant is as usual. So if you want, you please check and check whether you are getting this answer or not. Please check. Okay, and after that you can implement that. You can take this circuit in the simulator and check what is the output. Right. So this is the next gate, I mean next circuit. Okay, so here also we have 3 qubits, 1 2 4. Let me write the operations starting with the head mod. On 4, h0 comma 4, h1 comma 5. Next you have to add a 2 2 comma 6, h 3 comma 7. Yes, sorry, yeah, it's fine. Now one more head mod is there, so that's why on 1, that's why h of 0 comma 1. So this is nothing but you have to add a 2 2 comma 3. Next add 4 4 comma 5 and 6 comma 7. So the two head mods over, and after that if you observe carefully here, see here we have c naught and here we have y. Now you got a doubt, which one we have to write first, y or that above c naught? See, here there is no connection between 2 and 1 states. That means I am talking about this 2 and 1 states. That's why you can write y either uh, before that c naught operations or after c naught operations, no issue. But if you observe carefully, here there is a one c naught, that's why you can't bring this y this side. Okay, but you can write this y either before this c naught operations or after c naught operations, you can write anything, so no issue. Now I am taking x, that is a 4 to 2 4 comma 6, and you have to add 1, that is a 5 comma 7. Next one more x, that is a 2 to 4 this time, so 2 comma 6, and you have to add 1, a 3 comma 7. Next you can take y, that is a 0 comma 1, y 2 comma 3. Next y you have to add 4 4 comma 5, y 6 comma 7. Next we have this is c naught operation, and here also you can take here this h either before this c naught or after c naught, any no issue, because there is no connection between 2 and 4, that's why you can write. So now I am taking c naught again, that is 2 to 3 and 6 to 7, and finally we have head mod. Let me take this here, and final head mod is on 4. The first one is repeated, 1 comma 5, 2 comma 6 and 3 comma 7. Fine, so everything is ready. Now we have to start the start with initial state, that is a 0 1 2 3. Now first head mod operation is there, so all are off, that's why 0 plus 4 1 plus 5 2 plus 6 3 plus 7. Normalization constant I am not taking now. And next one more head mod, so 0 off, 0 plus 1, I hope you already understand, off on like this, right? So plus 4, that is a 4 plus 5. Next one on, 0 minus 1, and this is a 4 minus 5. Next to 2 plus 6, 2 is a 2 plus 3 and 6 plus 7. 3, that is a 2 minus 3 and plus a 6 minus 7, right? And after that we have x operations. I am taking this combined x together, okay, no need to apply separately. I am taking 2x, so 0, here there is no 0, no 1, and 2 3 is there, 4 5 6 7 is there, so 0 1 as it is, 4 to 6 6 to 2, 5 to 7 7 to 3. I hope you are observing, please see this one, please see that operations. Next to 0 as it is, next plus, no need to do it again, because earlier above step 4 plus 5 you have written 2 plus 3, now 4 minus 5, that's why 2 minus 3 I am directly writing. Next to 2, here there is no 2, but second 2 you have 2 to 6, that's it. 6 plus 3, here there is no 3 but here 3, 6 plus 7. Next here 6 is there, 6 to 4, here there is no 4. Next 7, 7 to 5, that's it. The next one is easy to write because 6 minus 7, just change the sign. Change the sign. Earlier it is 6 plus 7 become 4 plus 5. Now 6 minus 7 4 minus 5 I am writing. Next y. So here off state you will get I and on you will get minus I. Flip with some phase change, right? Okay, right. So proceed. 0. This is I 0. Sorry, it should be flip. I'm sorry. That is 1 minus a 0. I hope you understand. Plus I again. I think everywhere I is there. So that's why what I'm writing is, I'm writing outside I right now. So 0 flip, 1 minus 0, because minus I will be there. I have written I written outside. Plus 2 become 3, 3 become minus 2. I already outside. Next 0, same, 1 plus 0 plus 2, sorry. Whatever you have written earlier, just change the sign in the middle. Because 2 become 3, 3 become minus 2, that's why minus of minus plus. Next is 6. 6 becomes 7, 7 become minus 6, 4 to 5, 5 to minus 4 because I is common. Next here just change the sign in the middle, no need to worry, that's it, easy. And after that we have one more x gate is there, so little bit lengthy, right? So here x, that is a 2 to 3, 6 to 7, this one I'm doing that. So 1 minus a 0 plus 2 minus 3, again 2 and 3 flip, and 6 and 7 flip. 1 plus 0 plus 2 plus 3. Next 6 and 7 flip, that's why 6 minus 7 plus 5 minus 4, no change. 6 plus 7 plus 5 plus 4, no change. Next again we have to apply Hadamard. So here there is no combination of 1 0 2, I think nothing, you have to apply again. So here we have to finally apply this Hadamard operation, right? So I'm not taking any normalization constant. So 1 is nothing but 1 plus 5 minus 0, 0 plus 4 plus 2, 2 is a 2 plus 6, easy, minus 3, 3 is nothing but 3 plus 7. Next we have to take 1, the same above, just change the sign. I think now you understand what I'm saying. This is 1 again, that is a 1 plus 5, so plus 0 plus 4 plus 2 plus 6 plus, earlier minus is there but here now plus is there, like this. Next one 6, 6 become 2 minus 6 minus 7, 3 minus 7 plus 5, 1 minus 5 minus 4, 0 minus 4. Next one directly you can write, this is 2 minus 6, earlier minus now plus, okay, and here as it is, and here plus as it is, 1 minus 5, earlier minus, now it is plus, that's why plus 0 minus 4, that's it. And normalization constant 1 2 3 4 8 states are there, 1 over root 8. It's not surprising, 3 Hadmards are there, 1 over root 2, 1 over root 2, 1 over root 2. So you got 1 over root 8. And next if you want to get this 4 5 6 7, this is the initial state, then what is the final state? You need not to do it again. This is the advantage. And here this sign will change, this one will change, this one will change, here change will come, here change, here. So this part, just take, if plus is there take minus, if minus is there take plus. So here you will get minus, sorry, so here you will get minus, and this is plus, minus, 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 plus, minus, minus. So that yellow color is for this. Right, the rest of the things are the same. And I think I forgot this I outside, I'm sorry. So this is I outside. Okay, now you can write the unitary matrix for this also. Okay, right. So here this is our next quantum circuit, and here also we have 3 qubit states. That's why I'm taking the decimal notation 1 2 4. Okay, start from left to right. Start with Hadamard, 0 comma 1, add 2, 2 comma 3. Next you have to add 4 to the all the earlier operations, 4 comma 5, 6 comma 7. Next S, that is 2 2 1, that's why 2 comma 3. Add 4, 6 comma 7. X, 4 comma 6, 5 comma 7. S dagger 2 comma 3, S dagger 6 comma 7. X 4 comma 6, again 5 comma 7. This is a little bit quite interesting. No need to bother about that. These many things are there. Just wait and see. Some magic will be there. And here S 4 comma 5 and S 6 comma 7. And after that H on 1. That's why I repeat. Now carefully observe. So here we have this one. Carefully observe this operation. Whenever you have here X, poly X matrix, and some matrix A, B, C, D, here also I hope I explained this. Whenever you have this situation, this one, this is the right for R, right side R for rows. So it will interchange rows. And this X from left side, so column, let us say column. Automatically one is a right side means other one is a just row is other one is a column. So this will interchange columns. Then what will happen? Then the diagonal elements will interchange. If you want you can check. So this is a B and C. This one possibility. Of course here we are not using that. Okay, just to keep it aside. This one we are not using this, leave it. And here what you are using, please observe. Here X 4 6 and here X 4 6 and here X 5 7, here X 5 7. But you don't have here S dagger 4 6, S dagger 5 7 combination. If it is there, then you can multiply like that, interchange the diagonal elements. But it's not like that. Then what is the technique here? Very simple. Now first observe this one, very important. Please observe this one, 4 6 and 4 6. That means what? From right side 4 6, left side 4 6. That means 4th row and 6th row interchange, 4th column, 6th column interchange. That's why this 6 number is cancelled and it will become 4. Oh, fine. No need to multiply. Yes, no need to multiply. Next observe, still not understanding. So here we have 5 7, 5 7. So from right side, 5th row, 7th row interchanged. From left side operation column, 5th column, 7th column interchanged. Then in this matrix, that the 7 is replaced with the 5. Okay. Then this total operation, that means this gone now. This operation's gone, already over. The remaining is, here we have s of 2 comma 3, here you have s of 6 comma 7, and s dagger 2 comma 3 already there. Now s dagger 4 comma 5 it become, because of that x matrix x operation. One more time, you have x and operator and x is there. This x will interchange the rows and this x will interchange the columns. So this is the advantage. And after that we have s of 4 comma 5 and s of 6 comma 7. Now please focus on this. Now here this is s 2 comma 3 and this is s dagger 2 comma 3. That's why cancel I 2 comma 3. Next one, here s dagger 4 comma 5, here s of 4 comma 5, cancel. And finally we left with here s that is s square 6 comma 7. Nice. Finally this entire operations from here to here, that is equivalent to s square 6 7. That means it will affect only 6 and 7 states. That too, if it is 6, no change, because S is a diagonal matrix. I hope you know S square is nothing but Z. 1 0 0 minus 1. So 7th state, I mean if it is 7, you will get minus 1. Fine. Now let us proceed with the head mode operation. So I am taking that first elements 0 2 4 6, because it is easy to write the next one. I am taking head mode 0 plus 1, 2 plus 3, 4 plus 5, 6 plus 7. Now you need not to operate all these things directly, you can. In this method, this is the one of the advantage, cancellations will be there. Okay, so I hope you are following this method. Okay, if you are facing any difficulty, please let me know. And yeah, so only s square operation. So 0 plus 1 no change, 2 plus 3, 4 plus 5, 6 also no change, but 7 minus a 7. That's it. And finally again one more head mod is there. Now this is also simple, and here we have head mod operation. Say 0 plus 1 combination, 0 plus 1. For example, if you have 0 and head mod is operated, this head mod operation is operated, what you will write? 0 plus 1. Now here 0 plus 1 is there, that's why write 0. Next to 2 plus 3, write 2. 4 plus 5, write 4, because off state. And here 6 minus 7 is there, 6 minus 7, that's why on. Which one is on? 7 is on. That's it. And after that, if you want to write for the another unit input, 1 3 5 7, you need not to do all these things, directly come here, just write this, change the sign, 0 minus 1, 2 minus 3, 4 minus 5, 6 plus 7. Now you are applying a head mod on this. Okay, so 0 minus 1, on, which one is on? 1. 2 minus 3, on, 3. 4 minus 5, on, 5. 6 plus 7, off, 6. That's it. Okay, so I hope you are following this, and if you want you can check with this simulator. Okay, right. So the next one, here also we have 3 qubits. So let me represent the decimal notation 1 2 4. So first let me write the operations. Here I am writing. So first I am starting with the head mod, that is on 2, 0 comma 2, and add 1, 1 comma 3. Next you have to add 4, 4 comma 6, and 5 comma 7. Next x, it is on 4, 0 4, 1 5, 2 6, 3 7. Next C naught, 2 2 1, that's why 2 comma 3, add 4, 6 comma 7. Next again C naught, this time 4 to 1, 4 comma 5. I hope you are following. 6 comma 7. Next again C naught, this time 2 to 4, 2 comma 6, add 1, 3 comma 7. Next T, some phase gate is there on 4, add 1. Next add 2. Whenever you are adding, you have to add that number to all the previous operations. Don't forget this. Okay. Now this is also quite interesting. Now see here. Please observe here x operations. See x 6 comma 7, x 6 comma 7, that cancel because x square identity. Whenever you are doing like this, that numbers must be same. For example, you have 6 comma 7 and 6 comma 5, you can't cancel, right? And next, anything else, check. So you got one doubt. So here we have 2 comma 6, here we have 2 comma 6, shall we multiply and cancel? No. See, whenever you want to cancel this, be careful. X of 2 comma 6, x of 2 comma 6, that means you are bringing that x of 2 comma 6 this side. But in middle, you should not have any 2, you should not have any 4. Then you can multiply. But unfortunately, here we have 2. That's why you can't bring it. So leave it. Then what? Okay. So then apply the earlier technique. X from right side, x from left side. See, this is 2 comma 6, this is 2 comma 6. Okay. So 2 comma 6 can come this side. The reason is it is a 4 5, that is 2 comma 6, no common number. So now here 2 becomes 6 and 6 become 2, like that. That's why here whatever you have 2, that is replaced with 6. I hope you understand what I am saying. So that become x of 6 comma 3. Next, still not understanding, here x of 3 comma 7, here x of 3 comma 7. So from right side, third row, seventh row interchange. From left side, third column, seventh column interchange. That's why finally 3 is replaced with 7. Oh, finally again I got here x of 6 comma 7. Fine. So here I left with x of 6 comma 7. Next, anything else? Please check. This gone, 2 comma 6, everything is gone. Next, remaining x of 0 comma 4, x of 1 comma 5, next x of 6 comma 7. Now you got a doubt. Why you have written 6 comma 7 this side? Because there is no 6 and 7, na? That's why I can bring this side, no issue. Or you can keep it here, and here this is x of 4 comma 5. Okay, now you got it out. Why you didn't bring that 4 comma 5 here? Why you are not writing here? Because here 4 is there, I can't bring it. But earlier you have written 6 comma 7 this side. Because there is a no 6 and a no 7 number, that's why I can write commute, just like a commute, something like that. Okay, that's it. And this is the final x operations. And this side head mod as usual. Okay, and t as usual. Now let us take the initial state 0 1 4 5, because if I take the first elements, easy, this is 0 plus 2, 1 plus 3, 4 plus 6, 5 plus 7. Okay, next normalization constant I will write later. 0 become 4. You have to complete the operation. Okay, right. Start with 0. 0 become 4, 4 become 5. That's why it's a finally 5. Next to 2, there is no 2, no change. 1, 1 to 5, 5 to 4. 3, no change. 4, 4 to 0. 6, 6 to 7. Next 5, 5 to 1. 7, 7 to 6. That's it. And after that T operations. Okay, so off, on. 5 on. So I hope you remember that the T, let me write the T matrix here. The matrix corresponding to T gate. The phase difference pi by 4 for on state, and no change for the off state. 5. So e raised to I pi by 4, I am writing ket, plus 2 off state. Next 4, e raised to I pi by 4, I can't take out common, 3 off. Next 0 off, 7 on. Next 1 off, 6 on. That's it. And normalization constant 1 over root 2 because the two states are there. Next, if you want to get the other states, that is a 2, 3, 6, 7, apply our technique, no need to do anything, directly come here. Okay, easy. Here minus, here change minus, here this middle sign. So e raised to I pi by 4, 5 minus 2, and this is e raised to I pi by 4, 4 minus 3. Okay, so this is a 0 minus e raised to I pi by 4, 7. Or you can write here plus or minus like this. Plus is for these states and minus is for these states. Okay. So here this is the next quantum circuit, and 3 qubits 1, 2, 4. Let me write the operations. Okay, so this is a h of uh, 0 comma 4, and add 1, next add 2, next z 0 comma 2, 1 comma 3, 4 comma 6, 5 comma 7. Next we have C naught. Here wait a minute. Now what I am doing here, here we have a C naught combination is there. Okay, this one. Now carefully see. So why I am able to shift that y that side? Yes, there is no connection actually. Here there is no connection between these two. So that's why you can shift that y that to that end. Okay. Now one more time. So this one I am taking this first, and y just moving that side, right side. Okay. So here x combination, that is 4 comma 5, 6 comma 7. Next single x gate, that is 0 comma 1, 2 comma 3, 4 comma 5, 6 comma 7. Next C naught, that is a 1 3, 5 7. Now you can take y, that is on 4. So 1 comma 5 adding 1, next adding 2. That's it. Okay, now you can operate all these x operations at a time, but please check, is there any cancellations? No, here it's not like that. One thing is there. Yes, I think if you observe carefully, here 6 7. Oh, not one thing, two things are there. See here, x 6 7, x 6 7, side by side, cancel. Next x 4 5, x 4 5, side by side, cancel. That's nice. Okay, now let us take 0, 1, 2, 3. So first a head mod. I'm not taking any normalization constant. Earlier problem, if I am not taken, I request, yeah, I have taken already. Okay. So this is a 0 plus 4, 1 plus 5, 2 plus 6, 3 plus 7. Next we have Z. This is off and on, 0 off, 4 off, 1 off, 5 also. 2 minus 2, 6 minus 6, 3 minus 3, 7 minus 7. Next we have x operation. I am considering the total x operation at a time. 0, 0 to 1, 1 to 3. 4, no 4. 1, 1 to 0. 5, 5 to 7. Please observe. 2, 2 to 3, 3 to 1. That's why minus 1. 6, no 6. 3, 3 to 2. That's it. 7 minus 5. Okay, so please check. Right, absolutely right. And after that we have y. So here it is I, here it is minus I. That's why I'm taking I common. Okay, so it flip 3 flip to 7, and sorry, yeah, 1 minute, yeah. So 3 is off, so flip to 7, and 4 on, minus 0, because minus I is there, I already written outside. So 0, 0 to 4, I already written outside. 7 off state, minus 3. Okay, right. 1, okay, minus 5, flip. 6, minus of minus plus, flip to 2. Minus 2, flip to 6. 5 on state, that's why plus 1. That's it. Okay, so the normalization constant is root 2, 1 over root 2. And if you want to write for 4, 5, 6, 7, this is the advantage whenever we have head mod gate in the beginning, in the starting. So this is the advantage. No need to do all these things. And come here, I by root 2, just change the middle sign. Minus 5, minus 2, minus 6, minus 1. Like this. Okay. So I hope you are following all these quantum circuits. So this is the next quantum circuit. So I'm leaving this as a exercise to you. If you are interested, please try this. Okay, so I will write the operations. If you have still having any confusion, now see this, starting with h, 0 comma 4. Whenever starting it is a head mod, it is always having a advantage, because you need not to do the operations again and again. Okay, so h of 1 comma 5, next 2 comma 6, h of 3 comma 7. What I am saying is, you will write operations, I mean you will find the output state only for 0, 1, 2, 3. You won't find for 4, 5, 6, 7. You can write it directly. That is what I am saying. So next control S is there, 2 to 4, 2 comma 6. You have to add 1, that is a 3 comma 7. Next control T, 1 to 4, 1 to 5. You have to add 2, 3 comma 7. Now head mod 0 comma 2, 1 comma 3, 4 comma 6, 5 comma 7. 0 comma 1, and next add 2, next add 4 to all the states. Next swap, that is 1 comma 4, but remember you have to add the remaining qubit state, that is a 2. So swap 3 comma 3 comma 6. It swap finally 1 to 4, and 4 to 1, and 3 to 6, 6 to 3. So I have written the operations and I request you please start like this 0, 1, 2, 3, and I hope you remember S gate, that is a 100 I, and T, that is a 100 e raised to I pi by 4. Okay, so try to do it carefully, and if you are facing any trouble please contact. Okay, I will write the final answer, then you will get some small, you will get some confidence. I will write the final answer. So here I have given the final output. I request you please check. Don't bother about this, okay? So that we can write it as e power I 3 pi by 4. Maybe once you have taken this circuit in the simulator, you will get a phase difference of 3 pi by 4. That means 135, something like that. Okay. So right, I request you please check. And the next one, if you want to take 4, 5, 6, that is by 4, by 5, by 6, by 7, then you have to simply change the signs. I hope you know that. Okay, right. Thank you. So this is also easy, you can do it. 1, 2, oh, okay, no problem. So 4 qubit states are there, but no issue, you can do it. So here I am taking the first head mode operation. So that is H 08, no need to get tension. That is a 1 comma 9, you have to add 1, next adding 2. Whenever you are adding, you have to add all the previous states. Okay, so now you have to add 4, that is 4 comma 12, 5 comma 13, 6 comma 14, 7 comma 15. Right, next after that we have X. So the advantage taking that head mod operation first. If you find 0, 1, 2, 3, 4, 5, 6, 7, you need not to write again, you will simply change the negative sign, negative and positive signs. X gate, that is a 4 comma 5, okay, and after that adding 2, 6 comma 7, now adding 8, that is 12 comma 13, 14 comma 15. Next we have anything you can take, either X or this control Z, anything you can take, it's not a problem. I'm taking again X because X is side by side, it's better. So on 1, so adding it 2, next adding a 4, next adding 8. That's it. Next control Z, that is 8 and 4, 8 comma 12, adding 1, 9, 13, so adding 2, 10, 14, adding 2, 11, 15, right? And after that S, we have 0, 8, the same operations, just H is replaced with S. Just I am writing this, but I request you please try. Not at all difficult algebra, okay, so just try. Just instead of finding matrices and multiplying, this is just an alternate way, that's it. Okay, and after that we have control Y, that is a 4 comma 6, adding 1, 5 comma 7, next adding 8, 12, 14, 13, 15, right? Okay, so I request you please try this also, and here I will give you the answer, you please check. So here I have given the final state answer. I think now you can write 8, 9, 10, 11, 12, 13, 14, 15. You can simply change the signs in the middle. That's it. So I request you please check this and right. So the last two circuits I have given as a homework. Okay. So I request you please try to do it yourself, and if you are facing any trouble, please contact. Okay. So thank you, and we will meet again. Welcome to UV Physics Academy. So here we are discussing how to solve quantum circuits by using our new method. So here I am discussing 3-qubit quantum gates and some quantum circuits. So in the earlier classes, we have already discussed a single qubit quantum gates and 2-qubit quantum gates. So I request you please watch that first two lectures if you want to understand that new method properly. Okay, right. Right. So 3-qubit quantum gates are represented by this C square U operation, where U is the single qubit quantum gate, which is represented by unitary matrix of order 2. Let me explain one more time about this new method. For example, you have a single qubit gate. That means this is the qubit state we have, and this is the a single qubit gate. So only one qubit state, that's why we have to write it as a 1. So the operation is represented by this is U of, it may be X gate or it may be S or it may be T or anything. Okay, so it may be H. So U of 0 comma T, T for target. Here the target is 1 because that U is operating on that. So that's why I have written this, just written in that form 0 comma T. So for example, in this case, it will become, I will write here U of 0 comma T. So in this example, we will write it as a U of 0 comma 1. Now you got one more doubt. That is, for example, I have 2-qubit states, but here I have single qubit gate. Then how to do? So 2 states are there. That's why 1, 2. Okay. So 1, 2. Now please take the operations. Starts with that U on 2. That is U of 0 comma 2. After that, whatever the state remaining, that means whatever the state remaining, you have to add, that is plus 1. So just a decimal addition, U of number addition, that's it, 1 comma 3. Okay, right. So that's it, and this is for a single qubit gates. And for example, if you have a 2-qubit, if you have 2-qubit gates, this is represented by CU, control unitary operation. So let me take, here we have 2-qubit states, and so this is the control bit and this is the target, and here we have unitary operation. Yes. So controlled operation, that means if C equal to 1, then only this unitary operator, this operator will operate on that target. Otherwise, it will be as it is, no change. Fine. Okay, how to write this? The operation is represented by, this is U of earlier 0 comma T, but here C involves. That's why what I'm saying is C comma C plus T. So this is the operation, right? So let me take a small example. In this case, it is 1 and 2. First, you have to write the decimal states 1, 2, 3, 4, sorry, 1, 2, 4, 8, 16, like that. Okay, right. And after that, the operation, this is U of 2 to 1. You are coming from 2 to 1. That's why 2 comma 3. That's it. Now, for example, you have 3-qubit states are there, but you have controlled operation from the first top one and bottom one, then give the notation 1 2 4. It is coming from 4 to 1, so that's why this is u of 4 comma 5. Next, whatever the remaining state, okay, so that number you have to add, that is a plus 2. This is u of 6 comma 7. If you already attended this method, you can skip this part and directly go to the lecture. Okay, right. Now let's discuss about this 3-qubit quantum gates. Fine. So this is represented by C square U. That means two control bits are there and one target bit, just like this. So this is the control, and this is the target. So C1 and C2 and one target. Then how to do this? So the meaning of this is both C1 and C2 both are equal to 1, that means on, then only this U will operate on T, otherwise it won't operate. That's it. Okay, so how to represent its operation? One more time, if it is a single qubit gate, U of 0 comma T, and add the number, whatever the number left, you have to add that decimal state number. Okay, next one, 2-qubit quantum gates, that is U of C comma C plus T. Now here we have 3 qubits, 2 control bits and 1 target bit. The operation is represented by U of, okay, so C1 plus C2. That means both must be on. What is the meaning of C1 plus C2? You are considering both C1 and C2. That means both are on. So C1 plus C2 comma, it is operating on T, that's why C1 plus C2 plus T. That's it. In this example, 1, 2, 4. Then the operation in this is represented by U of, so 2 plus 4, 6, comma 6 plus 1, 7. That's it. So it will affect only that 6 and 7 states. Don't get tension, this is a decimal notation. 6 you can write it as a 110 later, and 7 you can write as a 111 later. So because if you are doing the algebra in that decimal notation, so I feel it is a little bit so easy to get the final state. That's it. Okay, let us take an example. So what is the meaning of this? So here we know what is U. U is nothing but A, B, C, D, a single qubit quantum gate. The first column stands for the amplitudes corresponding to off state, and second column for on state. I told you already, first number is off, second number is on in that operation. Always first one is off, second one is on. Okay, what is the meaning of that? That a target, see, if these two are on, you see, you will get clarity. These two are on, this target is off, what you will get? 4 plus 2, 6. 7 on, what is the meaning of 7 on? Target is on, target is on. Here what is off and what is on? Target is on. If target is on, 4 plus 2 plus 1, 7. That's it. Okay, all right. Now I'm going to write this sixth one. Sixth is off, that's if it operates on this gate, what you will get? A 6 plus B 7. So it creates a superposition state with amplitudes that corresponding to that first column, and 7 operates on this U circuit. Okay, I mean quantum circuit. You have to take the second column. The reason is 7 state is on, so that is a C 6 plus a D 7. So that's it. So finally this is a C square U, that means 2 controls and 1 target. Maybe later you will get one control and 2 targets also will be there. So that's why I have written like this. Okay, fine. Now let us take some examples. So first one I am taking U equal to X. that implies it becomes c square x, and this is nothing but Toffoli gate, right? Okay, now this is nothing but, here you have three quantum states. In the place of x in the place of you have this x gate 1 2 4. Okay, so the operation is nothing but x of, because here the unitary operator is x of 4 plus 2 6 comma 6 plus 1 7. That means it flip 6 to 7 and 7 to 6. That's it. Okay, next let us take a few more examples. So let us take two more examples like this. Now give the decimal notation 1, 2, 4. Okay. So here two controls are there, that is 1 and 2. So that's why this is x of 1 plus 2, that is a 3 comma 3 plus 4 7. So it will flip only 3 and 7. So 3 to 7 and 7 to 3. Right, and come to the next one. Here also again we have to take a 1 2 4. Okay, so now the two controls, that is a 1 and a 4, 1 plus 4 5. So this is a 5 comma 5 plus 2 7. That means it will flip only 5 and 7. The remaining states are as it is. Okay, right. So let us take another one. So for example, so here let us take another 3-qubit quantum gate. So one control and two targets. Okay, so this is a control, and here we have two targets. So how to solve this? This is equivalent to like this. So the first one is here, and the second one like this. So successive operations. Okay, so let us apply 1 2 4. Apply our technique. So this is the first one, this is the first one. Now this is u of 4 to 2. That's why 4 comma 6. But what is remaining? 1 is remaining. So that's why plus 1, if you add plus 1, u of 5 comma 7. Close. Come to the next operation, this one. So this is coming from where to where? 4 to 1. That's why u of 4 comma 5, the remaining is 2. Please add 6 comma 7. That's it. So this is off, on, off, on. Let us take one example. Now here I am taking, so one control and two targets. Here I am taking X gate. Okay, right. So this is nothing but CX, I mean control not, and one more control not. So 1 2 4. Okay, so please take the first operation, that is X 4 comma 6, add 1 5 comma 7, next 4 comma 5, add 1 6 comma 7. That's it. Okay, so now here I will tell you a small technique here. Wait a minute. So here let me take the states like this. If I take 4 5, now please apply the operations. 4 to 6, 6 to 7, that's why 4 becomes 7. Next 5 to 7, 7 to 6, that's it. Okay, so again, if you want to check that 6 and 7, otherwise take the 7 and 6 again, you will get the reverse. That means 4 5. So finally we can write this as x of 4 comma 7, because it is flipping 4 and 7. Next one, x of 5 comma 6. That's it. So if you have two I mean, if this sees one control and two targets, that two target a single qubit gates are equal to x. So here it is a Pauli, sorry, here it is a Pauli x gate. Okay, then we are getting this answer like this. So we can write directly. So this is x of, this is a possible only when u equal to, this u equal to x, that is 0 1 1 0, not for all, only for x. So this is nothing but, here we have t1 and this is a t2 and this is a c. So this is nothing but c comma c plus t1 plus t2, c comma c plus t1 plus t2, x of c plus t1 comma c plus t2. Wait a minute. This direct operation only when only it is possible when that u equal to, here this u equal to x. For example, if you have two s gates or t gates, it is not possible. This is only for that u equal to x. So still not understanding. Wait a minute. For example, I have like this. Okay, once again I am taking this two x gates here and one control. So 1 2 4. So directly we can write x of 4 comma 4 plus 2, 4 plus 2 plus 1, that is 7, and x of 4 plus 1 5 comma 4 plus 2, that is 6. This is what I am saying. Same answer. But this technique please apply only when you have two same x gates there. If one u is I mean, if the u is s or t gates, don't apply this. Okay, right. Right. So next another 3-qubit quantum gate, Prediction gate. This is a CU swap. So here you have a swap gate. Let us say this is S1, sorry, S1 and S2. Let's just interchange this S1 and S2. Okay. But here you have C swap gate. That means if control bit is equal to 1, then only a swap will exist, otherwise no operation. Okay, fine. Let us say this is S1 and S2. Now how to operate this? Carefully see operation. This is I'm taking just F letter of C comma, that means if C is on, then only operation occurs. So that is a C sorry. So C plus S1 comma C plus S2. Only these two states will swap. So for example, in this case, it is 1, 2, 4, then the operation Prediction gate. So this is a 4 plus 1, 5, 4 plus 2, 6. So only the swapping is between 5 and 6. Other states are as usual. Okay. So I hope you understand. Still not understanding, one more example. Let us take 4 qubit states and I am taking, here is the swap gate. Okay, so this is the control bit. Now give the notation 1 2 4 8, right? Okay, so now take the operation. It is 8 2 1. So this must be on. That's why 8 plus 1 9. Anything you can add, but not this 4. Okay, so you have to add either S1 or S2. So 9 comma 8 plus 2 10. Okay, next this 4 is remaining if you observe carefully. So as usual, same method. Earlier we have added that 4. So this is a 13 comma 14. That's it. Okay, that means it flipped 9 to 10, 10 to 9, and 13 to 14, and 14 to 13. Clear? Right. So next, let us take this equivalent circuit. Now we want to show that these two are equivalent. This Fredkin gate and this one both are same. Okay, let us start. Now here I am taking the decimal notation 1, 2, 4. First let me check this operation. This is f of, just for my understanding I am just taking that letter. Okay, so it represent a swap gate only. You can write yes a swap also, it's okay. F of 4 plus 1, 4 plus 1 5, 4 plus 2 6, that's it. Now let us check. Here we have control NOT gates. Okay, 1 2 4. So this is the first x, that is 1 2 2, 1 comma 3, and 4 remaining you have to add. So don't forget to add the remaining state. Next one we have c square operation. I hope you know that also. So c square means 4 plus 2 6, comma 6 plus 1 7. That's it. Next one is also from 1 to 3, sorry 1 to 2, that's why 1 comma 3. Next one 5 comma 7, we have to add 4. Now carefully check. So here if you observe carefully, from right side we have x of 5 comma 7, from left side also we have 5 x of 5 comma 7. That means it will flip, if it is on right side it flip rows, 5th row and 7th row, and left side it flip 5th column and 7th column, interchange, sorry not flip, interchange. So that's why this 7 is replaced with the 5, 7 is replaced with the 5. Now the remaining is x of 1 comma 3, x of 6 comma 5, and x of 1 comma 3. Now you can bring this side, because here there is no common number. If there is no common number, they commute. I repeat, if there is no common number, they commute. So you can interchange the positions. Then x13, x13 cancel, and the remaining is x of 6 comma 5 or 5 comma 6, anything you can write, it's not a problem. That's it. So both are same. Let us take one more circuit. Right. So this is also a very interesting one. So you have to show that. So both the circuits are equivalent if this v square equal to x, Pauli x gate. Okay. So we have to show that these are equivalent. Now first let me take this operation 1 2 4. So this is the swap gate. Okay. So 4 4 plus 1, that is a 5. 4 plus 2, that is a 6. That means it will swap 5 and a 6. If you want, you can write in the binary notation 101 and 110. Now let us check this. Here, this is a very nice one. Please check 1, 2, 4. Now let me write the operations. First we have x, that is 1, 2, 2, 1 comma 3. Add the remaining, that is 5 comma 7. Next control v, you can write v of, no issue, 2 to 1, that's why 2 comma 3. Add 4, 6 comma 7. Next again control v, this time 4 to 1, that's why 4 comma 5. Next add 2, that is 6 comma 7. Next again c naught is there, that is a 4 to 2, 4 comma 6, and you have to add 1 this time, 5 comma 7. Next again v dagger. Okay, so v dagger is there. This is from 2 to 1, that's why 2 comma 3. You have to add 4, 6 comma 7. Let me take this side. Right. Next one. Again c naught 1 to 2, that's why 1 comma 3, and you have to add 4 of 5 comma 7. Next again c naught, this time it is from 4 to 2, 4 to 6, and add 1 of 5 to 7. That's it. Now carefully observe. No need to worry. It's easy only. No need to worry. Now here we have, sorry, this V dagger, this one V dagger, and this is also V dagger. Right. Now carefully observe. Here in this, sorry, in this we don't have 2 comma 3, there is no 2 comma 3. So then you can write this v dagger to this one, you can write this v dagger 2 comma 3 here, and these two will commute, these two will multiply, v into v dagger equal to I. So finally we can write, just to cancel these two, that means 2 comma 3 operation over. Next check one more. Here we have x 5 comma 7, x 5 comma 7, x into x, I. So leave it. Next, still anything is there? Yeah, one more is there. So if you observe carefully again, after cancelling this 2 comma 3, 2 comma 3, and here there is no 1 and 3, no 1 comma 3. That's why this x of 1 comma 3 you can write here, these two commute and that also gone. Now let me write what is the remaining, x of 5 comma 7, and here I have v of 4 comma 5, this one I am writing, and after that these two are side by side, v of 6 comma 7, v of 6 comma 7. I can write this as v square of 6 comma 7. Next 4 comma 5 I have written, and after that x of 4 comma 6, x of 5 comma 7, and after that v dagger 6 comma 7. Okay, and anything remains? Yeah, one more is there. Yeah, so here again x of 4 comma 6, the last one. So that's it, this is what we get. Now carefully observe, already they have given v square equal to x, so that's why I can write this as x of 6 comma 7. Now fine, now carefully observe, this is 5 to 7 and 7 to 5, this is a 5 to 7 and 7 to 5, that means fifth row and seventh row interchange, fifth column and seventh column interchange, that's why this 7 is replaced with the 5 and this 5 is replaced with the 7. Clear? Then this operation gone, v of 4 comma 7, sorry, x of 6 comma 5. Next, what is the remaining? Still we have one more, this here. Here we have 4 comma 6 and 4 comma 6. So that's why 4th row, 6th row interchange and 4th column and 6th column interchange. So cancel the operation, 6 is replaced with 4. So the remaining is v dagger 4 comma 7. Clear? Now, so I request you please check, this is a v and v dagger I. So the remaining is x of 6 comma 5. That means 5 and 6 are 6th states are interchanged. That's it. Okay, so this entire circuit, the right side circuit, this is equivalent to this Faradacan gate if v square equal to x. Okay, so this cancellation is easy, it's not at all difficult, just see the numbers. If there is no common number, you can write, you can check, you can take the commutation law. Okay, so here earlier we have discussed one control and two targets. Let us take two more examples. Now in this case I have taken u as z, that is 1 0 0 minus 1. Okay, so 1 2 4. So here what you have to take, how to take it separately. So this is the first control z and this is the next cz operation. Then it is 1 2 4. So first one z of 4 comma 6, that means a 4 to 2, and you have to add 1, that is a 5 comma 7. Next z 4 comma 5, you have to add 2, that is a 6 comma 7. Now let me take a 0 1 2 3. Here there is no 0 1 2 3, that's why it is as it is 0 1 2 3. And next I am taking 4 5 6 7. You know that this is off and on, off, on. Now just go from left to right. 4 off, no issue. Next again 4 off, no issue. Next 5 off, but second 5 it is on, -5. Next 6 off, sorry, 6 is on, -6, but the next 6 is off, that's why no issue, -6. 7 first operation on, again on, minus minus 7 plus 7, that's it. Still not understanding? So this is equivalent to first control S gate, and again one more control S gate, 1 2 4. So this is S of 4 comma 6, add 1 5 comma 7. Next S of 4 to 1, that's why 4 comma 5, add 2, that is 6 comma 7. Off, on, off, on. Okay, right. So this is the first column for off, second column for on. Right. So here also I am taking 0 1 2 3, and there is no 0 1 2 3 involved in this operation, so that's why 0 1 2 3 remains as it is. Next 4 5 6 7. So here 4 is off, no issue. Here also 4 off, no change. Next 5 off, but here it is on, that's why I5. Next 6 on, and here off, one time on, that means I6. 7 two times on, I7, again one more I, that's why -7. That's it. Okay, right. So next let us discuss about this anti-control quantum gate. So here we have 2-qubit states, okay, and this is a unitary operator. So earlier we have seen this control operation, okay, but here take a hollow circle like this. So that means this is the control bit and this is the target bit. If control bit is a 0, then only you will operate on target state. Otherwise, it won't operate. It will be as it is. That means initial state is a C. Let us take like this, and this gives if C is a 0. So C as it is, and U operates on T. All these when it will be possible only if the control bit is a 0. That is called anti-control. So if you take this is example 1 and 2, two states are there, that's why I'm giving I have given this a decimal notation, and this can be written as U of 0 comma 1, but don't add that 2. Why you are not adding that 2? Because that is off. See, this is off, that means that is a 0, so you need not to add now. So wherever unitary operator is there, you just take that 0 comma target. Now you got a doubt. Earlier you have written like this. So single qubit quantum gate you have written like this. This is a 1 and a 2. Okay, maybe you got this doubt. You have written u of 0 comma 1, and here also you have written 0 comma 1. Yes. Here in this case, the operation is not only u of 0 comma 1, and one more is there. You have to add plus 2, that is u of 2 comma 3. But here no addition. So the only operation is u of 0 comma 1. Okay, right. So I hope you understand this difference. Now let us take some examples. So here I have this 3-qubit states. Now I'm taking anti-control, control, and this is U, something like this, right? So you may be a single qubit gate operator. You can take A, B, C, D like this, unitary operator. So here I have 1, 2, 4, right? So now here is a control, and this is the anti-control. So earlier how you have done that control, you do the same thing. That means u of, this is a 2 comma, it is 2 to 1, that's why 2 comma 3. But don't add 4 now, that's it. Anti-control, don't add. So here, because of this anti-control, don't add. That's it. And take one more example. Here you have unitary operator, I mean single qubit gate, and here anti-control, but this time this is the control. See that a dark circle as a control and hollow circle as an anti-control. So here we have this decimal notation 1 2 4. Right. So here control is fourth one and anti-control is second one. So wherever you have control operation, just to follow the same operation, that is u of c. C is here, it is a 4, 4 to 1. That's why a 4 comma 5. But now don't add 2. That's it. That is what I'm saying. So take some more examples and let us take here we have u and this is control and this is anti-control. 1 2 4 and this is control and this is anti-control. So this is u of 2 to 4. So that's why the 2 comma 6 and don't add 1. That's it. Next take one more and here we have yeah, anything you can take, it's not a problem. And this time I'm taking here anti-control and this is a control here I'm taking. So 1 2 4. This is u of 1 to 4. That's why 1 comma 5, but don't add 2. So just here I'm writing, don't add 1 and here don't add 2. Right. So the only difference between earlier operations and this operation is earlier we have added whatever the state decimal state remaining we have added, but now don't add that. That's it. Okay. Right. Right. So let us take a few more examples. Here unitary operator we have taken as x. Okay. So I'm giving the decimal notation 1 to 4. Here this is x. This is x of it is coming from 2 to 1. That's why it is simply 2 comma 3 and no more addition of a 4. So this is x of 1 2 4. This is nothing but 4 comma 5 and this is 1 2 4. This is a 2 to 4. That's why 2 comma 6 and this is 1 2 4, 1 to 4. It is a 1 comma 5. So no more addition of 2. Right. Right. So let us take a few more examples. Okay. So here we have 3-qubit states. That's why 1 2 4. Right. And now I'm taking this operations x of 4 to 1. It is a 4 comma 5. X of, see, two controls are there. So that's why 4 plus 2 6. Wait a minute. Yeah. 4 plus 2 6 to 1. That's why 6 comma 7. Next again here two controls are there, 1 and 2. So that's why 3 comma 7. Next x of one control and one anti-control, that is a 4 to 1, 4 comma 5. So any cancellation? No. Just proceed. So here 0, sorry, 0, 1, 2, 3. If this is the initial state, so 0 no change, 1 no change, and 2 also no change, but 3. So please check the operations from left to right. 3 here, 3 to 7, but see, after that there is no 7. Remember, you have to travel from left to right. So now you got 3 here, 3 becomes 7. After that there is no 7, but you will get it out. So before the 7 is there, no, the operations won't go backward. So right, left to right, time travel, left to right. Okay, so this is 3 to 7, so that's why it's a 7. Next 4, 5, 6, 7. Now see, first 4 become 5. Next check any 5. Yes, here last 5 is there, 5 to 4. Like that you have to come from first operation to last operation. And next 5, 5 become 4, 4 become 5. Next 6 to 7, 7 to 3, 7 to 6. That's it. Okay, so in the output state also, no state will be repeated. That is the indication. If any number is repeated, maybe you have done wrong, you have done mistake. So that means what I'm saying is 0, 1, 2, 7, 4, 5, 3, 6. No state will be repeated again. Okay, all right. So we can do this in a easy way also. Let me explain another way. So here we have written the operations. One more time let me take. That is x of 4 comma 5, x of 6 comma 7, and x of 3 comma 7, and x of 4 comma 5. So earlier I told you commutation relations. Okay, so now so here this does not contain any 4 comma 5, no 4 comma 5. So that's why you can bring this side and side by side, x4 comma 5, x4 comma 5 cancel, that is I. So the only remaining is a 6 7 and 3 7. So that means only changes occur between 3 6 7. Yes, exactly. See, 3 becomes 7 and 6 become 3 and 7 become 6. So like this you can do it directly. Now if you take 3, 3 becomes 7 over, and if you take a 6, 6 to 7, 7 to 3, and if you take 7, 7 become 6, like this. Okay. So the remaining states no change, 3 to 7, 6 to 3, no reverse arrow, be careful, 3 to 7, 6 to 3, and 7 to 6. The remaining will be as it is. And see the next one, 1 2 4. So here I'm taking the operations. So here x of 2 controls are there, that's why 6 comma 7. Next x of 4 to 1, that's why 4 comma 5. X of 1 and 2 are control bits, so that's why 3 comma 7. I hope you understand this method. And here 2 is control, 4 is anti-control, that's why 2 comma 3 only. That's it. Now any cancellation here? No, here there is no cancellation. 0 1 2 3. So just check any common. See here why these two commute means there is no common number. Again 4 5 and 6 7, why they commute means there is no common number. If there is no common state, common number means common state, then take a commute. Right. So here a 0 no change, 1 no change, 2 yes. So here 2 to 3, but don't come back again please. 2 to 3. Next 3 to 7, 7 to nothing is there, that's why 7. Next 4 5 6 7. 4 to 5 and 5 to nothing. So 5 to 4, that's it. Next 6 to 7, here 7 to 3, here 3 to 2. Once again, it's nice. Please check again. You are taking 6 to 7, 7 to 3, and 3 to 2. So that's why finally 2. Next 7, 7 to 6, and after that no operation. So that's why 6. And check any number is repeated. Nothing is repeated. That's why almost that means you have done correct. Right. Let us take another one. 1, 2, 4. So here anti-control, and this is anti and this is control. So two controls here, anti-control, right? Okay. Right. So both are anti-control. That means a 0 only. Here x of 0 comma 1, right? Because only x is on 1. So next after that one control is there, that is 1. It is coming from 1 to 2. That's why 1 comma 3. Next x. Two controls are there, 3 comma 7. One control is there, 1 comma 3. So no, I mean both are anti-control. That's why 0 comma 1. Now let us see. Here you have to apply another cancellation rule, which we have already discussed earlier. Still, if anyone not understanding, please check. Now carefully observe. Here this is the operation, some operator or some matrix, whatever it is, some matrix which is, I mean operator is represented by a square matrix. So this side you have x of 1 3, this side you have x of 1 3. What is the meaning of that? One more time I am explaining. If this is the matrix, if you consider, the right side 1 will interchange the rows of 1 and 3, and the left side 1 will interchange 1 and 3 columns. So that means what? 1 and 3, first row and third row will interchange, first column and third column interchange. Means here if you have 3, that 3 stands for third row, third column exists. So that 3 will be replaced by 1. This is the advantage in this decimal notation method. So directly some cancellations, some commutations, all these things we are understanding very clearly. So I hope you are following. So these two operations gone. Next, see again quite interesting. X of 0 comma 1 and again x of 0 comma 1. Now you please check. So this side and this side operation, left and right operations must be same. Then only you can do this. So here x of 0 comma 1 and here x of 0 comma 1. That means here 0th row means R0 you can take. So okay, so no need to get tension. 0 and 1, R0 and R1 will interchange, C0 and C1 will interchange. So that's why this 1 will be replaced with a 0. So finally x of 0 comma 7. I think this question is in this Nelson and Chong book. I think this is very easy to handle this type of problems with this algebra. Actually, if you want to do the original method, you have to take that matrix form and multiplication. And I feel this is a little bit easier than that matrix multiplication. Okay, right. And here one more, 1 2 4. Still not understanding? Please check. Now here I'm writing the operations, that is x of 2 control, 4 anti-control, that's why 2 comma 3. And here 1 and 2 are control, that's why 3 comma 7. So very easy. And here 2 control and 4 is anti-control, that's why 2 comma 3. Now you please try this. Pause the video for a few seconds and please try to do it yourself. So here 2 3, here 2 3 is there. So second R2 and R3 will interchange, C2 and C3 will interchange. So that's why here this side R operations, row operations, and this side column operations. That's why 3 is replaced with the 2. That's it. Okay. Here one question was given in the some exams. Okay, in one of the exam, uh, U operator is given, and here 3 qubit states are there. one quantum circuit is given. So here we have anti-controls A here, and yes, fine. This is the circuit given. They are asking what is the output for this 0 0. In our method, you can find the output of any state, any initial state. That means out of here 3 qubits are there, means we have basis states from 0 to 7. So anything you can find. So they are asking for 0. Let us find. But I am writing the operations for all the states. Okay. So if you want only 0, then you can write u of 0 1 only. But I am writing all the things. Please try to follow. So u of 0, oh, I'm sorry. I have to give the decimal notation 1, 2, 4, right. So this is u on 1, that's why u of 0, 1. Now we have to add, right. So you have to add 2, that is 2 comma 3. And again you have to add the remaining state, that is u of 4 comma 5 and u of 6 comma 7, right. That's it. Fine. And now let us go to the hedge. So h is on 2, so that's why 0 comma 2. So why you are not taking that anti-control? I told you already what is the meaning of anti-control. Don't consider that, it's off, so don't add that 1. So next the remaining is a 4, that's why add 4 only. Next x, it is there, but two anti-controls are there, but it is on 4, that's why 0 comma 4. But don't add 1 and 2. Okay, right. So I hope you got it. Now they are asking for initial state 0. That's why I'm taking a 0 only. This is very nice. Please check. So 0 is operating. I mean, U is operating on 0. So here it is off. Here it is on. Now please check where is this 0 in the operations here. That is U of 0 1. That means it creates a superposition state of 0 and 1. So with amplitudes of a first column, root 2 by 3 0 plus 1 over root 3 1. Nice. Now after that head mod operation is there. So I'm taking like this head mod operation. So please check, and 0 and 1 here it creates a superposition of a 0 and 1. So that's why, sorry, 0 and 2, that's why root 2 by 3 this is 1 over root 2 0 plus 2, because it is off, on, off, on. 0 is off, close, I mean bracket close, 1 over root 3. Okay, so there is no 1 here, so leave it. That means head mod it won't create anything, I mean it won't operate on that 1. So whatever the numbers you are seeing here, so head mod will change will those states only, 0, 2, 4, 6 only, no other states. I hope you got it. This is the advantage of this method, right? And this root 2 gets cancelled, and I'm just writing one more time. This is 0 plus 1 plus 2, right? And finally there is one more operation, that is x, that becomes 0 to 4, that's why 4 plus 1 plus 2, that's it. So this is the final answer. So if you want to do with the if you want to do mathematically, you have to find the matrices and multiply with the initial state, that is 1 0 0 0 0, so on. So because initial state is 0 0, tensor product of 0 0 0. Okay, right. So first please see this first circuit. Here is one more quantum circuit, and carefully observe here. Whenever you have x, control, and x, one more time. So this is here we have x, and this is the control, and x. This is nothing but anti-control. So this is what we get, anti-control. And after that x is the same here, this one, and after that control h, swap gate, and again here the top one. Again you got anti-control. So now I'm going to write the operations for this, that is a 1 and a 2. Okay, so let me write the operations. So first a head mod, that is h of 0 comma 1 and no addition. X of 0 comma 1 you have to add 2 comma 3 and control h. Okay, so whenever control h is there, control to target 2 to 1, that's why it is a 2 comma 3. No more addition. Swap, I'm taking SW, that is 1 comma 2 or a 2 comma 1, anything, it's okay, no issue. Or you can write x of 1 comma 2, it's okay. Swap 1 comma 2, you please write x of 0 comma 1 and add 2 comma 3. Next anti-control head mod, that is a 0 comma 1, x of 0 1 and add to 2 comma 3. So next control head mod, that is a head mod of from 2 to 1, that's why 2 comma 3. Okay, all right. So finally, once we got these operations, I'm taking this 0 1 2 3 at a time I'm taking. So now this is the head mod. So 0 becomes 0 plus 1, 1 become 0 minus 1. There is no 2 as usual and 3 as usual. After that, x operation is there, 0 become 1, 1 become 0, 1 minus 0, 2 become 3, 3 become 2. Next head mod is there, 1 plus 0 as it is, 1 minus 0 as it is, 3. 3 is a linear combination but is on state, so that's why 2 minus 3. 2 is off, 2 plus 3. Next swap gate. So sorry, 1 and 1 to 2 swapping, that is a 1 become 2, so 2 plus 0, 2 minus 0, 1 minus 3, 1 plus 3. Next after that x, so 2 plus 1, sorry, one more is there, please check. So 2 become 3, 0 become 1, 3 minus 1, 1 0, 3 2, 1 become 0, 3 become 2. Next again head mod is there. Okay, so you have to take the one more time head mod operation, but unfortunately, yeah, so this is 3, 1 is off, so that's why 0 minus 1. I'm not taking any normalization constant, finally I will take. So 3 minus 0 minus 1, 0, 0 plus 1 because off state, minus 2 as it is, and 0 plus 1 plus 2 as it is. Now this head mod over, after that some other operation is there, that is x. Still continue. So 3 as it is, and 0 become 1, 1 becomes 0. Oh, sorry. 3 become 2. Careful, you have to observe careful. 3 become 2. Next 2 minus 1 minus 0, 0 to 1, 1 to 0, 1 plus 0. Next minus 2, 2 to 3. Yeah, carefully check. 1 plus 0 and plus 2 become 3. And after that one more head mod is there, so that's why 2 is off, 3 is on, so 2 plus 3 plus 1 minus 0, 2 plus 3 minus 1 minus 0, 1 plus 0 minus 2 minus 3, 1 plus 0 plus 2 minus 3 because 3 is on state. So finally we got to 4, that's why the normalization constant is 1 by 4. The next one is I think that's it. Oh, already we have done all the 4 states, sorry. I thought that I have done only 2, I can give the homework to you, but it's okay. So I request you please check one more time. If any correction is there, please inform me, right? Right. So this is quite interesting one. So here they have given C square X operation. That means C square X gate, sorry. This is nothing but a Toffoli gate, okay? And they are asking to show that this is equivalent to this given circuit. Okay, right. If you want to do with the matrix algebra, it takes so much time, and let us do in a different way. Okay, right. So first let us check what is this operation. Here 1, 2, 4. So this is nothing but 4 plus 2, 6, 6 comma 7. That means it flip only 6 and 7 and the remaining as it is. So here also we should get the same thing. Okay. Now carefully observe the circuit. Don't bother about that so many gates are there, how to do. Here I will tell you a beautiful technique. All of you please see. Now here there is no connection between 2 to 1 from here. Observe, from that line onwards there is no connection between 2 and 1. So that's why whatever the gates you have on 1 you can bring this side. That means what I'm saying, you can take this as separately and two T and H, the last T and H this side. That means like this. Of course in this second part also you have 1, okay, and this is I'm dividing this as a 2 parts, okay. So one more time, and this is the first part and this is the second part, okay, ready. Now I am taking the first part. Here I will tell you a small technique. Whenever, if you observe carefully, all the gates are on that first state, first qubit state 1. So whenever you are having this type of situation, my suggestion, please take it as a psi. And let me take that circuit separately, then you will understand properly what I'm saying. So here, right, so this is what I'm saying. After that you have T and H here, so you can bring this side because there is no connection between 1 and 2. So here it is a T and here it is H. I'm not drawing that boxes, it's okay. Now this is 1, 2, 4. Now carefully see, if all the gates are in a single state, that means one state here, then you please take it as a psi. Then instead of taking this 1 and 2, 4, you can take only these two, that is 1 and 2. Okay. Then this 1 and 2 will form 4 bases, that is a 0, 1 and 2 and 3. That means both off, 1 on, 2 on and 3 both on, like that. So here input states, if you have any confusion, your input states will be 0 psi, 1 psi, 2 psi and 3 psi. So what about psi? Psi is a combination, it may be 0, it may be 1, later finally you can check it. You can take 0 once and you can take 1. So because this will solve very easy, I mean it will take less time, otherwise it takes more time. If you take 1 to 4, so many operations will come. This is one of the advantage whenever all the gates are here, okay, fine. Now let us start. So here I'm taking a 0 and psi, first input 0 and psi. Now carefully see, the entire circuit is operating on this 0 psi. Whenever it is a 0, if both are, that means both are on, sorry, both are off. That's why no control operations, no control operations. So only we have 0 as it is. And here the operations, listen carefully, we are multiplying the matrices. That's why I request you earlier operations, and here we are multiplying the matrices. That's why how to write from right to left. Maybe if you are following that tensor product notation, top to bottom tensor product you will take, right to left ordinary matrix product you will take. So like that you have to take right to left. Don't get confusion. Earlier operations method we are not doing here. The reason is it takes so much time, and if you take psi here and apply like this, it takes very less time. Please check. Please check. Right to left. That's why H, T, no X. The reason is it's off. So T dagger, T, T dagger, H and psi. Now this T dagger, T dagger, that is I, okay, and H into H, that is I. So finally we got 0 psi. Still one more if you are not understanding. So this is 1 as it is because no gate is on that 1, okay, that's why 1 as it is, and psi. So H this time, which is what is on, this 1 is on, okay. So then this C naught and this C naught will be operating on that side. H T, this is off, okay. So no X and a T dagger, yeah, this time it is X, I hope you understand. This one no, next one no, next T dagger, next one S, that is X, H, psi, okay. Now carefully observe. So again here we have T dagger, T dagger, X X I, H H I, that is 1 psi. Next still not understanding, 2 psi. Now this time this 2 is on, that means which gate, this gate, this gate will operate on psi. So 2 as it is because there is no gate on 2. That means now next one H T, okay, yes, this time X is on, T dagger, next X off. The reason is it is here it is a 2 on 1 off, next again T, next X on, next T dagger and X off and H psi. So here also T dagger I, X dagger, everything gone, that's why a 2 psi. And the last one is, it's quite interesting, and if you have this 3 psi, now carefully see, this is nice. So here there is I mean 3 means both on, both on. So no gates on 1 and 2, that's why no need to bother, only bother about that psi. So here all C naught gates will operate because both 1 and 2 on. So right to left, H, T, X, T dagger, X, T, X, T dagger, X, H, psi. Now carefully observe. See, I told you earlier, X operator X from right side and left side, that means rows and columns will interchange. So please identify that. Yes, this is easy. So T dagger I have already written there here. So right side X is there, left side X is there, means both the rows and columns are interchanged. That means the diagonal elements will interchange. I hope somewhere in the earlier videos I told you this technique. So finally here there is no space, that's why I'm writing here. So here H, okay, and I'm checking this only first. Leave that H, okay. So here this is T. So T, that is 100 e raised to I pi by 4. Next X T dagger X. So please go to T dagger and interchange. So that is e raised to minus I pi by 4 0 0 1. And next again T is there, 100 e raised to I pi by 4. Next again X T dagger X is there, that's why e raised to minus I pi by 4 0 0 1. All our diagonal matrix, happily just multiply that corresponding elements, okay, no need to do all these mathematics. 1 e raised to minus I pi by 4, 1 e raised to minus I pi by 4, this will become e raised to minus I pi by 2. Just multiply that corresponding elements because all these are diagonal elements. So sorry, diagonal matrices, 0 and here also 0 and here e raised to I pi by 2. So this is nothing but minus I 0 0 I. I can take minus I common, okay. So this is quite interesting. If I take minus I common, this will become 100 minus 1. Oh, this is nothing but Z. So finally here you have H and here you have H. So minus I outside face H Z H, which is nothing but X. So this is minus I X. So finally the answer is this 3 psi become minus I 3 x psi. This is not the final one, actually second one is there. So you have to combine both the operations. So at a time I'm not taking, because here one method I am applying, and for the second part I will take another method. The reason is there all the quantum gates are not on a single state. So both 2 and 4 it is having some quantum gates. Okay, so now let us take the second part and combine both the answers. Now carefully see one more time. Here 0 psi no change, 1 psi no change, 2 psi no change, and 3 psi minus I 3 x psi. Okay, that means uh, if initial state is a 3 psi, it will convert to minus I 3 x psi. If psi is a 0, it will become 1. Psi is a 1, it will become 0. Right. Now let us take the second part, and here this is a psi as it is. Now I am taking 1 and 2, but here I am taking the operations, because both 1 and 2 are having that quantum gates. Okay, so operations from left to right. Okay, right. So this is x 2 comma 3 and t dagger 0 comma 1 and t dagger 2 comma 3. Next again x 2 comma 3, and here we have two t gates. One is on 2, anything you can take, it's not a problem. T01, T23, and one more t on 2, that's why 0 comma 2, and add 1 comma 3. Now please apply the technique whatever earlier we have used. So this is a 2 3 2 3 interchange, but right side and left side is there, so that's why second row third row will interchange. I mean R2 R3, not second and third, R2 R3 will interchange, C2 C3 will interchange. That's why here 2 will become 3, 3 will become 2. Next after that, here there is no 0 comma 1, so that's why already this is gone. Actually in this there is no 0 comma 1, that's why you can bring this t dagger 01 and t01, you can bring side by side and these two gets cancelled. And finally we left with t dagger 3 comma 2 t sorry t 2 comma 3 and next t 02 t 13. So this is what we get. So remember, maybe here you will get one doubt. So shall I cancel these two? The answer is no. Sir, if it is x, shall we cancel? Yes. X23, X32 both are same, but T dagger 32, T23 both are not same. So because here 3 is off, no phase, and here 2 on, and here 2 off and 3 on. That's the difference. Okay. So then how to do this? I am taking again initial state. This is for second part of the circuit. Okay, and finally I will combine both the first part and second part. Final answer I will combine. 0 psi become, so here no operation on psi is safe, and only the operation is on first initial state 0. So here there is no 0 first, second no 0, here we have, but it is off, that's why 0 as it is and psi is as it is. This is the circuit output. And one psi, so here there is no 1 and here 1 off, that's why no change. Okay, next 2 psi. Okay, careful. So here we have 2 on, that's why e raised to minus I pi by 4, because it is a 2 dagger. 2 psi. Next again 2, sorry, again t, but it is off, no change. Next again 2 on, that's why, but it is this time it is a t. I think it's better to write like this. I think multiplying it's not good. Now let us try this. So here 2 on, that's why t dagger. Here 2 off, no t, and here 2 on, that's why t. This is better. So this is I, no change. Next, this one, careful, 3 psi. Okay. Now here 3 off, that's why no need to write T dagger. But here T, I mean 3 on, that's why T. And here on, again T square. That's it. Okay. So finally, you got a T square means e raised to I pi by 2, because T, you know this one, e raised to 100 e raised to I pi by 4, T square e raised to I pi by 2, which is I 3 psi. Now let us combine all the things. Now I am taking a final both 1 and 2, first part and a second part. So initial state 0 psi, the first part, let me check, there is no change, and second part also no change, and 1. So first part no change, second part no change, and similarly 2 psi, first part no change, and the second part of the circuit no change. But here third one, so the first part make it as a minus I 3 psi, and the second part make it as a I 3 psi. That's why minus I, that is a 1 only, so 3 psi. Sorry, I'm sorry, 1 minute, I'm sorry. Yeah. Right. So here this first part makes minus I 3 x psi. Be careful. Minus I 3 x psi. Next, second part make 3 psi. That means 3 become I3. Here already minus I. Here I is there. So that's why it become 3 only. And x psi as usual. So finally, the operation, this is 3 psi become 3 x psi. Now you please give the option. So for example, it is either 0 or 1. Okay. So here it is a 3, this is a 0. So here we have 2 qubits. That's why 2 3 is a 6 plus 0, 6. Okay. And here 2 3 is a 6 plus 1, 7. Okay. So then it become, so here for 0 it become 1, and for, sorry, for 1 it become a 0. So that's why 2 3 is a 6 plus 1, 7, and 2 3 is a 6 plus 0, 6. That's it. That means 6 become 7, and 7 become 6. So finally we can write this as x of 6 comma 7. So this is what we get here. It will flip 6 and 7, and here also we are getting the same thing. Okay. So I hope you understand and carefully observe. This is whenever all the gates are on one single state, you can apply this technique, taking psi. Right. So let us take the another equivalent circuit, and here we have anti-control and here control, and this is x 1 2 4. So this is nothing but x 2 comma 3. Now we have to show that from this circuit we'll get the same output, and carefully observe the difference is earlier here we have all this one T gates, but first part is as usual, I think. um yeah, no, first part is also having a small change. Okay, fine. So let us divide this into two parts, and this is the first part and this is the second part. Now I will explain this, and the next one I'll give you as I will give it to you as a homework. Please try to do it. So let me take the circuit again. Right. So here I have taken the first part, okay, and all the gates are on first state. That's why I'm taking this as a psi, and these two are 1 and 2. So save. Here we'll get 0, 1, 2, 3 possible cases. Okay. Now I'm taking it directly because already you understand this method. So 0 psi. So here only the operations on psi, but both are off. That's why there is no X gate. So 0. You have to take from right to left. So this is H, T dagger, T dagger, T, T, H and psi. So this T dagger I and everything is gone. That's I, identity operation. And the next one, so in this case, this C naught and this C naught will operate, and these two won't operate. So this is a 1 because 1 is on. So H, T dagger, next one off, next one T dagger, next one on, X, T off, again T, next off, sorry, on, H psi. Right. So carefully observe, here we have T dagger square and here we have T square. So I told you already one technique. So this is a T dagger square. So here I'm taking this as a 1 0. Let me write here because it's a space is there. So here I'm doing for one side. So this is a T dagger square, that is 1 0 0 e raised to minus I pi by 2, and after that we have T square but X, this side X and this side X. T square is nothing but 1 0 0 e raised to I pi by 2, but both the sides we have x x, that's why no need to multiply, directly e raised to I pi by 2 0 0 1, just interchange that diagonal elements, and this is nothing but I 0 0 minus I. Okay, so this is nothing but I common, that is a Z. So finally we can write 1 I outside, H, Z, H psi. H, Z, H is nothing but X. I 1 X psi. That's it. Okay. Next is still not understanding. 2 psi. You please pause the video and try to do it yourself. That is a 2. This time these two on, these two off. So H, T dagger on, T dagger off, T on, X, T off, and again H. So please check, and here side by side and gone, this is nothing but 2 psi and 3 psi. So this is a 3, all are on, that means H, T dagger, X, that means all C naught will operate, X, T dagger, X, T, X, T, uh, X, H. Okay, so fine. Now here we have some operations here. I hope you understand. Please take like this. Okay, let us proceed. Now here X, T dagger, X. Forget about H and carefully see this T dagger. I'm writing from here 1 0 0 e raised to minus I pi by 4, and here X, T dagger, X, take T dagger but interchange the diagonal elements, that is 0, oh, sorry, e raised to minus I pi by 4 0 0 1. Next after that we have T, that is 1 0 0 e raised to I pi by 4, and here we have x tx, so interchange the diagonal elements of t, e raised to I pi by 4 0 0 1. All are diagonal elements, just multiply. So it's gone 1. Oh yes, 1 0 0 1 I. So finally this is a h square, h square is also I, that's why it become a 3 psi. That's it. Okay, now we have to take the second part of this. So once again please check what is the result. 0 1 no change, 1 psi, yeah careful, I 1 x psi, 3 psi no change, 3 psi. Okay, now let us check the second part. Now please take this last state as a psi only. This is the second part of the circuit. Now here we have these operations 1 and 2. First one x 2 comma 3, next t dagger 0 comma 1, again t dagger 2 comma 3, next again x 2 comma 3. Now this time we have t 0 comma 1, first one, and add that to 2 comma 3. Next again 0 comma 2, this time add 1 1 comma 3. So this is x 2 2 3 and 2 2 3. So 2 will become 3, 3 will become 2. And this t dagger t gets cancelled. So finally here we have t dagger 3 comma 2, t of 2 comma 3. I'm sorry, I think this is a t dagger. I'm sorry. Yes, we made a mistake. One second. I'm sorry once again. So here this is a T dagger. So T dagger, and this is also T dagger. Okay, right. Fine. So this one as it is, 2 3 2 3 cancel, 2 become 3, 3 become 2. So finally here we have T dagger 0 1, T dagger 0 1, that is a T dagger square 0 1. And after that T dagger 3 comma 2 is there, and finally here we have uh, T dagger 2 comma 3, because already 0 1 gone, and after that again we have T of 0 2 and T of 1 comma 3. Fine. Now I am taking 0 psi. Psi no operation, only 0. Okay, so here 0 off, that's why no issue, and here also 0 off, that's why no issue. Next 1, if it is on, take that operation, off, leave it. So 1 psi. So here 1 is on, that's why T dagger square 1 psi. And next come to here, there is no 1, and here 1, but it is off, that's why T dagger square 1 psi, T dagger square, that is yeah, if you want you can write a T dagger square, that is 1 0 0 minus e raised to minus I pi by 2, that's minus I hope you understand. So this is 1 0 0 e raised to minus I pi by 2, that is minus I 1 psi. Next second, let me write here, here 2 on, that's why T dagger, here 2 off, and here again 2 on T. It's very easy. So this is again 2 psi. Next 3 psi, 3 off, 3 on, that's why T dagger, and T, I mean 3 on, but it is a T, so 3 psi. So which is nothing but 3 psi. I hope you understand. So if it is off, leave it. If it is on, take that operation and multiply. Okay. So that's it. And finally, we got this from 2. Now I'm combining both 1 and 2. And let us check. So here 0 psi, first one no change. So please one more time please check, no change. 1 psi become this one, be careful, 2 and 3 no change. So second one also no change. And here the first one, this is I1 x psi, I1 x psi. The second one is this one, minus, because here we have, I think here we made a mistake. This is e raised to minus I pi by 2 is a minus I. Okay, that's a small correction. So minus I. So then minus I gone. That's why, that means 1. This I, and this is a minus I. Okay, 1 state into x psi. So here we have some change. The remaining 2 psi and 3 psi, no change. So now let us take this final operation, that is only one change, that is 1 psi become 1 x psi. So here I can take this psi as a 0 or 1. So see how I am doing this. This is a 2 qubits are there. Okay, so that's why 2 ones are 2 plus a 0, that means a 2, comma 2 plus 1 3. So this will give either 2 decimal state or 3 decimal state. Okay. Yes, and here because of this exercise, you will get 0 become 1, first one, here 1 becomes 0. Okay, so this 1 2 qubits, that's why 2 ones are 1 plus 1 3 comma 2. So the finally we got 2 3 become a 3 2. So this total operation can be written as x of 2 comma 3. So exactly whatever we are getting here, this one, right? And the last one I'm giving you as a exercise, so I request you please do that last one, and if you have any doubt please contact. So here I'm giving you as a homework, I request you please try, and please take this as a first part and this one as the second part. And here we have this is 1 2 4, both are anti-control, these are both are anti-control, that's why this is x of 0 comma 1. So finally once you simplify this right hand side circuit, you have to get finally 0 to 1 1 to 0. So please do it. Okay, and take separately first circuit and second circuit and try to do it, and if you are not getting any, if you are not getting the answer, please contact. Okay, so thank you.